Hello everyone. Today we are going to learn about PLC. Let's start with its introduction. So PLC, it is programmable logic controller. Okay, generally what is controller? A controller is used to control some operations. Fine, that is what controller meant to it, right? Okay, so PLC is a dedicated controller specially used in an industry. Okay, so PLC are used in every aspect of industry to expand and enhance its production. For its production only, mainly PLCs were introduced in the industry. Okay, so in generally the definition of PLC can be, it is a unit of hardware used to control and automate the industrial process. Fine. So let me share the evolution of PLC image. So this is the evolution of PLC. So once upon a time we were into the manual control. Okay. So can you find an image over here? A man who is operating a hand valve by looking into the temperature gauge. Okay. He's very nearer to the furnace. According to the temperature range, he is going to change the hand valve. Okay. Do you think it is really safe for a human being who is always nearer to the furnace? Obviously no. And the second thing, as an industry point of view, obviously we are losing a precision and accuracy over here. Fine. So this is the main problem in a manual control. Okay, that's what we have shifted to the hardware control. Okay, so what is this hardware control? This is nothing but a relay control system. Okay, so older automated systems were used hundreds and thousands of relays. Okay, so obviously we know relay, right? It is a electromagnetic switch. Okay, for to make a simpler simple control system, we are in need of more wires to make it possible. Okay, so a single PLC unit can replace the hundreds and thousands of relays. Okay, that is the main thing. That's what we have faced so much of difficulty in this hardware control. So one of the main disadvantage over here is it is really tough to find where the fault occurs. If, for example, in a simple control system, there is one error in a wiring, okay, and it's really hard to find because we are into thousands of wires. Okay, there is one statement in the control industry. They will tell the relay control system as if the fault is happening means it is 5 hours to find the fault and 5 minutes to fix it. Okay, that is one of the main disadvantage in this hardware control system. That's what we have moved into the electronics control, which is nothing but a PCB designing and all. Okay, so there was a problem with the troubleshooting and the cost also. Okay, that's what we have shifted to the PLC control. Okay, PLC is a specialized computer used to control the machine and the process. Okay, it using the programmable memory to store the instruction and execute the functions that include on-off control, timing function and counting function, sequencing, logical, arithmetic and data handling functions. Okay, so the design of most PLC is similar to that of other computers, normal or personal computers. Okay, but it is specially for the manufacturing process equipments and machinery. Okay, unlike an office computer, it has been designed to operate in the industrial environment. Obviously, in an industry means a controller need to run for 24/7, right? So PLC can withstand those temperature. Okay, because it is equipped with special input and output interface and control programming language, right? Yeah, let's see the architecture of PLC. Yeah. So yeah, before that, I would like to introduce him. He is Richard Dick Marley, who is the father of PLC. Okay, in 1960s he has introduced this PLC and he is a father of PLC. Let's move on to the PLC architecture. So as I have already told, it is similar to our personal computer, right? So our personal computer, obviously it is having a processor, correct no? So it is having a processor which is a brain of the control system. Okay, so before that, let's have a look into this power supply. Okay, it is used to power the CPU and other field devices, right? It is a source, it is giving the source to all the devices. Okay, and let's have a look into this input and output module. What does this means? It is act as a bridge which is connecting our input and output devices with the CPU. Okay, is used to give the communication between IO devices. That means field instruments like push buttons, switches, transmitters, control valve, solenoid valve, VFD. So these are all the field instruments. So it is making a bridge between those field instruments and the CPU. Okay, and can you find the optical isolation over here? Okay, it is an isolation barrier. Okay, to electrically isolate the internal components of CPU from the IO terminals, PLC employs an isolation. Okay, so and coming back to the CPU, it is a brain of the PLC and it is having a processor used to perform logic and controlling the communication among the modules. Okay, user can enter the desired circuit in the ladder logic program, okay, which is by using this programming device. Okay, the processor accepts the input data from various input devices and execute the program which is stored in the program memory and send the signal to the output device. Okay, so and this one programming device, this may be a handheld device in our older days, and now we are using PCs and laptop where we are installing our PLC software and we will be writing the program into it. By using the communication portals, we are downloading and uploading the program into and from the PLC. Okay, so these are all the main components we have in the PLC, and apart from this, additional components, we may have an operator interface device to allow the data entry and data monitoring by the operators. And the second one is communication adapters for remote IO, so that the central controller can be connected to remote sensor and actuators. Okay, and the third one is a network interface, which is allow the interconnecting of PLCs with other controllers and the distributed control system. Okay, so the above three are the additional components, but these five are the very important components that you can find in all the PLCs. Okay, so let's move on to the advantages of PLC. Okay, let me share one more image. Okay, so advantage of PLC. So why we are using PLC over the previous control systems? Okay, let's see the first point, which is increasing the reliability. Okay, so here once a program has been written into the PLC and is tested, it can easily download to the PLC. Okay, since all the logic is contained in the PLC memory, there is no chance of making the logical error. That is one of the main advantages in a PLC. Okay, this program takes a place of much of the external wiring that would normally be required for controlling of the process. Okay, hard wiring is still required to connect the field devices, but it is very less comparing to the relay control system. Okay, so that's what it is, increasing the reliability. Okay, the second point we can see is it's more flexible. Okay, so more flexible in the terms like it is not really easy to wire and rewire the circuit, correct na? But in a PLC, changing a program will be very easy. End user can modify the program in the field, or if desired, security can be provided by features such as key locks and passwords. Okay, it is more flexible. And the third point we are having is a communication capability. Okay, so PLC can communicate with other PLC and other computer equipment to perform some functions. Okay, it can easily communicate with the SCADA systems, HMIs and other PLC and all. Okay, and also it is used for the uploading and downloading of programs. Okay, so comparing to the previous control system, here the communication capability is having more features. Okay, the next one is faster response time. Okay, it operates in a real time, which means the event take place in the field results in the execution of the output. Okay, and the next is easier to troubleshoot. It is having a LED indication, okay, to easily find out the faulty IO to fix the problems. User can display the control program on the monitor and watch it in a real time as it executes. Okay, by using all these, we are finding more advantages in the PLC. Okay, so this is all about the introduction of PLC. Meet you in the next session. Thank you. Hello everyone. In our previous session, we have seen about the introduction of PLC. And in this session, we are going to see about the types of PLC. So in generally, PLCs are categorized into three types. The first one is depends on size. The second one is depends on hardware setup. And the third one is power supply. Let's discuss one by one. First, depends on size. The criteria used in categorizing PLC in this type are functionality, the number of I/O points, cost, and the physical size. Okay, so majorly the count of I/O points is the more important factor in this type of PLC. So depends upon that, they are categorized that into the 5 type. One is nano, micro, medium, large, and very large. So according to these type of PLC only, industries, small scale industries, medium scale and large scale industries are preferring their PLC. So if you look into the nanotype PLC, it is having up to 16 I/O points. So it may be an entry level PLC that is more enough to fit into your chute packet. That much small it will be. Micro PLC can connect up to 32 I/Os. You can find the application of these two PLCs in elevators. Some car washing applications are mixture machines. The next one is the medium and small scale PLC, small PLC. So you can find this family mostly, it is having a maximum of 960 I/O points in a single rack. Okay, and most of the small and medium scale family will have a modular type, because it in some cases if they want to expand the number of I/Os, means they are having some option for the expansion module. Okay, let's discuss about the expansion module in the next type of PLC. Okay, and the next one is the large scale, which will be having 1000 I/O points. PLC of this type have almost unlimited applications and can control individual production process or the entire plant. Very large scale PLC will have more than 10,000 I/Os, and these type of PLC capabilities are quite higher than the medium scale. Okay, in terms of memory, programming language and all, I/Os and communication modules and so on. So these type of PLC are used in SCADA and distributed control system. So that's it about the size. So depends upon the size, PLC are categorized into these 5 types, and these 5 types are used in various types of PLC industries. That may be small, large, and very large. And the next one is depends upon the hardware setup. And this is very important one. If you see, we have 2 types over here. One is compact, another one is modular. So let's see into the compact type. Can you see a pic over here? Can you see a pic over here, which is the example for the compact type PLC? Every components, all the modules are inside this box. Okay, all the modules are inside this box. Power supply, CPU, what and all we have seen in the architecture of PLC. I/O modules will be there, no? That one, power supply, CPU. So everything will be in this one box. Okay, number of I/Os in this type is fixed by the manufacturer but not by the user. It is built by several modules within a single case. Some PLC of this type is designed to connect expansion module to make them somewhat modular. So what this means, for example, this PLC is having 6 I/Os. Let it be 10 I/Os, maybe 4 inputs and 6 inputs and 4 outputs. Okay, suppose you are preferring this in your project. You are running out of I/Os. For example, in your project, you are in need of 15 inputs and 4 outputs. So in that case, if you are using this PLC, it is insufficient, right? Because this PLC is having 6 I/Os, 6 DI and 4 DO. But you are in need of 15 DI and 5 I/O, 4, maybe 5 DO. Okay, so in that case, you are running out of I/Os. So in that case, some PLC are offering an expansion module. Okay, that means you can connect a extra module which will be supporting you with the running out of I/O modules, no? If you are running out of inputs and outputs, you can make use of this expansion module to add the extra I/Os that you are in need of. That's what this compact and integrated type PLC. Okay, the opposite to this type of PLC is the modular type, where all your components. For example, power supply, CPU, IO modules, everything will be in a separate one. Okay. So unlike a compact type, it is not in a single box. All the components are in an individual box combinedly that are plugged into the rack. It contains power supply, CPU as we have discussed. Okay. So which may be a form same or from the different manufacturer. It depends. Okay. So that's it about the second type of PLC. Depends upon the hardware setup. And the first one is compact and the next one is a modular type. Fine. Yeah. The third type of PLC is depends upon the power supply. Okay. So this is very important one because most of the PLC have their own power supply module cards which act as a SMPS to provide supply to the rack, which in turn supply to the different cards like analog input, analog output, DI module, DO module, RTD, etc. So most of the power supply module requires 220 volt AC or 24 volt DC, which turn converts into the required supply signal for the cards, which is typically maybe 24 volt, 12 volt or 5 volt. Okay, so basically to power up the PLC, we are in need of 230 volt or 24 volt. Okay, so how we are going to give this? For example, you can find a PLC which is accepting 230 volt, and obviously in some PLC which are not accepting 230 but it will accept 24. So what is the difference between these two means? If you are giving a AC supply to the PLC means, so that means it is having a SMPS within the PLC. Okay, so that's what it is, converting the 230 into the 24. In some PLC, we need to give the power supply of 24 volt. That means it is not having SMPS inside. We need to have SMPS outside. So that's the category of with SMPS and without SMPS. That means whether the PLC is having the SMPS inside or not. This is a basic idea of the PLC depends on power supply. Okay. So the next slide we are going to see about the PLC brand. So like our mobile phone which is having various brands like Apple, Lenovo, like that, no? Like that PLC is also having various brands, and here I have listed out the most popular PLC brand: Allen Bradley, Siemens, ABB, Omron, Delta, Honeywell, GE, Modicon, Schneider. Okay, so these are all the very popular brands used in the industry. I hope you have understood the types of PLC and its various features. So let's wind up the session 2. We'll meet you all in the session 3. Thank you. Hello everyone. In our previous session, we have seen about the types of PLC. In this session, we are going to see about the PLC programming language. So when it comes to PLC programming language, we have 5 language over here. The first one is ladder logic. Next one is functional block diagram. Next, structured text, sequential function chart, and instruction list. Let's see a gist of information about all these programming language. Okay. So, ladder logic. So, it is a graphical representation of the process with the rails and rungs of logic. Let's discuss about this rails and rungs bit shortly. It's somehow similar to the relay ladder logic technique that were replaced by the PLC. Okay. The next one is a functional block diagram. It is a depiction of simple and complex building blocks like logic gates to closed loop algorithm and control. Fine. So, for example, if you want to perform the AND gate, so there will be the AND block over here. You can take and make use of it. Fine. Next one is structured text. This way of programming similar to the object-oriented language to provide high-level syntax using control statements. Up next is sequential function chart. It's similar to the function chart. We know, right? There will be yes or no function. If yes means do some action, no means do some other action. So it is similar to that. Okay, which is having one or more action and transition. Fine. Next one is instruction list. It is a text-based language for building small and complex system. So these are all the 5 programming language we are having in a PLC. Now we are going to study about the ladder logic. Let's see about the introduction of ladder logic. The first point we are having here is originally designed. Ladder logic is originally designed to represent construction and design of relay racks. So we were into the hardware control, which is nothing but the relay control system. Fine. So there we were using this ladder logic to document or represent construction and design of relay racks, as they were used in the field of process controlling and manufacturing. Fine. So each of the device included in the rack was represented in a ladder diagram with the help of the symbols. So with the advancement in the technology, these relay racks were replaced by the PLC. So we were using ladder logic for the relay racks to represent the construction. Now we are using this ladder logic as the main programming language in the PLC. The next one is, it is a deployment of ladder diagram as a foundation stone of the new programming language can be declared as a practical. Next, why ladder logic got its name? Because programming this language resembled the ladder. We were using, we will be using ladder to climb the height, right? So it is similar to that. It is also having the vertical and horizontal lines. That's what ladder logic got its name. So we are going to study about it. So you will be getting the clarification on this point very shortly. The next one, it is a widely used programming language in the industry. Fine. So yes, why it is very popular programming means it is having a history on its side. Fine. So it is easy to troubleshoot and easy to learn and teach. That's what it is widely used programming language in the industry. Next we are going to see about the components of ladder logic. So here we are having the 4 components. So the first one you are seeing here is the power rails and rungs. So I have told you, right, rails and rungs. So can you see the 2 vertical lines over here? So these 2 are the rails and the horizontal lines are called as rungs. So rails are also called as power rails because we are going to give plus and negative over here. That means it is going to give the power supply to the components. That's what it is called as power rails, and the horizontal lines are called as rungs. The next one is a normally open contact. It is nothing like a switch. Normally we are using switches to turn on the outputs, right? It is similar to that. And next one is a normally closed switch. These 2 are the 2 input contacts we are going to use in the ladder logic. Fine. So normally open contact, what it will do means, whenever we are going to turn on, it is also simply called as NO contact. So NO contact means it will be making the circuit. That means whenever it is turned on, that time it will be giving the output. If you are turning off, it will not give the output. Opposite to this normally open contact is normally closed contact. What it will do means, if you are not disturbing the switch, if you are not turning on the switch, it will not give the output. It will give the output. So if you are turning on, it will break the output. It will break the circuit. So simply it is making the contact, it is breaking the contact. The next we are having a output coil which is used to give the output. So all these components are very important when it comes to ladder logic because these components are ruling the ladder logic. Fine. So let's see about the do's and don'ts. So do's and don'ts in the ladder logic. So all the contacts should be in the left side. So we have seen about NC and NO contacts, right? So that contact should be in the left side of the ladder logic, and all coils should be in the right side. We have seen that output coil, right? That should be in the right side of the ladder logic. Output should not be in the series. That means only one output should be in a rung. If you are having a multiple output for the single input, that output can be connected in the parallel contact. Okay, let me share the whiteboard to discuss about it in a better way. Just have a look into this. So here I have Yeah, I have drawn the contacts and coils over here in the ladder logic. Okay, just have a look into this. This is a normally open contact. I have represented that as X1, and this is no NC contact, normally closed contact. I have represented as X2, and these two are the coils. So parallelly I have drawn one circuit over here which is similar to the first rung. So this is the rung where I have placed all my components over here, and this is the second rung. I have placed the remaining, the next components, next set of components here. Okay, so the first rung is represented as a circuit over here. So I think we are very familiar with this type of circuits, right? We have done in the electrical and electronics lab. So this is a power supply we are giving to the switch. Since the switch is open, Y1 is off. Correct. The same thing is represented here. X1 is in an open condition, so Y1 is off. So whenever we are closing the X1, means the circuit is getting the closed loop, so Y1 is on. Okay, this is what the concept is, right? The same thing here. Whenever you are closing the X1, it will allow the power to get into the switch to reach the output. So output is on. Okay, so here it is a power rail, no? So it is represented as plus and minus over here. Fine. And the next over here is X2, which is a normally closed contact. So initially Y2 will be on. So it is depicted here as a circuit. So it is initially getting the closed loop. So Y2 is on initial stage itself. Okay, so here X2 is initially on, so Y2 is on. So when you want to break a circuit means you will be disturbing the switch. Disturbing the switch in terms like you will be turning on. That means you will be open the switch. That means the switch will be going over here, right? So Y2 will be off. The same thing, Y2 will be off here. So this is how the ladder logic works. Fine. So we have discussed about the do's and don'ts, right? So all the coils should be in the right side. That means all the output should always be in the right side. You cannot put this coil in this place. Fine. Same thing, all the contacts should be in the left side. You cannot put the contacts over here. This is wrong. Fine. The third point we have seen about output should not be in the series. For example, see here, you have another output here. Let it be some other output. Let it be like Y3. Right. So this one should be represented in a ladder logic. Same as here as parallel. So output should not be in the series. In another way, you cannot connect the output in the series. It should always be in the parallel. Fine. So these are all the do's and don'ts in the ladder logic. So let's wind up the session over here. Let's meet you all in the... Hello everyone. So in this session we are going to see how to download and install the Schematic Manager. So Schematic Manager is the place where we will be writing the PLC program. So this ladder logic page will be coming within this schematic package, and even we are having the simulation window also. So let's see how to find the file in Google. So just go to the Google page, and here you can type the Schematic Manager version 5.4 free download. So just click enter. So it will give you the Siemens support pages you can find here, and just click on the first option. This is the version we were looking for, so just click on that. So now it will enter into the Siemens support page. So to download the file, we need to have an account in the Siemens website. So then only it will allow you to download the file. So just create an account by clicking a sign up button over here. Already I have signed in, so it is listing my name and logout option. If you are not having, go with the sign up button. Once your verification is done, you can able to download the file. You can find the file over here, the option number 2, free download. You need to click for this zip file. Once you click, it will ask you where to save the file. Just wait for it. Yeah, so it is asking where to save the file. You can give wherever you want, and once it is save option is given, it started downloading. And once it is downloaded, you can extract the files and you can go to the setup option to install the Simatic Manager. It will be the regular software download options only, so no, you cannot find any difficulties in that. So just find the setup file and go with the OK options wherever it requires. So this is how we need to download and install the Simatic Manager. Hello everyone. In our previous session, we have seen about the basics of ladder logic. In today's session, we are going to study about the Siemens S7 Simatic Manager. Okay, so Siemens is a very well-known brand when it comes to the PLC. So let's move on to the topic. Yes, so step 7 is the standard software package. Okay, so which is used for configuring and programming the Simatic PLC. That means Simatic means it's a Siemens brand. Okay, so it is used for configuring and programming the Siemens PLC, and it is a part of the Simatic industry software. And there are so many versions when it comes to the Simatic Manager. So you can see the version here, step 7 micro DOS and step 7 micro Win, which are all for the simplest standalone application. Okay, that means you can make use of the controller like S7 200 series. Okay, the next one is Simatic S7 300, 400 or 1200. These are all the series of Simatic PLC, and it is used for the wider range of function, which may be the global data communication, configuring connection, opportunities of assigning parameters to function modules and communication processor. Like that, it is having a wide range of functions. Okay, and in this course, we are going to study about Simatic S7 series 300. Okay, so 300 is a CPU series. In that CPU series itself, we have another kind of series which is called as 313C. It is a CPU type. Okay, so in this course, we are going to study all the concepts and examples by using this series only. Fine. And Simatic S7 300 series is a modular PLC. So in the session 2, we have seen about the types of PLC, right? In that we have two types. One is integrated, another one is compact. So this integrated means what? Modular means what? All the components will be present as an individual slot. Okay, like that. 300 series is a modular type PLC where it will be having some rack. In that rack, you are going to keep all the components like power supply, CPU, IO modules, like that. You are going to keep all the components in a separate place. Okay, that's what it is, modular PLC. The third point is this CPU. This particular Siemens 300 series 313C CPU is having 24 DI, 16 DO inbuilt. Fine. So for example, for the required project, we are okay with this. We are more enough with this DI and DO and AI and AO means you can proceed with this CPU. Else, if you are in need of more DI or more IOs means you can go with the expansion modules. Fine. So these are all the inputs and output count which are all inbuilt in the CPU. Fine. And moreover, as like others, PLC has a range of individual CPU. Okay, differing in performance, installation, number and type of ports for connection of other device. Each CPU can be extended with other modules of individual digital input, output, analog signals and special modules, and moreover another one is communication interface. Okay, and here by using MPI cable they are making the communication. There are two type of cable, one is PPI, another one is MPI. PPI means point to point interface, MPI is multi-point interface. So by using MPI cable, here we are going to make the communication. Fine. So that's it about the basic information about the 300 series. Fine. Now move on to the addressing part. So addressing is very important in PLC because it is used to represent the location of the input and output. So all the inputs and outputs, that may be a digital or analog, whatever it may be, it should have a proper address because that address we are going to represent in a ladder logic. In our previous session, we have used the example like X1 as a contact and Y1 as the coil. So X1 we need to give us some address. Same thing for coil also we need to give some address. If we are not giving the address means PLC is failed to detect the location of the IO. That is the main thing. So depends upon the data type only, here addressing is getting varied. So when we are talking about the data type, we are having bool, integer, word, double integer, double word and real. So these are all the main data types we are going to use in the ladder logic. So obviously bool means it is binary, it is going to take a single bit. But when come to integer, word, dint, dword, real, these are all for the analog IOs. So these are all the registers where we are going to store our analog values. So if you are talking about the integer, it is a 16 bit. It will take a 16 bit. So double integer will take 32 bit. Same word will take 16. Double word will take the 32 bit. And real, that is nothing but a floating point number, will take a 32 bit to store its value. Okay, so these are the basic idea about the addressing part. And in Siemens, how we are going to address the IOs. That is what we are going to see in the next slide. So let's see about the input addressing over here. Right. So input addressing. For example, we have used that example in the previous one, no, X1 and Y1. So X1 is nothing but a one contact. That is one digital input. So for that, we are going to give one address, means we will be taking this I0.0. Okay. So how here they are preferring the address means here they are splitting the address with a channel. So each channel will have a 8 inputs. Okay. So here there are, if you count it, you will get the 8 inputs over here. Fine. So there are input addressing and output addressing also. So each channel will share the 8 bits. So for example, for one digital input, you will be taking a 1 bit. Fine. Suppose in your project, if you are having a 9 inputs you are going to use, means you will be taking I0.0 for your first input, second, third, fourth, fifth, sixth, seventh, eighth, and this one. So totally you are having a 9 inputs. You will be using a addressing like this. Fine. Same thing. I means here input. It is representing the input. Same, can you look out the output addressing? Here we are representing the output with a Q. Fine. Q0.0, Q0.1. So it is like a nothing but a bit. So on the whole, if you look into the all 8 bits is a one channel. That means 1 byte. 1 byte is a one channel. And in one channel we are having a 8 bits. So in one channel or in 1 byte we can take the address of 8 DI. Okay, if you are looking at this, it will be 8 DO. Right? This is for digital IOs. Okay, and the same thing we will be using memories obviously in our PLC. So if you are using a memory contact or coil, that will be the indicating as M0.0. Like that, here also per channel will have 8 bits. Fine. So how long it will go means it will go up to 127 channel. All for input, output and memories for all, it will take up to 127 channels will be there. Fine. And these are all for the digital IOs. How about analog? How about the register address? For example, instead of bit, you are having an integer number. How we are going to store that? Obviously, integer will take a 16 bit, right? We have discussed in the previous slide. integer will take 16 bit to store the value. So in that case, we will be referring that as MW0. And why I am not using MW1 means, since one channel is having 8 bit, integer will take 2 channel to store the 16 bit. That's what MW0 and MW1 will take a single integer. Fine. For the next integer, if you want to store means, that will go up to MW2 and MW3. Right. Now 32-bit input. That may be output also. Okay. For that, we are going to use MD0. That means, see here, the next 32-bit will be MD4. That means MD0, 1, 2, 3. So 4 channels will take the 32-bit. 4 8s are 32. That's what the concept is. Fine. So if you are representing the integer with the MW0, automatically it will take MW1 for that. Same here. For the 32-bit representation, if you are taking MD0, automatically it will take 0, 1, 2, 3. So 4 channel it will take to store the 32-bit. I hope you have understood the addressing part. Let's move on to the ladder logic program in the software. So here we are going to use a schematic manager. So I'm going to share the software now. Fine. I hope you are seeing my screen. So schematic manager is a software we need to open. Just wait for it. It will take some time. Yes, so it is a schematic manager. Once it get open, go for file, new. So it will be asking you to create a new project. I'm just giving. Just click OK. Since it is in a VMware, it is taking some time. Yeah, can you see here? The project we have created is here. So right click on that. Go for insert new object. So since we are going to study about the schematic 300 station, click on schematic 300 station. Yes, so it is created. Again, double click on that. It will take you to the hardware option. Again, double click on that. It will take you to the hardware configuration page. So in this place, can you see the slot and designation over here? So right click on that. Insert object. So again choose schematic 300. In that select rack 300 and choose rail. We have already discussed that schematic 300 is a rail type, modular type PLC. So modular means obviously it will be having the rail in a back plane. Okay. So here see here. So here we are having 11 slots. So in the first slot usually it will be the power supply, right? So in the first slot usually it will be the power supply. So you can add here by double clicking or right clicking. Insert object. You can choose any power supply, whatever you are having. And the second slot, obviously, it will be your CPU. Go for insert object. You are going to see CPU 313 series, C series. You can choose any version. Since it is a simulation, you can go with any version. Yeah, so it is created now. Can you check it out here? When you choose in this 313C, obviously it is giving DI24, DO16, AI5, AO2. So it is listing out how many IOs it is having. Okay. One more step is pending, that is click on this DI24. It will take you to the property page. In this property page, go to address. Check out this system default, because here we need to give 0. It is an optional one only. For example, here if it is 124 is the default one. That means in your program you need to start your IO addressing will be like I124.0. For the next input I124.1. Like that you need to use. Okay. So I don't want that. I want to start with a 0. So if you give 0, automatically it will take 2. So totally 3 channels, because 24 DI, right? 24 DI means it will be taking 3 channels. Same here, I am going to start output with a 0. So automatically it will take 2 channels. So click on OK. Same for analog also. I want to start with the continuation. Already we have used 3 channels for input. So here I am going to start with the 3. Here I am going to start with the 2. Fine. So why I have given 3 is for the digital input I have used the first 3 channels. So the next one is started over here. The first 2 channels was used by the DO. So for analog output it should be started with the 2. That's it. That's it. Click on save and close this page. Yeah, fine. So see here your CPU is created here. Click on that. S7 program, blocks, OB1. So organization block. So this is the main page of our ladder logic program. Double click on that. It will take you to the property page. Nothing need to do here. You just see here. There are 3 languages we can write in this schematic manager. I'm going to go with ladder. Just click OK. So it will take us to the programming page. Yeah, so this is our programming page. Here only we are going to write a program. In our previous session we have seen about this normally open, normally closed and coil contact, right? Let's see one small example here. In our course we are going to do the ladder logic by using a simulation method. So let's connect one simple program. The same thing we have discussed in the previous session. So this is a rail and this is a rung. Here only I am going to connect the component. So to get the component from this place to this place, click on this horizontal line or rung and click on this. So it will be coming. Okay. So for output, if you want, click on this, it will come here. So it is asking a question mark. That means I need to give the addressing. Okay. So I am going to give I 0.0. Fine. And here it is Q 0.0. Fine. So now I have connected one switch with one coil. So what will happen if I turn on? This fellow will need to on. Fine. So we are going to do the simulation. So go to schematic manager and open this simulation on off. If you want to see the output, you need to use this option. Click on this. It will take you to the simulation window. In this simulation window, you need to pick this option, run P. Fine. Now move on to your programming page. Click on download and this one, monitor. So once you click on the monitor, your run option will be blinking. Fine. And here can you see the green color? That means power is coming over here. and it is restricted by I0.0 because I0.0 I have not turned on yet. So how to turn on this in the simulation? By using the simulation window. So can you see here IB, QB, and it is having the 8 check-in boxes. That means it is indicating the first channel. IB0 means it is the 0th channel. Fine. So this one is the I0.0 and this is the Q0.0. For example, here I have used the address called I0.7. I should use this one. Since I have used I0.0, I am going to turn on this. Can you see here? If I turn on, automatically Q0.0 is on. Even you can see the output here. Whenever I0.0 is on, Q0.0 is on. Okay. If I turn off, it is going off. I hope you have understood this concept. Let's try with the normally closed switch also. So to go back to the edit mode, click on this monitor on off and click here, change that to normally closed switch. I'm going to delete this I0.0. Fine. And I'm going to do the same thing. Download monitor. When I click on the monitor, automatically output is on. I have not touched the I0.0, right? Can you see here? I0.0 is not on, but still Q0.0 is on. Why it is mean? Because it is a normally closed switch. It is allowing the power supply to enter. That means it is getting the closed loop whenever we are going for the run mode. See here, if I disturb the switch, if I am going to open the switch, automatically it is not getting the closed loop, so output is off. Fine. So this is how we are going to write a program in the Siemens Semantic Manager software, and lot more concepts are about to come. Wait for the next session, guys. Thank you so much. Bye. Hello everyone. So in today's session we are going to see about the programming concepts. In the previous session we have seen programming, introduction to programming language and introduction to the software. Now we are entering into the ladder logic programming. Fine. So we have seen what is normally open contact, what is normally closed contact and all, right? Just a minute. Yeah. So these are all the components of ladder logic that we have already discussed. What is rails, what is rungs and all. Fine. So now in this session, we are going to see about how normally open contact is working and how normally closed contact is working. How to connect normally open contact and closed contact with the coil. That means output device. Fine. So generally, come to normally open contact first. So it is like a normal switch in our home. Fine. So what normal switch in our home? If you turn on, your light or fan will be on. If you turn off, your light or fan will be off. The corresponding switch of light and the corresponding switch of fan you need to turn on a lamp or fan. Correct. So like that, normally open contact control is in your hand. That means unless or until you press, it will not give the supply. Okay. So I'll take a software help to explain this concept so that you can understand better. Fine. Okay. I'll start sharing the software. Yeah. So this is my software environment, right? So this is our normally open contact, correct? So I'm going to use this. I'm going to use only one. Fine. So whenever you are using this, it is asking question mark. So what address we need to put in Siemens? It is I0.0, correct? So you are putting I0.0. This is a normally open contact. Fine. So I'm connecting. You should not leave a rung without connecting output. It will be giving the error. For example, see, if I go for online, what it is telling, a coil or assign is required. Okay. So we need to connect some block or coil with the input. Fine. So to study this, normally open contact. I'm going to connect one more output here, one output here, and that address is Q0.0. Got it? So this is normally open contact. I'm connecting with the output. Fine. Shall we see the normally open contact, how it is working? So imagine a truth table for this. We are having one input and this is output. Fine. So if a input is 0, output is 0. Fine. If input is 1, output is also 1. Shall we see that? I'm going online. Yes. So this is online and I'm going to take the simulation box. This is the first channel 8-bit. Okay. So this is the address I have used, right? I0.0. So this is I0.0 and this is Q0.0 where I can see the output. See here, according to our truth table for normally open contact, input to 0, output to 0. Can you see? Input is 0, output is also 0. So now what is the second thing in truth table? Input is 1. What will be the output? Output is also 1. Correct. See, input is 1, output is also 1. Okay. So this is normally open contact. Unless or until you press, it will not give the output. That is normally open contact. See, if I turn off, it will off. Right? See? Like this. It will be working like this. Got it? Yeah. So now, imagine you are having two normally open contact. How you will be connecting? You will be checking whether to connect in nearby or parallel. So just now I'm for time being I'm just connecting in a series. I'm giving some other address. Fine. Let's go for online. So since both are normally open contact, it is 0, 0, 0. Fine. So if I turn on, up to this power is coming. So I0.1 is not turned on. No, that's what it is not giving output. If you turn on that, output will be on. Q0.0 is on. So like this only, you need to use the normally open contact. So unless or you can conclude that unless or until you disturb the switch, it will not give supply. What is the supply meaning here? Supply is coming up to this. Fine. It is not crossing this contact. Why? Since normally open contact is not pressed, it is not allowing the supply to entering. Suppose if I press this, imagine I am pressing this. See, once I pressed this, supply is crossed this place. Fine. Now again it is restricted by I0.1 because I0.1 is not pressed. Shall we press now? Yeah. After you have pressed, Q0.0 is on. Correct? Fine. So it is restricting the power supply until or unless it is pressed. Fine. After that it will be allowing. If you want to again, if you press, it will break. See here, if I again break that I0.1, I am breaking the I0.1. Now see here, again power is restricted up to this. If I turn off I0.0, again it is restricted. Fine. Yes. So this is normally open contact. Fine. Shall we see the normally closed contact, how it is working? So what is this normally closed contact? Normally closed contact. So it is just opposite to normally open contact. Fine. So if we thought about our truth table for normally closed contact, we are having one input and one output. So there, since I have mentioned it is opposite to normally open contact, what will be the first case of truth table? It is 0. Output is 1. When the input is 1, output is 0. Okay. So let me see that in a truth table. Now we are going to see about the normally closed contact. Fine. Yeah. Just a minute. Yes. So fine. So we have discussed this. So I'm deleting that. So where is our normally closed contact? Here it is. This one. Right? I'm choosing. You can choose from here, or in BitLogic also you can see here. This is also here. Okay. So anywhere you can choose. I'm choosing from here. You can choose from anywhere. Now this is also asking a question mark. I should give the address. I'm giving some address. Fine. So what I have told for the truth table, when this is input, this is output. Okay. When input is 0, output is 1. Second case, when input is 1, output is 0. Shall we run? Yeah. Yes, see here, I have not disturbed the switch. So I just went for run, correct? I have not pressed the switch. See here, in simulation box also it is not pressed. Correct? But your output is on. So it is 0, 1. Why I am mentioning the input as 0? Because I have not disturbed the state. Fine. So if I disturbed, you can tell that is 1. That means it is silently allowing the current to pass through, because the switch structure looks like already the switch is pressed. The switch initial condition is already pressed, kind of. So that it is allowing, see, it is allowing the power to flow in already. Fine. So if I press, what will happen? If you press, already pressed the switch, will open the switch, right? So that's what it is going to happen. See, I'm going to press I 0.0, which is making the power to restrict. I mean, the switch is restricting the power to flow. So output is not on. Can you see here? It is here up to this only power is flowing. Correct? So suppose, what if I switch off? Can you see? It is again allowing the power to get in. Fine. So this is normally closed contact. You can use two normally closed contact also. So same as normally open contact. I'm putting that in a series. I'm giving some other address. Okay. Let's go for online and check how it is working. Yes. So can you see here what is happening? I have not pressed both the switches. Output is on. Because both are normally closed contact. So both are allowing the power to flow. Got it? Shall we turn on this I 0.1? Okay, I'm turning on I 0.1. If I turn on I 0.1, immediately Q 0.0 is off. Why? Power is not flowing through this because the switch is opened. Okay. Again, if I turn on I 0.0, what will happen? Output is still in off condition because already this got broke. Now this is also broke. Fine. So how to turn on Q 0.0 again? I need to press again I 0.0 and I 0.1. See? Now the power is allowed to flow. Got it? Can you get the point? So this is normally closed contact. Fine. So in this session, what and all we have seen? We have studied about what is normally open and how it is working. This one we have seen, and normally closed contact we have seen. And output device is nothing but the one which is we are connected at the right hand side of the run. Okay, so without a coil you cannot able to test your normally open and normally closed contact. So output may be anything. We have seen about the digital and analogs, right? In outputs like motors, it may be a motor or control valve like that. So output coil should be anything. Fine. So yes, so this is the very basic 3 components we need to understand in the ladder logic. Fine. So in our next session we are going to see about the 3 main concepts in ladder logic. Okay. So yes, we'll meet you in the next session. Until then, bye. So in today's session, we are going to see about the programming concept part 2. Okay. So in the previous session, at the end of previous session, I have told we are going to see about the three main concept in ladder logic. Fine. So the first one we are having is turning on output using input. Fine. So it looks simple, right? So we need to turn on output using one input. Fine. So how we will be doing in a software? So I'll share the screen. Yes. So what we will be doing? Turning on an output using input. So first I need to turn on an input. By using that I will be turning on an output. So like this only, no? Fine. So I need to turn on an input, because of that output is on. So which switch you will be using? Obviously it will be normally open contact, correct? You need to turn on an input to turn on an output. Fine. So see here I am running. It is off. Whenever you are turning on, your output is on. Fine. Got it? So this is the first concept we need to know. Whenever output is connected with the input, by using any one of the switch or two switches you want to connect, you want to turn on your output, that should be directly connected without any disturbance. See here, there is no disturbance over here, correct? So that's what you have turned on the output using I0.0, any one of the input. Fine. So this is the first concept you need to understand. Fine. Shall we move on to the second concept? Okay. So what is the second concept we are having here? Turning off the same output using another input. So already we have turned on one output, correct? Now that output we need to turn off using another input. Why I am mentioning another input here? If by using same input means what you will be doing? By using same input means, if I have mentioned same input means you will be turning off this, correct? You will turn off this, automatically this fellow will off. But I have not mentioned this. By using I0.0 you are turned on. By using another switch you need to turn off. What you need to do? Yes. We need to use another switch to turn off. Okay? Okay. We get to know that we need to use another switch. Point number 2. That is point number 1. What is point number 2 means? The second switch I am going to use is normally open or normally closed. This is the very important decision you need to take. Correct? So whether I need to use normally open or normally closed contact. Right? So that's what the second concept is very, very important. Why means, if you want to turn off something, okay, that should be a normally closed contact. So always to break the circuit, we need to prefer normally closed contact. Fine. So how we are going to implement the normally closed contact? That is the point number 3. Okay, I have come to the conclusion I need to use normally closed contact. But how? What is this how? Where to connect? How that second switch is going to influence our output? That is a question mark, right? We are not knowing, no? So imagine you are connecting that in a parallel. This is your second switch. Fine. We have only two options, right? One in parallel or in a series or in a third rung or in a second rung. So in a second rung it is not possible. I cannot connect that in a second rung. Fine. So let's see this. I am connecting I0.1. First case I'll try this. Okay. So by using I0.1 I am going to turn off Q0.0. Let's see that. Yeah. So this will be the case. Correct. So I am doing it again. I am going online. But see, this I0.1 is turning on my Q0.0. Can you see? Power is flowing from this place to this place. So by connecting normally closed contact in a parallel is not having any influence to turn off. What is the purpose of implementing I0.1? To turn off my output, but that is not happening. Correct? It's not happening, no? So what it is happening? See, if I turn on, output is already in on condition, but still it is maintaining. If I off, nothing is happening. See, whenever I am turning off I0.1, it is not at all having any influence with the Q0.0. Correct? So this is not a right way to connect a normally closed contact to break the circuit. Right? Okay, I cannot connect like this. Then how can I? For example, you may have some other option also, like why can't I connect like this? This is your same output. This is your I0.1. Okay. This also wrong. Why means output coil should be in only one place. Okay. Input you can use it in multiple places. But output coil, output as a coil, if Q0.0 is used as a coil in one place, that should not repeated in any place. Okay. Output should be in only one place. Why I am telling like that means output will get confused now whether to follow this one or this one. Correct. Imagine I'll go for online. See what is happening. Output is on. Why? This is on. This is a normally closed contact. No, this is making the power to flow in. But it is confused whether to follow this. See here. If I turn on this, again, both are on. So this is not a right thing because it is toggling. Behind the screen, it is toggling off on like that. So we should not connect like this. Output should be in only one place. So this is also not a right thing. So this is the only option I am having. To break the circuit, always connect the switch like this. Where is your output? Here. Your output line is also here. So you need to connect a normally closed contact over here. Which line you want to break? There you need to put a normally closed contact. Okay. Shall we check now whether it is working or not? Yes. Shall we check? See, I am going online, right? Now see, output is off. Fine. What is our first condition? I need to turn on I0.0 to turn on Q0.0. It is happening? It is happening? Yes, it is happening. Why? Because I0.1 I have used as a normally closed contact. So it is allowing my power to flow inside. So that is not an issue. Got it? Yeah. So if I turn on I0.1, that is the second concept, right? It is making my output to go off. Why? Because it is breaking my circuit. Already we have known how I0.1 is working. I mean how normally closed contact is working. But we need to know how to connect. That is important. Fine. So you need to connect a normally closed contact like this so that it is turning off our output. Got it? So this is our second concept. Shall we see what is our third concept? Yes, we'll see. Turning on the same output using another input. So what is our third concept? Turning on the same output using another input. What? I need to use a third switch to turn on my Q0.0. As I have already told, you cannot connect in a next rung. Correct? So you need to use a switch within this rung itself. Right? Fine. So imagine you are having a scenario where you are facing a traffic while reaching your office or school or college. Okay? So in a particular place you are facing so much of traffic, you cannot be able to cross that place. So what you will be doing? Maybe you can find some shortcuts. You can take some left turn or right turn to find some other way to reach your office. Correct? The same concept. Where we are facing a traffic in this rung? Here. The line got broke here. Correct na? So I need to find a route parallel to this. Fine? So see here, if I find a parallel route here, what is the purpose of this switch? It is already breaking my circuit, no? So I need to find a way in this place. So I need to take a parallel route to reach my office. What is this parallel route address? The third switch. All three are different switches. That's what I am giving a different name. Don't confuse with that. Okay. All three are different switches. That's what I am to refer that this is the different. I am giving different address. Shall we go for online? See. First when I press, your Q0.0 is on. First concept. What is the second concept? To turn off Q0.0, I need to press second switch. It is turned off, right? Why it is turned off? The line got broke. Fine. Now, what is the third concept? By using switch 3, you need to turn on your output again. So, if you turn on, can you see the power is restricted here. So, but it is taking this path to reach Q0.0. Fine. So, yes. So, Q0.0 is on by using the third contact. Fine. So this is the three concepts you need to understand. First to make the contact, then to break the contact. Third one is again to make the contact. Fine. Yes. So yes, this is a three important concept we need to understand. I hope you have understood this. In our next session, we are going to see about the logic gates. Fine. So we have AND OR. And we have a logic gates, no? AND OR, XOR, XNOR, NAND, NOR, NOT. So, we are going to implement the ladder logic for those gates in the next session. Fine. So, we'll meet you all in the next session. Until then, bye. Hello everyone. So, in today's session, we are going to see about the logic gates. So, we are going to implement all our logic gates in the ladder logic. So, we are very well known about the logic gates and truth table, right? So, for OR and NAND, NOR, XOR and XNOR, we are having two inputs and one output. And only the NOT gate is having only one input and one output. Got it? So, we'll see that. So, yes. So, now we are going to implement that in a ladder logic. So first we will check out the OR gate truth table. So this is a truth table for OR that we are very well known to us, right? So we are going to write a ladder logic that satisfy all the four conditions. Okay. For example, I will be using two inputs and one output, and that logic should satisfy same logic. We should not change the logic for all the remaining gates. Remaining cases. There should be only one logic that satisfy all the cases. Okay. So we'll see that from the first case 0 0 0. So whenever you are not disturbing the input, output should not be happening. Okay. When you disturb the input, the second case 0 1. That time your output should be 1. So from this we get to know we need to use the normally open contact. Right? So I'll share the software. We'll see over there. Yes. So we need to use a normally open contact. Okay. And according to the second case 0 1, answer is 1. That means any one switch is on, output is on. Okay, so it is like an option to us. Any one is on, output need to on, like that. So when it is an option in ladder logic, you should have the word called parallel connection in your mind. Okay, that means you should connect normally open contact in parallel to get the OR logic gate. Fine, we'll see that I 0.0, this is I 0.0 and this is I 0.1. Right? So what is this means? If any one input is on, output is on. That is what the case is. Let's go for online and check. Yeah. So see, what is the first one? 0 0 0. Fine. So 0 0 0. Now I'm going to turn on 1 0. Only one input, output is on. See, the I 0.1 is in an off condition, but still output is in an on condition. Okay, this is OR gate when it comes to option. See, if it is 0, 1, I'm not turning on I 0.0, but I'm turning on I 0.1. Output is on. What is the last case? 1, 1. 1, 1. Output is also 1. Fine. So this is how we need to perform the OR gate. So OR gate means any one input is on, output need to on. It is like an option. So you can make use of normally open contact in a parallel connection. Fine. So this is OR gate. Correct? This is OR gate. Right? So shall we do the AND gate next? So what is AND gate? 0, 0, 0, 0, 1, 0, 1, 0, 0. What is the last case? 1, 1, 1. So from this we get to know both inputs need to turn on output. Okay, here it is not an option. Both need to be turned on. So in the previous session I have told about the series connection, right? So yes, in AND gate we need to connect both in a series. AND gate. Okay, so this is I'm giving I 0.0. This is I 0.1. This is Q 0.2, or I'm using 1. Right? So what will happen? 0, 0, 0, 0, 1, again it is 0. Right? And 1, 0, again it is 0. When it both are 1, that time only output will perform. Can you see here? This is AND gate logic. Okay? 0, 0, 0. I'm turning on 1, 0. See, 1, 0, still it is 0. Correct? Now I'll perform 0, 1. 0, 1, still it is 0. Right? If I'm turning on both, output is 1. Got it? So, AND condition means, AND gate means it should be connected in a series. It's not like a OR gate. OR gate means that is an option. Can you see here? In a OR gate, if any one input is on, OR gate is giving the output, but AND gate is not giving the output. Got it? So this is AND and OR gate. Fine. Shall we move on to the next gate? What is our next gate? NAND. Okay. So we'll see the truth table. Yeah. So see the truth table. First case is what? 0, 0, 1. So I'm not going to disturb the switch, but I want output need to on. So from this what we get to know? We need to use a normally closed contact. Fine. See the second case. 0, 1, 1. So any one output is on, any one input is on, output is remains on. So it is like an option, no? Option, correct? So option means what circuit we need to have it in our mind? That is, yes, parallel. Fine. Let's see the same NOR gate again. NOR gate, next gate. See here, 0, 1, it's still 0. So it is a AND condition. Fine. So NOR is optional. NAND is optional. NOR is condition. Okay. We'll see that in a software. So I'm going to take a third network. Yes. So we get to know we need to use a normally closed contact. And how we are going to use a normally closed contact? I have told option. So option means what? Parallel circuit like this. And I'm connecting one output over here 0.2. Right? Let's go for online and check. Yeah. Can you see the NAND gate? 0, 0, 1. Correct? Again 1, 0. It's still 1. Still 1. See? Still 1. Again 0, 1. Still Q 0.2 is in a on condition. If both are 1, Q 0.2 is off. Okay? If both conditions are 1, Q 0.2 is off. Okay, so we need to connect a normally closed contact in parallel since it is a NAND gate. Fine. Same thing can you see for AND and OR gate. This is the AND gate output. This is OR gate output. This is AND gate output. Correct. So those are on because both the switches are in a on condition. Fine. So this is NAND. So what will be for NOR? NOR is a condition. Correct. So what we need to connect? It is in a series. So normally closed contact in series. Like this. And I am connecting the different output, that is U0.3. So this is NOR. Fine. Yeah. Let's go for online and check. So yeah, already it was on. That's what it is giving. What is the truth table now? NOR 001. Correct. 001 is NOR. I am putting over here to see the output of all. See, this is NOR gate. NOR gate is giving output when both the switches are 0. Correct? Yeah. Suppose if I turn on one input, 1 0, output is off. Q0.3, this is the output of NOR. This one, or you see here. If you are getting confusion in this, see here. Q0.3 is off. Because I have given 1 0. Now 0 1. Still it is off. See? If both are on, still it is off. Because it is breaking the circuit. I have connected in a series which is breaking the circuit. So this is NOR gate. So NAND gate is optional with NC contacts. NOR gate is conditioned with the NC contacts. That is the difference. Okay, fine. So we have 3 more gates pending. Let's see that. What is our next gate? Yes, it is XR. Correct? XR. Fine. So let's see the XR gate logic gates. Truth table first. Yeah, this is our XR. So can you see here 0 0 0. Okay, 0 1 1. 1 0 1 1 1 0. Fine. So you may confuse like 0 0 0. So we should use a normally open contact. Okay. But see the last case 1 1 0. What is this 1 1 0 means? If you are using a normally closed open contact, it should give 1, no? Right? But it is 0. So from this truth table you get to know you need a combination of NC and NO contacts. Both contacts we need to use. Right? So let's see how to use that. For XR gate, 1 open contact, 1 closed contact, and in parallel 1 closed contact and 1 open contact. Okay. I am connecting on different output here. And this is I 0.0. This is I 0.2. 1. This is again I 0.0. This is I 0.1. So this is XR gate. So you are using only, don't confuse that we have used 4 switches. We have used only 2 switches only. What is the address of the switch? I 0.0 and I 0.1. But we are using the copy of this. Another switch with the same address. So practically we are using only 2 contacts, but logically we are using the another state of the switch. Okay. So this, by using this only we can achieve the concept of XR. See, now both are 0, output is off. That is XR gate, right? 0 0 0. 1 0, output is 1. 0 1, output is 1. If both are 1, output is 0. Can you get the point? So this is how we need to do the XR gate. Okay. So one need to be parallel contact in I 0.0 is a normally open contact in this, and I 0.0 is normally closed contact in this, right? So same, here it is closed contact, here it is open contact. You can exchange this rung also, no issues. You can put this in first and put this in second, that is also working, right? Yes. So what is the next gate? X NOR. X NOR is just opposite to this. Let's see the truth table. Yeah. So for X NOR is just opposite to XOR. X NOR. So 0 0 is 1, 0 1 is 0, 1 0 is again 0, 1 1 is 1. So first and last cases are having 1 and the remaining 2 are having 0. Fine. So this is opposite to XOR. So what I am doing, I am connecting like this to open contact in series and to closed contact in the parallel. Just a minute. Like this. So this is X NOR. So this should be I 0.0. Next is I 0.1 and up next is again I 0.0. This is I 0.1. Fine. So this will be your next output, which is Q 0.5. So what is the first case of X NOR? 0 0 1. Correct? Can you see? 0 0 1. No, I have turned on this. Yeah, now see here. 0 0 1. Fine. In the previous, when I was explaining XR, I was not turned off this. That's what? It was still in the on condition. So I have turned off now. So see here 0 0, but output is 1. Now 1 0, output is off. 0 1, output is remains off. Now both are 1, output is on. So this is the last case, this is the first case. For the remaining two cases, output will be in the off condition. Same thing for XRC. If both are on, output should be off. That is XR. If both are on, output should be on. That is X NOR. Fine. Right? So yes. So what is the pending? Only one gate is missing, right? What is that? NOT gate. So for NOT gate, there is only one input. Let's take I 0.0. So what is the truth table for NOT? When input is 0, output is 1. Correct? So obviously it should be a normally closed contact. So it should be like this. When input is 0, output is 1. That means you should connect a normally closed contact directly with output. Let's go for online and check. Yeah. See here. Okay. I have not turned off this previously. Now see. Okay. Just a minute. I see. I have given the wrong address here. It is Q 0.6. Yes, see. Whenever your input is off, output is giving 1. NOT gate. If you turn on that, output is off. So 0, 1, 1, 0. I have turned on I 0.0, but output is in a off condition. So this is NOT gate. Got it? So this is how we need to perform the logic gates. So this is R, where both any one is on, output is on. AND gate, both need to be on to turn on a output. NOR gate and NAND gate are just opposite to OR and AND. Okay. See here, any one is on, output is on. But see here, it is like a condition, right? So 0, 0, 0. That's what I have preferred normally closed contact. Here also 0, 0, 0. That's what I have preferred the normally closed contact. So this is XR. It is like similar means 0. That means what? 0, 0 should give 0. Okay. Right. Different value means it should give 1. Fine. So this is just opposite to XR. X NOR. So 0, 0. Again it should give 1. For 1, 1 also it should give 1. Remaining 2 cases it should be 0. NAND gate is, NOT gate is, input is off, output on, input on, output is off. It's like a opposite negate function, like negate function, right? So these are all the logic gates, and this is how we need to perform in the ladder logic, and the circuit is common for all the cases. Truth table is having 4 cases, no? 0, 0, 0, 1, 1, 0, 1, 1. So this circuit, whatever circuit we have seen here, no, for all the logic gate, it is common for all the 4 cases. Fine. So yes, so that's it. So we'll meet you all in the next session with another interesting examples. Fine. Yeah. Until then, bye. So in today's session, we are going to see about the example problem in ladder logic. Fine. So far we have seen some programming concepts and how to use contacts, right? So we are going to implement whatever we have learned by using the example. Fine. So let's read the first one. You are having a switch named SW1 and one lamp named L1 with you. Write a ladder logic program to turn on L1 when SW1 is on. Correct? So when you are turning on, that time only L1 need to on. So obviously what contact it is? Yes, it is normally open contact directly connected with output. Correct? So let's do that in a software. So yes, so like this it will be. Correct now? So you need to connect normally open contact directly with output. Let's go for online and check. If you turn on, output is on, right? So that's what they have asked us, right? When SW1 is on, lamp is on, correct? So yes, so this is the solution for the first problem, which is very easy, right? Easy for understanding also. You are having a switch named SW1. When it turns on, lamp 1 is on. That's what I have connected directly with output. Got it? Yeah. So second one. When SW1 is pressed, Q0 is pressed. Q0 is on. So when you are pressing the first switch, one output is on. When you are pressing the second switch, another output is on. When you are pressing the third switch, third output is on. So here we are having 3 inputs and 3 outputs. Correct? So each output is having corresponding input. Fine. So how to do it in a software? So we are having 3 switches and 3 outputs. Fine. So I'm going to take a 3 rung for this. So in the second rung, I'm connecting second switch, second output. And in the third rung, I'm connecting the third switch and third output. Here I'm going to give the address. This is first output, first input. So this is your second input. And this is your second output. I'm just giving the different address because all are different, correct? Yes. So Q 0.2. Fine. Got it? So let's go for online. Yeah. What is our question? Read. When Q1 need to turn on, first output need to turn on when you press the first switch. See, when I press the first switch, output is on. First output is on. When you press the second switch, second output is on. When you press the third switch, third output is on. That's it. Because why I have connected everything in the different rung? Because each input and output are not having any relation. Correct na? Each are different. That's what I have connected in a different rungs. There is no connection between the outputs and inputs. That's what I have preferred 3 rungs. Okay, fine. So yes, so whenever you are not finding any connection between the input and outputs, better prefer the different rung. Got it? Fine. So yes, let's go for the third question. Yeah. When SW1 is pressed, Q0 and Q1 are on. When SW2 is pressed, Q3 is on. So here we are having 2 inputs and 3 outputs. Correct? So one switch is common for 2 outputs. And this is common. No, this is we can do it in a different rung, SW2 with Q3. But here both the outputs are interlinked by using SW1. Right? So for this, how to do it in a software? So I'll delete the network 3. This is your switch 2 and this is your switch 3. I'll make switch 2. Okay, this is switch 1. When you are pressing that, 2 outputs need to on. So one output is this one. Another output means how we need to connect? We need to connect it in a parallel. Why? Because in our previous session we have seen do's and don'ts in ladder logic, right? So there we have discussed output should not be in the series like this. See, in this you cannot able to connect your coil. Fine. So one switch, 2 common output means that should be in the parallel. Fine. So when you are pressing the first switch, 2 outputs will be on. Let's see that. Yeah. Fine. When you are turning on the switch 1, first switch, both the outputs are on. When you are turning on the second one, third output is on. Fine. Got it? So yes. Right. So this is how we need to do the example. When you are having one switch and multiple outputs means that should be connected in parallel. Fine. Let's move on to the fourth example. When SW1 is pressed, Q0 is on. When SW2 is pressed, Q0 should off. So for turning on one switch, for turning off another switch. Got it? To turn on one switch, to turn off another switch. So what is the solution? Do you remember the concept we have seen? 3 concepts we have seen, right? In that second concept. So what we will be doing? I'll delete this. Yeah. To turn on means we will be connecting directly with the output. To turn off means we will be connecting that particular switch in normally closed contact like this. Fine. Let's go online. Yeah. When you turn on first switch, output is on. When you turn on the second switch, output is off. Fine. To break the circuit, we should use a normally closed contact. Got it? If you want to turn off output, we need to use a normally closed contact. Since here they have given the second switch to turn off the output, we need to put that in a normally closed contact. This is breaking the circuit. Okay? To break the circuit, we need to give like this. Got it? So this is the answer for the fourth example. Fine. So let's see the fifth one. Yeah. So when SW1 is pressed, Q0 should on. When SW2 is pressed, Q0 should off. When SW3 is pressed, Q0 is again on. This is nothing but our third concept. Fine. So we'll continue with the previous problem. By using this we are turning on. By using this we are turning off. By using the third switch we need to turn on. This one we have already seen, right? This one we need to connect it in a parallel. Where the line got broke, there we need to connect. I'm going online. Yes, see. Whenever you are turning on for the first time, output is on. Second switch is on, output is off. Third switch is on, again your output is on. Got it? Fine. So yes, this is how you need to turn on an output again. Because it is already turned off using I0.1. Again we are turning on, no? So we need to connect a parallel contact. Fine. So I hope you have understood all these 5 examples which are very basics one. It's not very tough. It is a very basics with some statements. You need to know how to implement that in a ladder logic. Fine. So yes, we'll meet you all in the next session. Fine. So until then, bye. Hello everyone. So in today's session we are going to see another 3 example on the basic ladder logic programming. Fine. So yes, let's move on to the session. So when SW1 or SW2 are pressed, Q0, Q1 should turn on. When SW3 is pressed, Q0 and Q1 should go off. Fine. So they have given 3 switches and 2 outputs. Fine. SW1, SW2 and SW3. 3 inputs. Q0 and Q1 are 2 outputs. Fine. So to turn on Q0 and Q1, they have given 2 inputs. Fine. So when SW1 or SW2, so they are giving the option, any one or both are pressed, both output need to turn on. So this is the R. R means option. Option means what is the one word you have it in your mind? Yes, it is parallel. Fine. So we need to connect these 2 switches in parallel to turn on this Q0 and Q2. Fine. Q0 and Q1. After that, when you press SW3, both need to go off. We need to break the circuit. Fine. Let's see how to do it in a software. So this is SW1 and SW2 I am connecting in a parallel. Why? Because they have given in a question like OR. Any one need to turn on. Like that they have given, no? So I am connecting like this. So any one is on, output is on. Correct? Fine. Shall we do that? Now see here. Any one. For example, I am turning on the first input. Output is on. Or if someone is turning on the second input, output is still on. If someone is turning on both, output is in a on condition only. So first condition is satisfied. What is the second condition they have given? By using the third switch, we need to turn off the output. So we know, right, how to break the circuit? Yes, we need to put a normally closed contact in series like this. Like this. Fine. This is I0.2. This is your switch 3. Got it? So I'm going online. So any one you are turning on, your output is on. If you are turning on your switch 3, output is off. Got it? So in the same question, if they have given AND, like SW1 and SW2, both need to turn on, means how you will be connecting? Then it will be like a condition. Condition means what? Normally open contact in series like this. Got it? Fine. So this is for AND case, that is for OR case. You cannot put the AND condition for OR case because this is like when both are on, that time only your output will be on. See, I am turning on one input but output is not on because I have connected in a series. So both need to turn on output. If the third switch is on, output is off. Fine. So yes, so like this only we need to do the first example. Let's see the second one. Yeah. So when SW1 is pressed, Q0 is on. When SW2 is pressed, Q1 is on and Q0 is off. Q0 was already turned on using SW1, correct? So what is the third case? When SW3 is pressed, Q0 is again on and Q1 is off. So they are having only 2 inputs and 3 outputs. Sorry, 3 inputs and 2 outputs. Fine. By turning on the first input, you are turning on Q0. By turning on the second input, you are turning off the already turned on output and new output. By pressing the third one, you are turning on the first output and turning off the second output. This is bit big, but it's not very tough. It's very easy only. Let's do one by one. So this is the first case, right? You are turning on I0.0 to turn on Q0.0. This is fine? Yes. So now you are going to use one more switch to turn on one more output. What is that output? This is your second switch and this is your second output. Correct na? Right? Yeah. By turning on the second input, you are going to turn off the first one. So it should be the normally closed contact. Got it? Like this. Like this, no? Got it? Fine? Yes? Yeah. So now, by pressing the third input, you are going to turn off the second output and turn on the first output. Correct? So to turn off means you will be connecting like this, no? Your third switch and connecting the parallel contact to turn it on again. That's it. This is very simple, no? We have seen the concept separately. Now everything is combinedly it is coming. Fine. So I'm turning on. Yeah. See here, when I press the first one, output is on. When I press the second one, output is off. Second output is on. If you turn on the third switch, second output is off, first output is on. That's it. Right? It is like combining all the 3 concepts here. That's it. Nothing big. Fine? Got it? So this is the answer for second example. Let's see the third one. Yeah. So here we are having 4 switches and 4 lamps. Correct? When SW1 is on, all 4 outputs are on. When SW2 is on, Q0 and Q3 are off. Okay, they are turning off 2 outputs. When SW3 is on, Q1 is again off. Q1 is off, Q3 is on. When SW4 is pressed, Q2 is off, Q1 is again on. So let Q0 is again on. Let's do one by one. First we will turn on all the outputs. Then by pressing this, we need to turn off last and first output. Let's do that. I'm deleting all. So 4 outputs you need to turn on by using one single input. How you will be connecting? You will be connecting the branches like this. This is for the first input, second input, and this is third input, and this is fourth output. Okay. So Q0.1, Q0.2, Q0.3. Fine. Yes. So by pressing I0.0, everything we have turned on. Correct. Now, by pressing the second switch, first output and last output need to off. So to turn off, we will be connecting a normally closed contact like this. Yes. Fine. Correct na? Like this. What is this next statement? Shall we read that? When SW3 is pressed, Q1 is off, Q3 is again on. Q1 is off, Q3 is again on. Q1 off means you will be connecting like this. Q1 is again on means you will be connecting the parallel contact like this. Fine. Yeah. What is the fourth one means? When the fourth switch is pressed, Q2 is off, Q1 is again on. So you will be connecting like this. And here it is a parallel contact. Right? We'll go online and check. So I'm turning on the first input. All outputs are on. When you turn on the second input, first and last output are off. When you turn on the third input, your second input is off. Your second output is off. Last output is again on. When you turn on the fourth input, your third output is off and first output is again on. Correct? So like this only we need to break and make the circuit. Make the circuit, connect directly. Break the circuit, put a normally closed contact. Again you want to turn on means get a parallel contact where the line got broke. For example, see here the line got broke for Q0.3. So here I took the parallel contact to reach the Q0.3 again. Got it? Fine. So yes, so this is how we need to perform the example problem in ladder logic. So it's like breaking and making and breaking the contact. Fine. So yes, that's it about the example problems in ladder logic. Basic programming concepts. Fine. So in our next session, we are going to see about one important concept. Let we discuss over there. Fine. So until then, bye. Hello everyone. So in today's session, we are going to see about one important concept in ladder logic. Fine. Let's see what is the topic name. Fine. So before that, I'll explain one situation and let's learn the topic from that. Okay. Fine. So far we were using a switch, like turning on a switch using I0.0 and we are turning on one output, name it as Q0.0. Fine. So what it will be actually doing, even if you are turning on, it will be on. If you turn off, it will be off. Right? That's what the switch is, right? Whatever we are having in our home, if you turn on a fan switch, it will on. If you turn off the switch, your fan will be off. Correct? This is the switch case. Imagine you are having a push button. Okay? Imagine I0.0 is the push button. So you are pushing the button. So your output is on. If you release that, your output is off. Correct? So we may have a push button in our home for turning on a motor. If you push that, it will make a contact. If you release that, your motor will remain in an on condition. Correct? So push button is like, we cannot make the push button to press continuously, right? Anyhow, we need to remove our finger from that so that the motor should continuously on. Okay, we need to find out what is behind that screen. How that even though we break the contact by releasing our hand, how come it is making the output to remain on? Correct? So whatever we are having here is the switch. See here, if you turn on, it will be on. If you turn off, it is off. Correct? But how to turn on a Q0.0 continuously? Even though if you turn off I0.0, how to make Q0.0 to turn on continuously. Right? That is very important. Fine. So what we can do? That we need to check it out. For example, by using switches you want to turn on and turn off a motor. Means imagine this is a motor. Okay. What we will be doing? We are using one switch to turn on and another switch to turn off. Like this. Correct. We will be using one more switch here. So it will be like start switch and stop switch. Correct. See, by using one switch you are turning on, by using another switch you are turning off. Fine. But how to make a input continuously on even if you turn off this? See, your I0.0 is off, your Q0.0 is off. But I don't want such situation. I want to turn on Q0.0 continuously. It should be in the on condition continuously. So, in that case, what is the solution? What we can do for this? That is the concept we are going to see, and the concept name is called as latching. Okay, imagine your I0.0 is a push button. Even though if you turn off this, how to make this output continuously on? Okay, how we are going to make means we are going to introduce a parallel contact parallel to your input like this. Okay, fine. So this contact I am going to name it as your output contact. Output address I am making. So by connecting a parallel contact of your output will make the output to continuously on. Let's have a look. Shall we check that? Yeah. Imagine I0.0 is a push button. You are turning on. You are removing your hand. You are removing your finger, but still your output is in a on condition. Right? So this is latching. By connecting a parallel contact of your output in parallel with your input. Because here your input is getting off, but still you can get supply from this place. So this is latching or seal in contact. This is also called as seal in contact. Fine. So this is called as latching. So by connecting a parallel contact we can make use of this. So you may ask me how it is on. How this Q0.0 is getting, see here, now in the initial condition this is not on, correct now? Your Q0.0 is not in on condition. Why? Because this is not on, right? That's what, this is also in off condition. So when you press this is on, because of the address, this is also on. So now the current is flowing through this passage also and this passage also, right? So if you turn off this, current cannot take this route, but current can take this route. Power is taking this route to reach from left rail to right rail. Got it? So like this only we are doing the latching. So this is seal in contact or latching. So even though if you are turning off the input, your output still is on. This is called as latching. You can take this as a push button also. I0.0 is a push button. So this is how in our home or in a metro station and all we are having a push button for operation, right? Even though you are removing your finger, it remains on, no? So this is the concept behind that. So they have done the latching of your output coil with input. That's what, even though if you remove your input contact, it still is on. Fine. So this is called as latching. Fine. So now you may have another confusion. So yes, I have turned on. So how to turn off this? Somewhere, in some place I need to turn off my motor, right? Q0.0 we need to turn off in some place. Correct? So how to turn off? obviously with I0.0 we cannot turn off, correct? So we need to use one stop push button for that, right? So stop push button means that also is a push button. You need to put over here like this. So this circuit is called as unlatching. Okay, so this is latching and this is unlatching. So for unlatching there is no need for parallel contact, right? Because anyhow it is going to turn off. So no need for parallel contact. See here, I'm going to turn on and turn off. Still output is in on condition. When you want to turn off the output, press I0.0, it will off. Okay, even if you release that, it's still in a off condition because this line got broke, no? So power is not having any route to flow, any route to reach the output, so it is off. So this is latching and unlatching concept, which is very, very important in ladder logic. So I'm repeating, I0.0 is on, output is on. Even if you release that, output still in a on condition. Fine. So even if you turn on your unlatching, I mean I0.1, it is unlatched the circuit, right? So this is making contact and breaking contact using push button. Fine. So push button is one of the important digital input. So in industries, people will be using push button more comparing to switches, because push button is having more advantages than switches. It is easy for operation and even corrosion will not happen. In normal toggle switches and all, corrosion will be happening, right? But in push buttons and all, it is very useful to operate and it's very easy. Flexibility will be there and corrosion will not happen in that. So that's what push buttons are preferably used more in industries. So obviously all the digital inputs will be, at most it will be push buttons. Fine. So yes, so like this only we need to use the push buttons in the ladder logic. Fine. So we can also use this concept in memories by using memories, that we will be using in the next chapter. In next chapter I will be explaining the memories, and there also we can make use of this latching and unlatching concept. Fine. Because imagine you are having a start and stop push button in your project. Okay. So what is the purpose of start button in a project? Until or unless I press that, nothing should start. Correct na? So you should include that start push button in all the rungs. Your project may have 100 rungs. In all the rungs you should include the start push button. Same thing, stop push button or emergency stop. That should be included in all the rungs to stop the process immediately. Right, some in emergency cases, if you press the stop push button, everything should stop. Correct. So start and stop push button, we need to place it in all the rungs. Correct. So in that case, latching is also very important, that I will be explaining in the upcoming chapters. Fine. So I hope you have understood the latching and unlatching concept. We'll meet you all in the next session with another interesting concept. Fine. So until then, bye. Hello everyone. In today's session, we are going to see about memory concept. So in the initial session, I have told about memories. So bit memories we are having, and same thing we are having for the register also. So generally, what is this memory? Let's see that bitwise memory and register are used to hold or store the status of IOs. Fine. So it will be the temporary memory used to store or hold the status of IOs, and we cannot allow to use it physically. Okay, unlike input and outputs, we cannot use it in a physically, because for example, if I'm using I0.0 in my program, that means physically I'm connecting any one of the digital input with I0.0. Fine. So for example, take a bitwise memory M0.0. If I'm using M0.0 in my ladder logic, it is not that I'm using any digital output or input for that physically. Okay, so it will be, address is used as logically to store the status of inputs and outputs. That may be a digital or that may be the analog. Fine. So it is within PLC. Within the programming, we are using some memories to store the status. Understood? So you should be very clear that if you are using memories in your ladder logic, it is not available physically and we cannot allow to use it physically. Fine? Yeah. So how the address will be means, it will be M0.0, M0.1 up to M0.7 will be there in first channel. It's same as input and outputs. Fine. For example, if it is a bit wise, you will be using zeros or ones, right? So you should be using M0.0 for one bit. Another bit if you are in need means it will be M0.1 or up to anything you can use, make use of it. Okay. If it is an analog, it should be an integer, real, word or double word. If it is an integer, you will be using MW0. Integer means it will be taking a 16 bit. So it will be MW0. That means it is taking 2 channels. One channel is having 8 bit. So 2 channel it will take. Right? If it is a double integer, it will be taking 32 bit. Same for real. So it will be taking 4 channel. That time we will be using MD0. So it is taking first 4 channel to store the double integer or real or double word. Got it? So where we are going to use the memory concept? I just want to give you one example, that is where inputs are having multiple states. Fine. Just see the tabular column. We are having one switch and one lamp. Fine. So whenever you are pressing the switch for the first time, output is on. Whenever you are turning off, output should go not off, but it should remain on. In the third step, you are turning on an output that will make your lamp to go off. It is a sequence. This is one. This is first one, second step, third step. It is a sequence. Okay, just add 1, 2, 3. It is a sequence. First step need to done. Second step next. Third step next. So it is a sequence. So here can you see this input is having multiple states. One is there. Again it is going off. Again it is going on. So for the multiple states of input, we are having only one lamp. Fine. So how to do this? I think you can do it up to this. Because this is nothing but a latching concept, right? See here. Whenever your input is on, output is on. Even though your input is off, output remain on. This is nothing but a latching concept. Correct. Up to this you can do. Up to latching concept. Fine. But after that also when the input is on, output should go off. It is like we are in need of an extra contact to turn off the lamp. Correct. But I am having only one contact. No. Where I can get the extra contact? And that contact, that extra contact can be given by the memories. Got it? So first I'll explain up to this what we can do. Why can't we use with whatever we are having? Why can't we do the problem for this question using lamp, only lamp and switch? Let me explain in the software. Yeah. So let it be I 0.0 is a switch and I am going to turn on the lamp. Fine. So first case is what? Whenever the switch is on, output is on. Okay. What is the second sequence? When the input is off, output should remain on. See here. If I am not doing the latching, what will happen? Input is on, output is on. First is done. Second case is what? Input should off, output should remain on. But here, output is also going off. So I need to go for the second step, right? So how to make the output remain on? That's what the latching concept will come. So what I can do? I can latch here. What I need to latch? What I want to remain on. This one, no. Right? Now go for online. Yeah. So according to the tabular column, I am turning on. Output is on. I am turning off. Output remains on. So first two steps are done. How about the third step? What is the third step? If I am turning on the input, output should go off. Let me do it. See, output remains on. Correct. So I cannot do the logic I have given in the tabular column with one input and one output. So I need to turn off Q0.0 with one normally closed contact here, because we have seen no basics of ladder logic when we have discussed the three concepts in the previous session. We need to use normally closed switch here to break the circuit. Then only this fellow will go off. Correct. So I am in need of one extra contact. So in this case, memories will help us. Can you understand the purpose of memory here? Right? So that's what we are in need of memories. Fine? Right. Okay, I'm using one memory here. Let it be like this. You cannot use a memory stately here. Why? See, why it is means it is not having any influence. Where you will be turning off. See, it is up to the second step, okay? So third step you are turning on, but it is not at all happening. So we should connect I0.0 with M0.0. Then we need to use this normally closed contact. Okay, so since we are in need of one extra contact, we cannot connect like this as it is. So I should be giving some proper connection between I0.0 and M0.0. Got it? You may ask me, why can't I turn off M0.0 to turn off this? Correct. You may have a bit memory here. See, this is bit memory. Okay. See here. So if I turn off, if I am turning on, this fellow will go open. That will make our Q0.0 to go off. I will show you. See, whenever I am turning on, this is going open, this is off. Even you can see in the ladder log, that is also off. But this is not my concept, right? Whenever I am turning on my input for the second time, that time only Q0.0 will go off. Correct? So that's what we cannot able to use this. I should not use this, but I want output using memory. How to do that? There is the logic. So let's see the logic. So what I need to do means, you save all your steps. For example, you are having 3 steps, no? In the tabular column, you are having 3 steps. Save all the 3 steps in the memories. Fine. How to save that? Just use one coil and just give the address as M0.0. Fine. So what you are doing here? You are turning on I0.0 and you are saving that in M0.0. Got it? So what will be the next rung? In the next rung, you are turning off I0.0. That time you are saving in another memory. Fine. Next, you are again turning on, no? That also you are saving in another memory. like this. So don't confuse that why I have used I0.0 in a normally closed contact. Okay, that means I0.0 is going off. Okay, that's what I have used here like this. So this is on, this is off. Okay, so I have used all the three memories. So in the fourth rung, what I am going to do means, see, in which step your output is going on for the first time? For which memory it is going on for the first time? It will be when you are turning on for the first time. So what I am doing, I am connecting that M0.0 with Q0.0. This is my output now, like this. Fine. For M0.1 also it remains on. So it is already in on condition. So I am connecting that in parallel. I should not connect this M0.1 in series, because after you turn off only output will be turned on. Like that it will happen. So it should, both are having same, like this is on here also, this should on in this place also. So I am making use of OR gate here. Fine. When it is going off, when M0.2 happen. Correct. So I am doing like this. Let me run. Let's see whether the logic I have done is right or wrong. See what is happening here. I have not done anything. Oh, this fellow is on. Okay, I'm just turning on and do it again. In the previous case, we have turned on this I0.0, right? I have not turned off here. That's what it was in on condition. So I'm going for download. I'm going for monitor. See here. This fellow is off, but it is on. Why it is on? Because I have connected a normally closed contact with the coil. So what will happen normally closed contact with the coil? It's like a NOT gate, right? NOT gate, 0 means 1. That is what it is happening. So do you think this is right? Obviously no, right? According to my tabular column example, after I press only this should happen. But here, initially it is happening. If I turn on, it is remaining on. If I turn off, it is remaining on. So it is not having any influence. So this program is, the logic is wrong. Correct? Why it is wrong? Because of mainly this rung, this second rung. The second rung is having normally closed contact. Because of that, it is initially on. And that is making the next steps to not to follow the logic. Correct? So this is wrong. So from this what we get to know? We should not connect normally closed contact directly with the coil. It should be with some normally open contact, because the control should be in our hand. Correct? Understood? So what I can do? I can make use of latching concept and sequence. Okay, so the importance of sequence and ladder logic programming is it should follow one by one. After this step only, this should happen. After second step only, third step should happen. Like that, you are making the connection between the rungs. That is very, very important in ladder logics. Okay, so how to give the sequence? For example, this is our first step. After this only, this should happen. So what I can do? I can get a reference, like first is done, it is giving a signal to the second rung. How can it give the signal? I can make use of normally open contact of M0.0. So what is symbolically it is telling? I am done, you can start. Same thing. M0.1 is done means it is telling a signal, hey, I am done, you can start. Right? So this is sequence 1 by 1. Fine? Let me run now. Let's see now how the logic is working. See now, our initial problem was resolved, right? It is solved. See here, it was previously on, no? Because of this. Now I have connected one thing, normally open contact of the sequence M0.0, so it is not on. So one problem is resolved. Now I am turning on. Yeah, it is happening. Even if I turn off, output is off, my second step is not coming. Why? Because this fellow is going off, no? That's what it is going, it's not coming. This output is going off. So here also we are in need of latching. So what is storing? I have introduced the memory concept as storing, correct na? So you should store means even though this I0.0 going off, this fellow should store when it was on. What was the status? Correct. So that case I need to do the latching here. M0.0 like this. Okay. So why we are using memories? To store the status of the input. So when the input is on, that time it is storing the status. Okay. Even though it is going off, it remains same, because when it was on, no, that time it was stored. So it is returning that. Okay. Same for here also. When it is going off, I'm storing here and that I'm going to retain. So I need to use a latching across which input I want to store. That is important, right? Because the input is having multiple states here. Correct na? So when it was off, that time I'm storing and I'm returning using this. Here also. When it is on for the second time, I want to store that in M0.2. That is also I am storing. Fine. Now the last time I have explained again, but still I am repeating. M0.0 I am connecting initially because I'll do it again. Okay. When my input is going on, output is on. So I am connecting directly. Even though my input is going off, output remains on. So there is no need of connecting this M0.0 anywhere. Even though if you want to connect, that should be parallel. This is actually having no influence, but still if you want to include all your memories in the output rung, if you want, because it is not having any influence, but still since you have used this, you are using. You may ask me, since it is not having any influence, why you are using this step? You can directly go to this step, no, like that. But without finishing second step, how can I go to the third step? My sequence is missing, no. That's what I am using this here. Okay, I have told you there is no need to use this place, but it should be there. It's mandatory. There are 3 steps, 1, 2, 3. 1 should go get over, after the 2, after the 3. So sequence is very important. That's how I have used AM0.1 here. Okay. See, I have used here. No, this is the important. After doing the second step, third step is happening like that. Correct. So now when it is going off, when I'm pressing the input for the second time, when I'm turning on, that case I'm going to break the circuit. That will be this. Fine. Got it? Let me check. Yeah. Got it? Whenever I'm turning on, output is on. If I turn off, output remains on. I'm turning on for the second time, output goes off, but still it is on. I think we have done some mistake. Let me check what is that. See here. Yeah, I have used the wrong address. See, this is the issue. So what address we need to use? It should be I 0.0. Yeah. Fine. So let's do from the beginning. Oh, memories. Okay, there is one issue here. See, whenever for the first time I have run, this fellow was on, right? So still it is on because we need to clear the memory. We need to clear the memory. So for clearing, you can reset here like this. For example, go here, reset this. Okay, or you can use one separate normally closed switch or stop push button we will be using. No, stop switch you can use. This is because of we need to reset the memory, because memories we are not doing the reset, right? That's what the issue was. Okay, if you are resetting the memory, output will go off. So before going for the download and monitor, you should reset the memory. You can reset here, or you can use one normally closed switch as a stop button, so that it will automatically erase all the memories. Got it? So let's see. I'm turning on, it's for the first time. My output is on. It's going off. Output remains on. When I'm turning on for the second time, output goes off. Got it? See, I have used all the 3 memories now, so it is turned on. Fine. Got it? So like this only we need to use memories. Okay. In some cases, memories are used to reduce the size of the program. How means? For example, you are having a start and stop push button. In a previous classes we have seen, no? Okay, so what is the purpose of start and stop push button? Means after pressing the start only, all the operations in your program should go on. If you are pressing stop push button, immediately all the process should go off. So imagine you are having a project with 100 rungs. In all the 100 rungs, we need to include this start and stop push button. Correct? So it is having 2 contact. One is for input start push button, another one is for stop push button. Okay, so how come we can include this start and stop push button in all the 100 rungs? And obviously, since it is a push button, you need to make use of latching also. Correct? So what I can do means, instead of that, what I can do means, I can make use of the memories to store the start and stop push button keys. Okay, and this memory I can make use of in all the remaining rings. I can start with only this M0.0 with some process. You may have some other process. I'll explain that also. See, this is one process you are doing. For example, I'm just connecting, okay? For here also I'm connecting some other process. And for this I'm connecting one input, which is I0.2. And here also I'm having one input, which is I0.1. Okay, imagine this is my program. Fine. So I'm going for online. Memories are not reset. I'll just stop the PLC and I'm going to reset this. Got it? Yeah, I'm going for online. Right? So now this is my program. So I want to start Q0.0 and Q0.1. So I'm turning on the respective input I0.1. See, I0.1 I have used for stop push button. So I'm going to use some other input. Right? Go for online. Yeah. So I'm turning on I0.3, but both the outputs are not turned on. What is our output here? Q0.0 and Q0.1. So whenever you are pressing start push button, then only it will on. What is start push button? This one. See, both are on. Even though if you are pressing this, the next input is on. So all the process are happening. Immediately some emergency case you are pressing stop. See, all the outputs are off. Right? So instead of using these two contacts in all the memories with all the rungs with the latching, you are using memories. Only memories you are using. So like that, memories are used to reduce the size of the program also. Fine. So that's the concept of memories. Let me, we'll see the next topic in next session. Fine. Until then, see you. Bye. Hello everyone. In today's session, we are going to start the instructions in Siemens PLC. So far we have seen this normally. Can you see this bit logic over here? So in this, we are going to study instructions one by one. Fine. So this is normally open contact. If you want to know the name, once you are clicking, just see here, it will show the name of the particular instruction. Fine. Can you see here? Normally closed contact. This is normally open contact. This one is invert power flow. Fine. This is our normal coil. This is midline output. Fine. Let's see about the instruction. So normally open contact, normally closed one, and coil we have seen already. Right. For the previous examples and concepts, we have used these three. Fine. So let's move on to the invert power flow. What this instruction will be doing. So to get the instruction to our network, click on the network and just click on this. It will come. Okay. So what invert power flow will do? We'll see that. So for that, I'm taking one input and one output. Okay. So for this, I'm going to give fine. And this is for this particular invert power flow, there is no need of address, because if address is needed for this instruction, it will give you the question mark here. Red question mark will be there. From that, you get to know we need to give the address for that. But for this particular instruction, invert power flow, it will not ask for the address. So what this instruction will do means, for example, invert power flow, that means if power is coming, it will not allow. If power is not coming, it will be allowing the power inside. Like 1 means 0, 0 means 1. It's just a NOT gate. Fine. For example, for this particular example, if I am not pressing I 0.0, what will happen? Let's see that. Can you see? Can you see the output here? Your Q 0.0 is on. How it is on? I'll just expand this. Yeah. So can you see here? I'll just keep this. QB is output, right? So output is on. Because power is not coming, so it is 0 here. It is inverting that. 0 inversion means it will be 1. Alright? So 1 means power flow. Okay. So if you want to turn on a output without switching on your I 0.0 means you can make use of this invert power flow instruction. Okay. Let me turn on this I 0.0. I am turning on I 0.0. So when I am turning on, what will happen? It will give 1 here. So after the inversion function, 1 is converted to 0 here. See, Oh, this is no. Yeah. So 1 is here, 0. So Q0.0 is off now. Fine. Got it? So this is invert power flow instruction. You can go with some other example. I'll take one more instruction here. I mean one more contact here. Coil. Fine. See here, I'm taking just Q0.1 here. So Q0.1 is connected directly with the I0.0. Got it? So what I have done here, this is connected with the Q0.0. Let me check the output now. See, only Q0.0 is on, Q0.1 is in off, because I have connected that directly with I0.0. Let's see, if I turn on, this will on, this will go off. Got it? Fine. So this is how the instruction will be working. Let's check now. I am connecting 2 NOT here. Let's see what will happen. See, so it is double NOT. 0 is here, that is converted to 1 here. Again 1 is coming here. Here also I have repeated the instruction, which is making 1 to 0. Fine. If I turn on this, then only it will on. Both will be on, because 1 is converted to 0. Here 0 is converted to 1. Got it? So like this also you can connect the instruction in series. So this is invert power flow instruction. Correct? So according to your application need, you can make use of the instruction in your ladder logic program. This is one of the instruction in Siemens Schematic Manager. Fine. Let's move on to the next instruction. So I'm going to delete this. Right. Let's take only one input and 2 outputs. Fine. What is our next instruction? This is coil. We have discussed already. Coil is nothing but output. This one. These 3 are already here. Normally open, normally closed, and coil. Fine. So now we have discussed not. Now the next one is midline output. Right? The instruction name is midline output. You can see here. What is midline output? The name itself is telling no midline output. I can, as we have discussed about the rules, do's and don'ts in ladder logic, we have seen output should not be in the series. Correct? I cannot connect another output here. Can you see? I want to connect one output here, but this function is disabled because this is one of the don'ts in ladder logic. But I want to connect. What I can do? I can make use of this midline output. Can you see the midline output structure? It is also looks like a coil. Correct? With a hash symbol inside. Just click on that. Can you see? What is this? What is this? It is midline output. Question mark is there. Undefined. So I need to give address to this coil. Right? So I'll just change the address of this one. I'm going to give address as the next of Q0.0. It is Q0.1. Got it? So what will happen? When I0.0 is pressed, these two will on and also this is also on. This is option only. I'm just deleting this. Fine. Let's see. I'm going for online. See, both are off. If I turn on, both will be on. So, I am connecting 2 outputs in a series with the use of midline output. Got it? So, you may ask me, why there is a need? If you want, you can connect like this also, no? For example, If you want to have two outputs for the same input, you can connect like this also. This is also right now. I can connect here also. Correct? Both are same. Instead of this, I can connect like this. Both are same. But you just see, this is taking one branch. Correct? But by using that midline output, I am finishing my program in single rung. It is reducing my program size. See, this is a simple example. So it's just a one rung, one network. But if you are having more rungs, in that time, if you are using the branches continuously, it will be taking more space. Obviously, scan time will get affected. So by using midline output, you can reduce the scan timing. Correct? Moreover, the length of your program. Obviously, scan time depends upon length of the program. Length means number of rungs we are using, or here in Siemens, it is network. Got it? So here we are having one more option. What is that? You can connect one more input in between. So what is symbolically it is telling means, when I 0.0 is pressed, this will on. Okay? This will not on now. Why? Because another contact we need to turn on. Then only this fellow will be on. Okay? Let's check that. See, I'm pressing I 0.0. Only Q 0.1 is on. Q 0.0 will not on because this contact is open here. If you turn on that, it will be on. Okay. So if you turn off I 0.1, only this fellow will be on. This will remains on. This will go off. This will remains on. Why? Because it is getting signal from I 0.0. If you do this, then that will also go off. Got it? So like this, you can make use of midline output. Right? Yeah. So this is midline output instruction. What we are having next? A reset, set. Fine. So what is generally set function? What it will do? What is the purpose of set means? It's somehow related to latching. Okay. So for latching, what we have done? We will be connecting one parallel contact of the output which we want to maintain remains on. Correct? So instead of taking that parallel contact, you can make use of the set coil to make that output remains on. So set is a inbuilt function which will be doing the latching operation. So what we will do for latching? Okay, I'll do one thing. I'll do the program. So what you will be doing the latching? You will be doing like this, correct? You will be connecting. So if even though I 0.0 is going off, this fellow needs to remain on. So you are using latching. So for unlatching, what you will do? You will be using one more input to unlatch it. So this is latching. This is unlatching. Correct? So what I'm going to do with the set instruction means, let's take one more input, that is I 0.2. So whenever I 0.2 is pressed, I'm taking set coil. Okay, set is the output coil. It's not will be coming under the input. It will be looks like this. And it is having a question mark. Obviously, you need to give the address. What address I'm going to give means I'm going to give Q 0.1. Okay. So if I turn on, Q 0.1 will on. If I turn off, Q 0.1 will remains on. So this function is inbuilt here. Okay, let me check. Yeah, see, I'll do the first network first. When I 0.0 is pressed, Q 0.0 is on. When I 0.1 1 is, when I 0.0 is turned off, output is remains on. Can you see here? Output is remains on. So when you unlatch it, it will go off. Correct? So whenever I am turning on, it is latched. Same thing. I'll do this. I'll do the second network also now. See, whenever I am turning on I 0.2, this output is on. So I am going to turn off the network 1. Output remains on. When I am going to turn off the second network I 0.2, still it is on. Can you see here? This green color, this is on. This green color, no, this is on. So this is the inbuilt function. How to turn off this? How to turn off the set function? Here I have used I 0.1. So it will go off. But for this, what we can do? So for that, let's check with this I 0.1 here. Because anyhow it is to turn off, no? We'll do I 0.1. I'm going online. Let's see now. Whenever this is pressed, both the outputs are on. If I turn off, both the outputs are remains on. Now I am going to press I 0.1, which will unlatch the circuit because I have connected both in the normally closed contact with the output coil, correct? I'll press. Can you see Q 0.0 is off by using I 0.1 because it is unlatching. But can you see here it is open here but set is remains on. Correct? So this is the difference between the network 1 and network 2. First set is similar. Latching part is similar. But unlatching part is different in set function. What is that unlatching function? For that only we need to use one separate coil to unlatch it. And that coil is known as reset. Okay? So reset, what you can do, I'm taking one more network and here I'm connecting this I 0.1 as a normally open switch with the reset coil. So now reset is also having a question mark. What I need to give? Which output you want to do the reset? You want to turn off this Q 0.1 only, no? So you should use that address. Got it? Got it? So this is for unlatching. So set is like latching, reset is like unlatching. So in your program, if you are using a set function, you should use reset function also. Got it? And obviously you should use the set function first. Then only you need to do the reset function. Let me check now. Yeah. I'll do the reset first. Yeah. See here. Why I have done the reset first means in the previously when I go for the online, this I 0.1 was on, right? So set was on. So I didn't reset this. That's what I have done. So that's not an issue now. So let's turn on I 0.1. Q 0.0 is on. If you turn off, Q 0.0 remains on. Now come to the set function. When I 0.2 is on, Q 0.1 is on. If you turn off, it remains on. Now I'm going to do the unlatching or reset. If you press this, can you see? If you press I 0.1, both the outputs will go off. That's it. Okay. So this is how you need to do the reset function. Set, reset. Got it? So it is similar to latching and unlatching concept. Only thing is latching is same, unlatching is different. For unlatching you should use the reset function. Got it? So we'll meet you all in the next session. Until then, bye. Hello everyone. In this session we are going to see about the remaining bit logic instruction. Fine, let's move on to the session. So today we are going to see first one is SR flip flop, right? Set, reset, flip flop. So in Siemens it looks like a block. Fine. So how to choose this means click on the rung and click on block. So it will be coming over here. So see here it is asking a address to give. It is asking a address to give and this question mark is meant to that. So what I'm doing, I'm just giving a memory address for this. Okay. So here, so for set I have given one input. I'm just deleting this. So usually when you're taking a block, it will be looks like this. You should give the memory address for the block. Okay. For block, it needs some address. And apart from that, it is having two inputs and one output. Right. So one input is for set, another input is for reset. So both should be a bool type input. So click on this place and click a normally open button. Contact. So for this you just give I 0.0. So for reset is another input. You need to give another input. So I'm giving I 0.1. Got it? So now Q is the output. So output also I need to give. So I'm just taking one coil and I'm giving the name as Q 0.0. Got it? So what SR flip-flop will do? Okay. So in the previous session we have seen set and reset function. Set means once the input is on, set will be on. Even though the input goes off, output will be remains on. Whenever you press the reset, output will go off. It is going to do the same function, but there is one priority will be there. Okay. So when set function is on, in the meantime, if you are pressing reset, what will happen? That's what SR and RS flip-flop is going to do. Let's do a simulation for this. So what I'm doing, I'm just going to do the set function. First I'm turning on I 0.0. See here, I 0.0 I have given to set. So I'm turning on I 0.0. Input is on. So output Q 0.0. Can you see Q 0.0 here? That is also on. Fine. So if I turn off, what will do? Since it is a set function, output will remains on. Got it? So it is similar, no? It is similar to the set function. When I press the reset, output will go off. Correct? This is same as set and reset function. But what additionally it will do? Let's see that. For example, set is on, output is on. In the meantime, while set is on, no, when this input is on, no, that time, if you are pressing reset, what is happening? Output is off. Even though the input is in on condition, output is off. So it is giving priority to reset. When comparing to set, it is giving priority to reset. Why I am telling the priority? Because see here, set is also on. But when reset function is on simultaneously or in the meantime of set on, output is responding to reset first. Got it? Suppose if I am turning off the reset, what is happening? Again your output is on because set function is on. So this is SR flip-flop. Got it? So in the meantime, when the set is on, if I turn on, output is off. For example, after that I am turning off set. If I turn off reset, output will remain on because set is not on. Got it? So this is set and reset function. Got it? So let's move on to the next flip-flop, that is RS. It is just opposite to SR. So here also I am going to give one memory address, and for this I am going to give one input. So see here, since it is a RS flip-flop, it is having first input as reset. This is set. I 0.1 is set. I 0.0 is reset. Can you see? These two are the inputs. input port of the block. So what are the ports which is left side of the block is inputs or inputs. What are the ports which is right side the block are called as outputs. Got it? Let's do the simulation for this. So it will also do the same set and reset function, but when it comes to priority, for what it is giving the preference. Let's see that. First I am turning on set. I am turning off the set. See, I0.1 is a set. I have turned on and turned off. Output remains on because it is a set function. Now I am going to do the reset. It will off. This is normal. Correct? So what it will do specially, let's see. I am turning on. In the meantime, I am turning on reset, but reset is not happening because it is giving preference to set function. For example, if I turn off the set function, output is off because reset is on, no? Right? So SR flip-flop and RS flip-flop will be similar to set and reset function, but for what it is giving priority, it is a matter. And for both the blocks, we are having two inputs, set and reset, and one output, which is Q. There you can connect a coil, and this is optional. You can, even you don't need to connect it. It is just option. It will not give any error. Let's see this. See, it's happening only. If you want to showcase, then you can make use of that. Else, no issues. See. Up to this it is coming. If coil is there, it will enable. That's it. Got it? So this is SR and RS in Siemens PLC. Fine. Let's move on to the next one. Yeah. What is this? Negative RLOH detection. This P is a positive RLOH detection. What is this H detection? H detection means whenever the pulse is changing from 0 to 1, that time it will give one pulse. That is positive pulse. Okay. Whenever the input is changing from 0 to 1, it is rising. No, from 0 to 1 it is rising, right? So that is positive H. Whenever it is changing from 1 to 0, that slope is there, right? That falling slope. That is negative edge. It is nothing but rising edge and falling edge. Okay. So how to do this in a Siemens? Let's see that. So I am connecting one input and I am connecting this P. Let's see the positive RLOH detection. This is result of logic operation. Fine. So this is also asking some question mark, just filled with one memory, right? I'm connecting one more output. You may ask me, this is a coil, no? Why can't it be here? Okay, it should not be there because this is going to capture the rising edge of this one and going to show the pulse in this one. Okay, so it is like a single pulse. Let's see how it works. Okay. See, whenever I am turning on I0.0, so it will be moving from 0 to 1. That single pulse will be passing to Q0.0. See, you cannot able to see here. Sometimes if I do fast, can you able to see? See, can you see that? Now, yeah, just now it came, no? So like that you can see the single pulse here. So how to maintain that output continuously? I can use a set function for that. Let's see that, okay? Fine. So why I am using the set function here? Because that single pulse cannot able to see because it is very fast. Correct? So how to see that means you can use the set function. See, when I am going to turn on, that single pulse is captured by the set function and it set the coil. That's it. This is how it will work. Got it? Fine. So this is positive edge, and opposite to this is negative edge. What is negative edge? When I 0.0 is going off, I mean it is changing from 1 to 0, no, that time it will be giving 1 pulse. I am going to take the coil which is here, no, I am going to take that. So this is N, that means negative edge detection. Can you see here? Negative RLO edge detection. RLO is the rung condition, right? So here also I am going to give one memory address which is different from this one. Okay, and this address you use to perform the particular instruction operation. So here also I am going to use set function. So I am going to use some different input, different output. Fine. Let's go for online and check. So whenever I 0.0 is turning on, it will give one pulse and it will be stored in Q 0.0. Whenever I 0.0 is going off, Q 0.1 is captured that pulse and it will be showcasing. Let me turn on. See, this is on. While going off, this will be on. See, got it? So that is rising edge and falling edge. It will not be continuous. Why? Because 0 to 1, that rising slope is only once it will happen, correct? After that it will be 1 only. And same for falling edge, it will be changing from 1 to 0 at only once. After that it will be maintaining 0. That's the logic. Fine. So like rising edge, falling edge as a coil, we are also having the same instruction in terms of block. Okay, and that is address positive edge detection, address negative edge detection. You may ask me, both are same, no? See here, this is also positive edge detection, this is also positive edge detection. Then what is the difference means? Let's see that. Can you see? It is a block. This was a coil. This was a coil. Okay. So for coil I have given M0.0 and this rising edge will be depends upon I 0.0 changing from 0 to 1. Okay. But this block, no. This block is having two address. It is asking two address. One is memory address, another one is block address. For example, if I have given the block address as I 0.2. I 0.2. Right? I have given the block address as I 0.2 and memory address as M0.0. Okay. So what will this instruction will do? No, it will be concentrating on when I 0.2 goes on. That time it will be giving the pulse. That is the difference between this block and this coil. This coil will be depend upon the contact which is connected in series. But this block will not bother about I 0.0 but it will bother about I 0.2. This is just a rung condition. This will be act as one normal switch which will be the condition for this. Okay, let's see that. See, forget about this one. Forget about this. This is just input and output. I'll do one thing. I'll delete that rung so it will not confuse you. Yeah, let's see this. Yeah, when I 0.0 is on, output is not on because this is just a wrong condition. So when I 0.2 is goes from 0 to 1, right? So that time it will be giving the pulse. Can you see here? Q 0.0 is on. Correct. So this is a block. Same thing for negative edge. I will be connecting on parallel this one, negative block. So here also it is asking the address. By using which one you want to catch the falling edge. I am going to use I 0.1. And memory bit I am just giving one more. And here I am going to use the reset function. So reset function is Q 0.0 because already I have done the set. For the same one I am going to do the reset. Now see here. Now I 0.1 is the, just a minute. In the previous I was explaining, that time I was not reset. That's what this is on. Now see, when I 0.0 is pressed, this is the wrong condition. When I 0.2 turning on, it will catch and it will turn on your output because it is a set function. So when I 0.1 is on, nothing is happening because this is a falling edge. No. So whenever it is changing from, this value is changing from 1 to 0, that time it will be giving a pulse which will turn off the Q 0.0. Right. So see here I am going to turn off this, which will make your output to 0. Got it? So this is address positive edge detection and address negative edge detection. This is similar to negative RLO edge detection. This is like a block. This will be a coil. So if it is a block, whatever address you are giving here, that will be considering for rising edge. Whatever address you are giving over the block, that will be considered for the negative edge. Right? So this is how you need to work with the bit logic instructions in Siemens. Fine. So we'll meet you all in the next session. Until then, bye. Hello everyone. In today's session, we are going to see about timers. So generally, timer is one of the important concept in ladder logic. So let me know, what is timer? So where and all we are using timer in our daily life. Fine. So if you find a home appliance like a washing machine, we have a timer. Induction stove, we have a timer. Right? So these are all doing some operation by using timer. You can set the timer in a washing machine, right? For 20 minutes, 30 minutes. After that, you turn off. Like that, you are setting a timer for the washing machine. Correct? So like that, industry is also in need of timer in most of the operations. Right? So, used to create a time delay between operations or activate and deactivate the device after the preset interval of time. What is the preset interval of time? Like washing machine should run for 20 minutes means you are setting the 20 minutes, right? That 20 minutes is preset interval of time. Okay. So on the whole, timer is used to give the time delay between the operations, or it is used to activate or deactivate any device. Fine. That may be a digital output or it may be a analog output. Fine. Let's see. There are generally 3 types of timers are there. One is on delay, off delay, retentive, on delay timer. Right? Retentive timer. Mostly it will be retentive on delay timer. These are all the generalized categories of timer in the industry. Fine. So before getting into what is on delay and off delay and all, you should know some timer specification. Right? Let's see the timer number. If you are using a timer in your PLC, obviously all the PLC software will ask for the address for the timer. The timer number is nothing but timer address. Okay, depends upon the PLC manufacturer, the timer number will get vary. Okay, in Siemens we are going to use the timer number as T0, T1 like that. In Allen Bradley it will be like T4:0 like that. It will get vary according to the PLC manufacturer, right? Then what is the preset value? So preset value already we have discussed, right? That washing machine 20 minutes. Okay, so that is also depends upon the program logic. Maybe in your application you may set a washing machine for 40 minutes. In my application I'm using it for 20 minutes. Some may be using the spin option for just 7 minutes. It depends, right? Okay, in some washing machine we are having the option to set a timer. In some cases automatically, for example, if I'm choosing the spin option, it should be 7. So it is fixed by the manufacturer of the washing machine for the spinning option, spinning operation. Okay, to dry the clothes we will be using the spinning, no, that one, right? So it depends upon the program logic, preset value. Okay, so to give that preset value also there should be some format. Fine. So while entering into the software, I'll let you know what is the format. Okay. Then what is this accumulator value? Accumulator value means, for example, now imagine, let's take that same washing machine example. I want to do the spinning operation, so I'm turning on. So in my washing machine, spinning time is 7 minutes. Okay, so whenever I'm pressing that spinning option, timer will also on. So it will be started counting, right? 1, 2, 3, 4 like that. It will count in a seconds, correct? And that counting option will it may be in seconds or it may be in milliseconds also. That's fine. Anyhow, it is counting from starting to 0 to 7, or countdown also in some PLC will happen 7 minutes to 0 minutes. Like anyhow, it is counting maybe up to down or down to up or up to down. Anything. Okay, so that counting value where it is storing, like 0, 1, 2, 3 up to 7 minutes it is going, no, how it is storing, and that running value of the timer is stored in accumulator value. So accumulator mostly it is running value. So when accumulator value reaches the preset value, that time my washing machine will get off. Right, let's imagine my washing machine is starting from down to up. It started counting 0, 1, 2, 3 like that. When it reached 7 minutes, 7 minutes is nothing but our preset value. Correct. So that time my spinning operation will get stopped. So it is deactivating my operation. It stopping my operation indirectly, right? So that is accumulator value. So PLC is storing that accumulator value also in some place. Okay, so why this accumulator value is important means, for example, in some cases you can make use of this accumulator value in your program. Okay, you can make like 1 to 2 minutes you do this operation, 2 to 3 minutes you do this operation by using a single timer, and by using that accumulator value of the timer, you can make use of so much of operation. Fine, that is the importance of accumulator value. Right? And what is this time base? Time base is nothing but how the timer is counting, whether it is counting in a seconds or milliseconds, like that. Why it is important means, timer base, if it is timer base is small, for example millisecond timer means the accuracy will be more, the resolution will be more. That's what. Mostly time base will be 1 minute. 1 second. Right? And enable bit, done bit, timer timing bit. So these are all the things you should know, because these are all the components which is common to all the PLCs. I'm not talking about only Siemens now. It's common to all the PLC. So enable bit. What is enable bit in a timer means? Obviously, for timer you should give one input. Okay? Timer is not an input. You should trigger the timer by using one digital input. Right? So whenever you are triggering, the timer is started running, no? So timer is doing its operation. Timer's input is on. Timer's input is one digital input, no? That is on. So enable bit will be on. So whenever a timer is receiving the input, Timer's enable bit should on. That means timer input is on, like that. Okay, and done bit. What is done bit? Yeah, my work is done. My 7 minutes delay I have done. Correct. So like that, you are doing a done bit. You are making use of the done bit. Done bit will indicate my work is done. My timer, you have given 5 seconds delay, so I am done with that. Like that, one bit will get enabled, and that is done bit. Okay, so there should be a difference between enable bit and done bit. Whenever you are turning on timer, that time itself enable bit will on. After that delay, whatever, for example, I have given the preset interval of 10 seconds. That time, done bit, after 10 seconds, done bit will on. Okay, and what is this timer timing bit means? It is between, for example, you are giving 10 seconds delay. You are giving input to the timer. So it is started counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So up from 1 to 10, the timer is running, right? Accumulator value is running. No, that time only this timer timing bit will be on. Okay, so these are all the 3 different types of bit in timers. But anyhow, timer timing bit will not be in Siemens. But it is good that you should know what are these bits and the timer specification. Got it? Let's move on to the first timer, on delay timer. So the name itself is telling that it is creating a delay between the on operation. It is delaying the on operation. Simple example I will tell. You are turning on your switch, maybe for fan or light, anything, but that fellow should not turn on immediately. After some seconds only it should on. Okay, so the switch you are turning on, it is creating a delay of 5 seconds or 10 seconds. After that only your fan will be on. So it is delaying the on operation of your fan, right? So that delay, whenever you are going to turn on something but you want a delay to turn on, that is on delay timer. The on delay timer operates such when the rung contains the timer is true. That means what? The input to the timer is true. Okay, the timed output becomes true after some time, which will activate the output connected after the timer. That means you may connect that output after the timer. That is your fan, nothing but your fan. Okay, so the timer is set to have a on delay. Okay, so the length of the time delay can be adjusted by changing the preset value. It may be 5 seconds, 10 seconds, it depends upon the logic. Okay, and what is a good example for understanding this? We have a air conditioner here. Okay, you just watch the air conditioner. You are having 2 inputs for the air conditioner. One is main switch. Main switch means the switch which is in a plug board, panel board, no? Okay, another one is your remote. Okay, so whenever you are turning on an air conditioner in the switchboard, you will be turning on. Immediately if you press the remote on button, the air conditioner will not on. Do you ever tried that? If no, please try that. Okay, so you will be turning on the switchboard. You will be turning on the switch in the switchboard. Immediately at the next moment, if you turn on the AC using the remote, it will not on. Why? Means air conditioner is taking some delay to turn on. It will give one beep sound, right? After that, if you use your remote, it will be on. Okay, that is on delay timer. It is giving a delay for the turning on of the air conditioner. It will give one beep sound. After that, if I turn on, it will on. Right? It is taking some time delay. Right? So that is on delay timer. The next one we are having is off delay timer. Right? So off delay timer means, obviously name itself is telling that it is delaying the off condition. Right? The perfect example of here one thing you need to know, if delaying the off condition means whether it will give delay for the on condition? No. Obviously no. Here is the concept you need to understand between the difference between on delay and off delay. Same example we will take, that fan and switch. You are turning on the switch, fan will immediately on. Whenever you are turning off the switch, it will take preset value, I mean maybe 10 seconds or 5 seconds. After that it will turn off. Okay, so for turning on, it will be the normal operation. You will be turning on, fan will be on immediately. But when you are going to turn off, it will take some time to turn off. Correct? That is off delay timer. The perfect example of off delay timer is, we have a sleep option in TV, right? After 20 minutes, after 30 minutes, like that in TV we have an option. So what will happen after 20 minutes? It will automatically off. Right, and obviously, and in the induction stove also. Okay, so if you turn off the induction stove button, it will immediately will not go off. It will take some time. After that, it will go off. Okay, I'm talking about the button which is on the induction panel, not a main switch. Okay, if you turn off the main switch, it will off, because that is like a main control. But I'm talking about the switch button which is in the panel of the induction. Okay, so these are all the example for off delay timer. And the next one we are having here is retentive on delay timer. So it is similar to on delay timer. What it is doing? It is delaying the on condition, right? But what is the difference between on delay and retentive means? For on delay, you are turning on, a timer started running, it will start counting from 1, 2, 3, 4, 5, 6. In some cases, if you are turning off, in any situation, if you are turning off your input, the timer will go off. The timer will not run, because the run condition become false, no. The input timer turns off will make the timer off. That is on delay and off delay. Okay, but in retentive, even though if you turn off your input after some time, the timer still runs. Can you get the point? On delay timer will depends upon it. The operation will be happening only if the input condition is on. I'll show that in software so that you can understand better. Just understand what I'm saying now. So the difference between on delay and retentive is, for the retentive, a single pulse is enough. If you are turning on, after that if you turn off your input, it will still running. Where is the application of this retentive on delay timer means? Imagine you are filling a bottle. Okay, for example, we have a coffee vending machines and all, no. So the solenoid valve which is letting the coffee to go, coffee outlet, right? You are keeping a cup or something over here. They are giving some cup, okay. So in that, the solenoid valve will open for just 10 seconds. In that 10 seconds, the cup will get filled. That is the program logic they have done. Okay, so you are keeping the cup. Solenoid valve is on. At the 5th second of the solenoid valve, the main power goes off. So the solenoid valve is not getting input. So the solenoid valve will go off. So your cup is half filled of coffee. Correct? For 5 seconds only it is filled. At the next moment the current came. The solenoid valve again started from 10 seconds means your cup will get overflow, right? For the remaining 5 seconds of the coffee will go waste. Huh? So this is one example that for easy understanding I'm telling. Okay, what is the problem here? For that solenoid valve I am creating for 10 seconds only you should operate. If I am putting an on delay timer or any other timer for in that place, it will be turning on for the 10 seconds. If some power supply is cut off, that timer is getting reset. That is the one thing you need to understand. Reset. Reset means what? Timer accumulator value will go back to 0. Whenever the power comes, timer accumulator value will start from 1, 2, 3, 4. Like that it will start again. But I don't want that. My coffee is already 5 seconds filled. I don't want to stop it. So retentive timer, what it will happen? No. Even though the input condition goes off, return to timer will finish the 10 seconds. After that it will go off. So your coffee will get 5 seconds. At the 5 seconds the input condition goes false. The solenoid valve remains to give the remaining 5 seconds coffee. That is retentive on delay timer. Fine? Yeah. So I'll share the software screen. We'll see everything in the software now. Fine. Yeah. So you can find the timers here. Can you see? 5 block type of timers are here and 5 coil type timers are here. Right? So 5 coil type and 5 block type. So generally 3 types of timer we have seen, but according to the software, according to the brand of the PLC, they may have their own timers. Okay, like that in Siemens PLC we have on delay timer. That one we have known already. This is off delay timer. If you are not getting the name, please see here. In this place they are specifying what is the name of the timer, right? So this is on delay. ODT is on delay. This is off delay. This one. This is retentive on delay. These are all the 3 timers we have seen already. Right? And they are having 2 more timers. See, pulse timer. Pulse extended timer. We are going to study that maybe in the next session. Right? We'll see about the on delay timer now. In the next session, we'll see the remaining 2 timers, general timers, off delay and retentive. Okay. So I'm going to take this on delay timer. Yeah. So this is the block will be looks like this, and it is having 3 inputs and 3 outputs. A timer is having 3 inputs and 3 outputs. So for input, it is having yes set. Okay. Maybe a input. Just a input. Okay. And this is reset option, and this is TV. What is this TV? This is preset value. This is the place where we need to give the preset value. See, they have given yes 5 times. That means preset value. And what is this question mark? Timer number. I have told no timer specification, timer address. Fine. This Q is the timer output. Okay. This one is accumulator value. These 2 are the accumulator value. BI and BCD. Okay. In these 2 places you can get the accumulator value of the timer. Right? Right. So I am going to give one input here. We'll give I 0.0. And I have told no. For in Siemens, we have a timer address as T0, T1, T2 like that. So I am going to give T0. Okay. And here, what I need to give here? Preset. That may be 5 seconds or 10 seconds like that. Okay. So I am going to give a 10 seconds. Should I give a 10 seconds like this? See, unexpected input end. Okay. In some PLC, in some PLC program, maybe in some other software, you can give the 10 seconds directly. But in Siemens, you should have a format. In that format only you should give. What is that format? Means S5T hash. S5T hash. Right? After that you should give 5 seconds or 10 seconds, anything. I'm going to give 10 seconds. So S5T hash 10S. See, it is accepting now. So this is a format to give the preset value in timer. Fine. So I'm going to connect one output here. What is the output? Let it be anything. Right? And it is asking the reset. What is the purpose of reset input in the timer means? In between, if you want to turn off the running of the timer, you can make use of this input. This is the option here. Anyhow, I will explain in the next. First we will do the simulation now. After that we will see what if I give the reset. See, now I have given a 10 seconds delay to turn on this fellow, right? So let's see what the timer is doing. I'm going to turn on I 0.0. This is the timer input. When the run condition goes on, timer will start running. No, that condition is this one. Okay. See, timer started running. It is starting from up to down. See, 5 seconds, 4 seconds, 3 seconds, 2. This is accumulated value. See, after it is reached 0, the output is on. Okay. So the Q 0.0 was not on when I was pressed I 0.0. It is turned on after 10 seconds, right? For example, if you turn off, on the whole it will off. We'll see it again. You are turning on. It is creating a 10 seconds delay. After that Q 0.0 is on. Don't confuse why it is counting down. It depends upon the PLC manufacturer, right? Anyhow, it is counting, no. From top to bottom, it is counting. That's it. Got it? Let me change the preset value and check once. I'm going to change only for 5 seconds. I'll do. See? Right? Fine. So like this, you can make use of the timers. You can also give preset value in hours, in minutes also. If seconds means you will be using S, for hours it will be H, and minutes it will be M. Okay. So that and all you can get in a specification sheet. Now I'm going to introduce this reset. What is the purpose of the reset? What is the influence it will create? Let's see that. For that, I'm going to increase the timer preset for 15 seconds. Okay. Anything you can give, but to view, no. For example, we need to view it properly. That's what I'm increasing the preset value. Let's run. I'm turning on. Timer is running. Immediately, you do something, I'm going to turn off. So, you have two options. One is I 0.0 straightly you can cut. See, if I turn off this, automatically this fellow is off. If I again turn on, it will start from the 15 only. So in between, without turning off I 0.0, you want to turn off your timer, means you can make use of the reset. See, when the reset is on, immediately accumulated value will go to 0. If you release the reset, still it is not running because it needs a fresh pulse to turn on. If I turn off, it will be like this. Even though if you turn on again, input again, it will start from the beginning. Reset value is to make the accumulator value to go back to 0. Okay. So this is on delay timer. And there are two ways to give the output to the timer. One is you can connect the output directly here, and here also you may connect one more input. That is also fine. Here as usual you can connect parallel contacts. This is one way. Another way of giving timer output is you can make use of one input contact with the address of T0. This is done bit. This is done. This is done bit. After your operation only it is off. No, this is done bit. After that you can turn on one fellow. That will be U0.3. Let it be. Okay. So I'm turning on. Let's see. Both are same. You can connect here also. In some other places if you want to use, you can make use of this T0. So let's see that. Timer is running for 15 seconds. So all three output will turn on at the same time. Yeah, fine. So if you are reset, all outputs will go, I 0.1, all outputs will go off. Got it? So this is on delay timer, guys. Let's see about off delay and retentive on delay and the remaining timers in next session. Fine? Yeah. So we'll meet you all in the next session, guys. Thank you. Hello everyone. In today's session we are going to see about the off delay timer and retentive on delay timer, right? So in the previous session we have seen the on delay timer. So let's see the off delay timer now. So this is the off delay timer instruction, right? S_OFFDT. So how to get this timer here? Click on the run. Click on this. It will come, right? So here also you can make use of the timer address T0, right? And here I have told about the format, right? Same format, S5T hash 5 years or 10 as it may be. Okay. So here also I am connecting one output. So what off delay timer will do? It will delaying the off condition. So what will happen now? If you turn on I0.0, immediately Q0.0 will on, right? So if you turn off I0.0, Q0.0 will not off. It will take 5 seconds to turn off. That's the logic here. Okay. Let's see the simulation. Yeah. Ready to run? Output is on immediately. Okay, it is not similar to on delay, right? It is delaying the off condition. So it is not having any influence while turning on. That's the logic. Okay. So now what I'm going to do? I'm going to turn off. This fellow will not go off. It will take 5 seconds to turn off. Let me see that. Yeah, can you see? It is not turning off. Timer started running after I pressed off condition. Correct. So after that your Q0.0 is also off. I'm repeating. See? It is on normally, like how we are turning off a switch, it will turn off the output immediately, like that. So but if you turn off, it will take the seconds whatever you have specified in the preset. After that it will turn off, delaying the off condition. Okay, got it? Yeah. So now I'm going to add the reset here. Let's see what is the reset having influence. Yeah, let me turn on. It is running. For example, if I'm pressing reset now, what is happening? Your output is off, right? This is one thing. If you turn off, the output will again on because input is coming, no? Okay, but in on delay timer, it was not turned on. You need to give the input pulse again, right? Now see, now I'm going to turn off. Your output is still on. In this time, if I press the reset, the accumulator value will go back to the 0. So output will also remains on. Okay, now again you need to give a pulse. If you turn off, it will start running. If you press the reset, accumulator value will go to 0. Right? So this is the reset function. So let's see one more time. So here also you can use the input contact with the T0 address to make use of the another output. Let me connect one more rung here. See, I'm going to use T0 and one more output here. So this T0 is nothing but timer output, right? So I'm going to give another address here. So let's see. Yeah, see here. Both the outputs will turn on because timer is on. If you turn off, both the outputs will not go off until accumulator value goes to 0. See, both the outputs are on, and when the accumulator value is 0, both the outputs will go off. So you can make use of this type of contact wherever you want. Okay, for example, you are using a timer in the first rung, but in the 15th rung you are in need of this timer's output. That time what you can do, you can make use of this T0 to use in your rung. Fine, got it? So this is off delay timer, right? So let's move on to the retentive on delay timer. So what I'm going to do, I'm going to replace that timer with retentive on delay timer, right? So here I'm going to give address of T0, right? I'm going to give the preset value. Let me go for the online. See what it will do. It will also create the on delay timer. See, if I turn on, it will not on the output immediately. After some time it will on. Correct? After some time it will on. This is similar to on delay timer. But what is the difference? Let's see. So now if I turn off your I 0.0, see, still these outputs is turned on. Timer is still on. Even though if I cut down the input, timer is still on, then how come I can turn off the output? So here reset is mandatory. In our previous timers we are not using the reset, and we have used reset in some places to, for understanding. But whenever I am turning off the input, all the output and timers is also off. But here I am turning off the output, will not having any influence with the timer. So the timer triggers with one pulse and will continue its work. So how can I reset the timer? So for that I need to use the reset switch. So reset is mandatory here. Without using reset you cannot able to turn off the timer. See, if I go for on and still it is in on, because in a previous condition I have not reset. No, so see, if I press I 0.1 it will get reset. Got it? So this is retentive on delay. So main thing, see, it is working with single pulse. I have told you, see, I'm turning on, immediately I'm going to turn off. See, still it is running without the input pulse. Okay, this is the difference between on delay timer and retentive on delay timer. Let me do one thing. In this rung, I'm going to put on delay. Let's see that, so that you can understand better. I'm going to put on delay here. Okay, I'm going to use a different address because I'm going to use two timers, no? So address should not be same. If this is one timer, this is another timer, another different timer. So I should use a different address. So here I'm going to give the same time. Let me increase so that we can see the output for some time. Right? Shall we run this so that we can see the difference? Yeah, I'm connecting, both the inputs are same, but output should be different. So I'll first reset this. Yeah, it's done. So now I'm going to turn on. Let's watch both the timers carefully. I'll tell what it will do. I'm turning on I 0.0. Both the timer will start running. I have given 10 seconds. No, it will start at counting from 10, 9, 8, 7, like that it will start. In between, if I turn off I 0.0, on delay timer will go off. Retentive on delay timer will continue to on. That is the thing it is going to do. Let's see. I'm turning on. At the 8th second, I'm disconnecting. See, here it is stopped, but it is still running. Got it? This is the difference between these two timers. Let me connect off delay also. I'll connect here itself. This is off delay. This is also another different timer, so I'm going to use another different address. I'm going to give same 10 seconds delay with one different output. I'm going to connect Q0.2. Output should be different. You cannot connect same output for all. Right? Shall we see? So what off delay timer will do now? If you turn on input, immediately it will on. Okay? Let me see here. Yeah. I'm going to turn on. See, this fellow is immediately on. So if I turn off, it continued to run. It is started running to turn off this. That's the logic. After some time it is off. Okay. So these are all the 3 general timers that you can find in all brand of PLC. Got it? So this is on delay, off delay and retentive on delay timer. So for all the retentive timers, reset is very important. If the retentive timer, see here, in this retentive, I have not used the reset bit before, but it was accepting. But when it comes to online, I couldn't be able to turn off the output. That time I suggest you to go for the reset. Correct? But in some PLC, if you are not giving the reset, it will give you the program error. Here in Siemens, it is accepted. Okay. So reset is, retentive means reset should be there. Because retentive means that input pulse will go off, will not having any influence. No? Then how come you will turn off the timer? There should be some control in our hand so that we can turn off the timer. No. That control should be with the with the help of reset. Got it? So these are all the 3 timers we have seen. In our next session, we will be seeing the remaining 2 timers. Fine. And we'll see about this also. What is this and all. Okay. So I hope you have understood the timer concept. We'll meet you all in the next session. Thank you guys. Hello everyone. In today's session, we are going to see about the remaining 2 timers over here, which is pulse timer and extended pulse timer. Fine. So let's see what is this pulse timer. So in our introduction to the timer session, we have seen the timer specification. In that timer specification, I have told about timer timing bit. Do you remember that? What is the timer timing bit? It will be on only when the timer is counting. When the accumulator value is running, that time only the timer will be on. That timer timing bit will be on. Okay, so that is these 2 timers. According to the timer timing bit, if you understand the timer timing bit, these 2 will be very easy for understanding. Let's see the timer. So I'm going to connect 1 input and timer and 1 output here. Let's see the pulse timer. Okay, so what is this pulse timer means? It will not be like delay and all. Okay, so if you are turning input, output will be on immediately. After some time, it will go off. After the specified time, it will be going off. Okay, so let's see that. Here also I'm going to give T0 as an address and timer preset value is I'm giving us 10 seconds. Okay, here I'm going to give I0.0 and here I'm going to give Q0.0. Right? So let's see what it is doing. So let me share the screen again. Yeah. So let's see what it is doing now. Okay. I'm going to turn on the input. See, immediately output is on. Timer is also running. Let's see after the time delay what the output is doing. See, output is going off. Can you get the point? So this is pulse timer. Let me do it again. See, it is immediately output is on, timer is also on. Both are happening simultaneously. So after the time delay, your output will go off. Right? So what will happen if I turn off the input after some time? Let's see that. Yeah, let's see that. I'm going to turn on. Timer is running. If I turn off, output is also off. It is stopped with this 6 seconds. Already 4 seconds only happened. So if I turn on again, it will start from the beginning. Okay. So while turning off, it is stopped here, because if I have used the reset, it will go back to 0. Even though if I again turn on, it will start from the beginning. This is pulse timer. So pulse timer acts like a timer timing bit. So whenever the timer is running, that time only output will be on. After the accumulator value is stopped, right? It started counting from 10, 9, 8, 7 and up to 0 it will be running. When it reached 0, when it comes to 1, it will be running. When it comes to 0, it stopped running. This is timer timing bit I have discussed already. Fine. So this is pulse timer. Got it? So I'll do one thing. I'll use a reset bit over here. See, I'm going to turn on. Immediately I'm doing the reset. What is happening? Accumulator value go back to 0. The purpose of reset is to make the accumulator value to the 0. So if I turn off reset, it will still in the same condition, because it is a pulse timer. No, you should give the fresh pulse again. See? Got it? If I turn off, it will off. This is pulse timer. Let's see about the pulse extended timer. So what is this pulse extended means? It's similar to pulse timer. What is the difference then? Extended pulse. That means even though if you turn off your input, it will continue to run like we have seen in the retentive. Got it? So let's see that. I'm connecting here itself so that you can understand better. This is pulse extended. Okay, here I'm going to give one different address. This is output. I'm going to give different address. Got it? So let's turn on. Yeah. So what's the difference? Or first see this one. I'm turning on. Input is running. Correct? Timer is output is also on. If I turn off, here it is still running to finish the accumulator value to meet 0. Got it? See, it is off after the time delay. But what will happen to this pulse? It is immediately off if I cut down this. This is extended pulse. That means one pulse is enough. After though, if you turn off this, it will not affect your timer. See, I am turning off I0.0, which will make this timer to off, which will make this timer to continue on. It is extended. That's it. Both are working as a timer timing bit only, but the difference is input pulse. Here it is needed continuously. Here one pulse is enough to start the timer. That's a difference. This is pulse and this is extended pulse. So there are 5 timers in the Siemens PLC. On delay, off delay, retentive on delay, pulse timer, extended pulse timer. So according to the logic your application or your whatever the project requests, according to that you need to prefer the timer. Fine. So anyhow, we are going to see some examples in the next classes. Depends upon the timer. Okay. Regarding timers, we will be seeing the examples. So we can understand better over there. Right. So let's move on to the coil type timers. What is this coil type timers? Can you just click on this and check? This is pulse timer. Oh, this is this one. This is extended pulse. This one. Same. This is also going to work as a same as a these type of block instruction. This is a block instruction. This will be like a coil instruction. Let me show that also for you. Okay, this is a coil type, no? So I should connect as a coil here. See, I'm clicking on here. I'm going to give the on delay first. On delay timer I'm going to give. See, it is coming like a coil. And it is asking 2 question mark. This is what? This is timer. I mean the timer address we need to give. Timer address we need to give. Okay. And this S5 time. This is a preset value. Right. So we'll give the timer number here. Here is the preset value. Right. So since it is the end, since it is a coil, how come I can get the timer input, timer output? So for that I have already explained that T0. Right. This one. T0 and that the regarding output. Yeah. Can you see here? So I'm taking the feedback from the timer and I'm making the contact as T0 that is connected with the Q0.0. Let me run and let me check. See, whenever I'm turning on, this value is on. See, it is creating on delay. After the 5 seconds, the output is on. Correct? So if you turn off, both the rungs will be off. If you again turn on, it will be doing the operation. Got it? So it is doing the same operation whatever we have seen already, but this is a coil type. Correct? So let's replace this one with off delay. This is off delay. I'm going to give some timer address. Let's see this one what it will do. Turn on. Immediately output will be on. If you turn off, output will not be off. It will take 5 seconds to turn off. That's it. Fine. Got the point? This is a coil type. So I cannot connect here. So I am connecting in the next rung. So if you want to connect here, what you can do, no, you can take one branch and there you can connect like this. This is also right. Both are right. I am just connecting in the next rung. Here you can take a branch, you can connect. I am just connecting one more output here. Okay. Both are going to be doing the same operation. Let me check this. See, both are on now. If I turn off, this fellow will be off. Why? Why? Because this condition is there, right? This is also one rung condition. Okay, you should be make sure if you are connecting in a parallel, this fellow should not go off. Instead of that, I am going to connect one more input here. Let's see, I am going to connect one more input here and this should be the timer input. This is the timer input and this is just one rung condition. Let's do this. Like a on switch. Okay. So I'm going to turn on the on switch. After that I'm going to turn on the timer. Okay. See here. Now all the outputs are on. Even though if you turn off, this fellow will not be off. After some time, these two will go off. Okay. So here this is a rung condition. This is timer input. So like this, according to the logic needs, you can make your program change according to that. Fine. Let's move on to the next timer, which is return to. I'll delete this. What is return to here? So it will be like this SS. So I'm going to connect this one, and this is T0. Fine. So let's move on to the online. So if I turn on, output will be turned on after some time. This is retentive on delay timer. If I turn off in between, it will still it will be running. So now how to turn off this? So in the previous block like structure, in this you have a reset input, but here I am not having any reset. How to make a reset? You can make use of another rung and give one input. This is a reset input. Okay, let it be, this is the reset input, and in bit logic we have this reset coil. No, you can make use of that reset coil here, and this should be your, which one you want to reset, that one you need to give, that should be T0. Got it? So if you go for the online, I'll just reset this first. Yes, so I'm going to run. Even though if I turn off, output will still remaining on. Timer is remaining on and output is on. If you want to turn off the output and turn off the timer, see, timer is also on. Can you see here? This is timer on. So if you turn on, output will be off. This is how you need to use the reset instructions. Right? Got it? So in a coil type timer, you will not have a reset option in the timer itself. You should take the reset from outside. Got it? So the same thing you need to do it for the pulse timer and extended pulse timer. Okay? So let me see some examples in the timers in the... Hello everyone. In our previous session, I have told we are going to see about the counters in this session. There is one small correction over here. In counters, we are in need to use the comparators. So better we will see about the comparator topic before getting into the counters. Got it? So generally, what is comparator? So we have usually 6 comparators, right? One is less than, greater than, equal to, not equal to, greater than or equal to, less than or equal to. So usually where we will be preferring such functions, right? When you want to compare two things, that may be a number, that may be a string. Okay, so when you want to compare two parameters, obviously you may in need of any one of the 6 comparators. For example, if you are having a let's take a tank example. Okay, you are having a tank and you want the tank to be at the level of 80 liters. Okay, and you are having an inlet valve which is feeding the water inside. And what you will be doing? You will be comparing the tank present level with your preset value. You will be comparing whether the given value is equaling 80, which is the set point. Okay, so here it is like set point. Correct? Or in some other case, if you want to create an alarm, like when your tank value is reached above 80, when it is crossing 80, you want to give an alarm. In that time, what you will be using? Greater than or equal to, or you will be using only greater than. When greater than 80, let me know, I need to create an alarm. Okay, so like that, there are so many applications are there, depends upon the comparator. So comparator is one of the important function in PLC. Got it? So let's see what are the comparators and we are having in Siemens. Can you see here? We have more comparators here. It is all about the blocks. Correct? So if you have a look into this, see here, this is equal. Right? This is compare integer for equal to. So comparator block we are having in Siemens is for the analog values. That means it may be a integer or it may be a real or double integer. Okay. So if it is an integer, that means that will be a 16-bit. Correct? So what they have given means for the 6 comparators they are having. See, this is equal, not equal, greater than, less than, greater than or equal to, less than or equal to. Like that we are having 6 comparators. This is for integer. And the same comparators are there for double integer. Okay, this is 32-bit. And the next 6 set is for the real. Real means what? Floating point number. Got it? So this is how we are going to make use of the comparators. Okay. So let me see how to use the comparator block. Okay. Since we are going to touch the analog values, just remember what are the address I have told for analog in a simulation. For a 16-bit, it should be MW0. For the first input means it should be MW0 or anything you can take. For the first input, you can take MW10 also. So that will be taking MW10 and MW11 channel. 2 channels it will take for 16-bit because one channel is having 8 bits. These are all the things we have discussed in our initial session about the addressing. Correct. So if I am going to use the integer block, what address I need to use? Let's see that. Click on the run and click on the block. Okay. So it is not asking any question mark about the block. It is not asking any address, block address for this. So there is no need to give. But it is asking a question mark over here to give the input. So what we are going to do? We are going to compare 2 integers. Can you get the point? See here. This is integer. This is the second integer. Got it? So let me give. You can give the constant value also. For here, see here I am giving just 90 and here I am going to give 100. Okay. So output. The output of the block I want to showcase in Q0.0. Let me run. See, initially the output is off because input condition I have not turned on. So what I am going to do, I am going to turn on I0.0. Output is off. Why? Because 90 is not equal to 100. Okay. Both are not an equal integer. So your output is off. Got it? So this is how the comparators will be working. So if you want to change the value in the runtime, you can give the address here. MW0 for the first integer. Let it be, this will be the 100, okay. This may be your set point. Okay. So let me run now. See, I am going to turn on. My output is off because 0 is not equal to 100. Now I want to change the value of MW0. Because tank value will be coming online, no? How can I change? Click on that. Click on this place. Right click. Modify. Okay. So here you need to give the value. So I am just giving 100. Can you see your output is on? Because both the values are equal. So it is turned on. Now let me change this to 99. See here. Output is off. Got it? So this is how comparator block will work. See, it is accepting negative value also because this is integer. Got it? Right? So this is how comparator block will be working. Fine. Let me change the block to not equal to block. What is not equal to block? When two numbers are not equal, it will be giving output. If both are equal, it will not give the output. Got it? So I am going to change this as MW0 and the next one is MW2. Let me give both the values in online. Now see here, already I have given that MW0 as -7. No, that's what it is taking the previous value. Now since -7 is not equal to 0, it is giving output. Let me do one thing. I am going to change this one also to -7. Let's see what will happen to the output. Output is turned off. Why? Because this is not equal to block. Output is off because it is not equal to block. Understood? So like that we are having greater than less than, greater than or equal to, like that we have all the blocks over here. I'll do one thing, I'll connect all the blocks in the parallel here. Greater than, I'll take one more branch from here, less than, and up next it will be greater than or equal to, and next will be less than or equal to. It added here. I'll take a branch that will be less than or equal to. Got it? So for all I'm going to give the same address. Let it be MW0, MW2. I'll copy this and I'm going to paste it in all the place. Right? Next one is this one, MW2. Why I am giving same values means for each and every time we will be changing, no? If once I change, it will be common to all. So same here, I am going to connect one output here. Different output it should be. Input can be, you can use in multiple places, but output should be different. Output should be in only one place. That's what I'm connecting 5 different output. Let me go online and check. Yeah. See what is happening. Only 2 blocks are on. Can you see here? This is on and this is on. Why? This is greater than or equal to and this is less than or equal to. Equal to is there, no? That's what both the blocks are on. Right? So this is not equal to, this is greater than, this is less than. Let's see, if I turn on, Q0.3 and Q0.4 will be on. Can you check? See, remaining and all is off because it's not matching our condition. Okay, let me change this. Let me change this MW2. I'm changing that to 0. So when I'm changing that to 0, see here, not equal to block will on. Greater than is not on because it is comparing MW0 greater than MW2. MW0 I have given is -7, MW2 is 0. So it's not true, no. That's what this fellow is off. Got it? So see here, next, less than. -7 is less than 0. Yes, it is true. So it is on. And -7 greater than or equal to 0. No. It is actually less than and not equal to. So both the cases it is false. So it is false. And check out here. It is less than or equal to. So -7 is less than but not equal to. But it is like our option, no? Less than is true. So it is making the output to turn on. Got it? So it is comparing the first parameter with second one. So how you will frame the equation? MW0 greater than MW2. For example, how you will be checking this? MW0 less than or equal to MW2. Like that you need to check. If you check for MW2 greater than or equal to MW, you should not do like this. Okay. First input is the first parameter you need to compare. Got it? So this is how you need to use the integer block. Got it? So how to use this block? It's very simple. What we are going to do means, instead of integer, if you want to use the double integer, what you will do? So deleting, okay, I'll delete this. I'll take one double equal to block. Let's delete all these. Yeah, I'm taking equal, not equal will take, and here will take greater than, and I'll take less than or equal to I am taking, and let it be this greater than or equal to. Okay, fine. What address we need to give? Suppose I'm giving MW0. Can you check? It is giving an error. Can you see this MW0 is turning red color? Why? This is a double integer block. I should give the proper address. So this should be MD0. What will be the next one? If you are giving MD2, it will accept. But when you are going for the input, you are feeding the input. No, that time it will be issue. Why? Because 32-bit will have 4 channels. So 0 you are using means 0th channel, 1st channel, 2nd channel, 3rd channel. All these 4 channels are dedicated to input 1. So you should use the next free channel is MD4. Okay, got it? So I'm going to use the same channels over here also. I'll copy this. Got it? So this is how it is going to work. Let's see. Remaining and all. Addressing part is different. Apart from that, everything is common. Okay. So here I'm going to give some values. See, I'm giving 89 and here it should be, let it be 89. Since it is a 32-bit, it is showing a value like this. Okay, so 89, 89 equal. So it is giving, this is greater than or equal. This is less than or equal. This is greater than or equal. Since it is equal, it is giving the output. Let me change one thing. Here I am changing that to 100. What we are having? Not equal to block we have not used here. So this is, this is not equal to, I'm sorry. This is not equal to. Okay, I have not used this block. Less than block I have not used. All the blocks are doing the same, no? That's what. Okay, this is greater than block. 89 greater than 100. It's not true, so it is not on. See here 89 greater than or equal, less than or equal to 100. So equal to is there, so it is not happening, but less than is true. Correct? That's what Q0.3 is on. Got it? So this is how you need to use the integer block. Okay. So how to use the real block? This one is the real block. So there what we need to give? We need to give a floating point address. Correct? Let me take one equal block and here not equal to block will take. Here one thing will take greater than or equal to. Here I am going to take greater than is taken already. Here I'll take greater than or equal to, and here this time will take less than. Last time we missed this, no? This time we'll take this. Okay. So here also address should be same, correct? So I'm going to give MD4, here also MD4, MD4. Why? Because real also 32-bit. Correct now? So there is no separate address for real. Real also 32-bit. So I'm going to use the same address, whatever I have used for the double integer. So then why we are having a different block? Both are 32 bits only. Then why I'm having double integer block is different, real block is different? Because real block input should be a floating point number. Okay, for double integer we are not having a floating point. Okay, so how we need to give a output means, for example, see here I am going to give 1.5. Okay, MD0 is 1.5. MD4 I need to give is 89.9. I'll give some bit less. I'll give 2.5. Okay, see here equal block is off because 1.5 is not equal to 2.5. Correct? Not equal to will be turned on because both are not equal. See here greater than, obviously 1.5 is not greater than 2.5, so it is off. See here greater than or equal to, this is also not true, but less than is true. Got it? So what if I am not giving the floating, this point if I'm not giving means what will happen? It will be showing a value like this. Okay, but indirectly it is taking the 7 I have given. I have given the 7, no, it is taking. See, not equal to block is turned on. Okay, so if I give 1.5 here, so you should give the floating point number. I'll give 1.5 now. So all equal blocks will be turned on. Greater than or equal to will be turned on. Less than will go off because it is not less than. So same thing. These blocks are also turned off. So like this only we need to use the comparator instructions. So in a counter we are in need of a comparator instruction. That's what I have taken comparators before the counters. Let me move on to the counter chapter in our next session. Until then, bye. Hello everyone. In today's session, we are going to see about counters. Like timers, counter is also one of the important function in PLC. Let's see what is counter and how to use it in a software. So generally, counter is used to count up or down or doing the both function. Right? So in a process, if you want to count any products, you may come across in so many examples, like in an industry, in a conveyor belt, some products will be moving. If they want to check how many products they have received or how many product is getting packed. So for these functions and all, counter is playing a vital role. So in an industry, there are 3 types of counters we are having. One is up counter, then down counter, and it having a both function, that is up down counter. Fine. So mostly in industry they will be using up counter. Comparing to down counter, people are using up counter more. Fine. So what are the timer specifications? Here counter is also having some specification. Let's see that. Yes, here also counter need a number. This is counter address. So we have seen a timer address, right? T0, T1, like that. We have a counter address here. That is one of the mandatory thing that we need to use. According to the manufacturer, the counter address will get vary. Fine. So next one is preset value. What is this preset value? For example, you are going to count one product and that product is equal to 5 means. If the count of the product is 5 means, you need a signal from the counter. Why we are using a counter? At one point it should give a signal so that I can start or stop some function. Correct? I can do some action. For example, if you want to pack only 10 products, at the end of 10 products, it may shut the door of the outlet. So like that we can do so many options or functions we can do. So for that I need one limit number, and that limit number is nothing but a preset value. Fine. That is a limit. Preset means up to this count, like that. Correct. Next one is accumulator value. So as we have discussed in the timer, accumulator is a running value. What is the current product? What is the count of the current product? It may be 1 or it may be 2, 3, 4, 5, like that. It is a running value. How many products has crossed the counter? Got it? Right? For example, you can take 10 products you want to pack. Right? You want to, let it be, take some product like some chips packet or something, or any food item. Okay, you want to pack by 10, right? So one product is crossing, so it is counting 1. So next 2, 3, 4, like that accumulator value will be running. When accumulator value reached preset value, what is the preset value in our example? It is 10. Got it? So when accumulator value reached 10, it will give the signal that I have reached 10. So with that signal, you can close the exit, or you can stop the conveyor motor where the products are moving. right? So like that you can make use of the counter in your application according to the requirement. Got it? Now we are going to see how to use these counters in software. Let me share the software. Yes. So where is the counter tool? So can you see here in the side window, there is a counter option under the converters, correct? So see, this is up down counter. Next one is CU, up counter. Up next is down counter. Got it? Right? And as same in timer, here also some coil type is there. Correct? Let me see the block type. After that we will discuss about the coil type in the next session. Got it? So what I'm going to do, I'm going to use the up counter for my program. Right? So what I'm going to do, I'll delete the previous one. Right? So I'm going to put a up counter here. So I selected the rung and I'm going to put. Right? So see here, this is the block of counter, up counter. So since I have told about the timer counter number, right? Like that it is also asking a question mark. So I should give the counter address. What is the purpose of counter address? Because PLC need to know, right? That's what we need to give the address. So in Siemens, timer address is like T0, T1 like that. For counter it is C0, C1, C2 like that it will go. And the maximum counters and timers will be fixed by the product manufacturer. I mean Siemens. Right? Fine. So I'm going to give this is C0. Got it? And see how many inputs we are having? 1, 2, 3, 4. We are having 4 input to the counter. Correct? What is the CU? What is the input we need to give to CU? This CU is the one which is getting the input to the counter. For example, I'll tell you the product example we have seen 10 products I need to pack. In that, which sensor is detecting the object is crossing? Maybe that is the proximity sensor or object detecting sensor, anything it may be. So that sensor is sensing the product is crossing, or it is sensing the product and it is giving the signal. No, that input should be your counter input. Like because of that input only the counter is started counting. You can take in that way also. Okay, so what I'm going to do, I'm thinking that, and I'm making this I0.0 is one sensor which is detecting the input. I'll take we will take the car parking example. Okay, so this is a entry. So I can park up to 5 cars, or let it be for example 3 cars I can park in the parking slot. So this is the entry sensor which is detecting the car which is going inside. Okay, so it is a counting. This sensor is counting the car which is going inside. Got it? Fine? Yeah. Then what is this set? Set is also one digital input. I will tell you after performed the counter function what influence the set is having in this counter. Fine. I'll just give one input address for the set. And what is PV? This is nothing but preset. So like in timer, we have some format to give a preset here. What is that format? C #3. That means up to 3 I want. 3 count I want. For example, in a car example, we can tell 3 cars can park inside. If the 4th car is entering, please let me know the signal. Or when the 3rd car is finished, let me know the signal. So C#3 is the limit I'm setting. If you want, you can set more than 3, 5, 6, 7, 8, more, whatever you want. According to the requirement, you can. Got it? And reset. So reset input is very important to the counter. What reset will do? Reset will make your accumulator value to go 0. Okay, so reset is a mandatory input to counter. Got it? And CV, the output of the time counters are three outputs are there. One is Q, CV, this is B, C, D. So these two are the accumulator values. Okay, and the Q is the counter output. Okay, I'll connect one output to the counter. I'll connect Q 0.0. Right? Got it? So what the counter will going to do now? So whenever I am going to turn on I 0.0, it will start counting. Fine? Right. So I'll do. See. It is in a run mode. So this is the input I have used, right? So I'm pressing. See, when I press that for the first time, it is counted 1. Correct? See, it is counting 1. Output is immediately on. Output is immediately on. In some cases, in some PLC softwares, after finishing your count only, after reached limit only, output will be on. Okay? Because I need a signal, no. At the end of the limit, I need a signal. That's what the counter is. Correct? But in Siemens, it will give the output immediately. If you are turning on, it will give the output. Okay, see. Next. Still it is on. One car is entered. So the sensor is going off. Now the second car is entered. See here, it is changed to 2. Now, the third car is entered. Fine. Third car is entered. Now, suppose if the fourth car is entering, it is taking the count. But I want this to stop. Okay, and moreover, at the third car end only, I want this signal. Because if that is the case, I can make use of the counter output to do something. For example, in the car example we can take, after the third car enter, I can put a display like parking is filled. Can I do like that? No. By using that signal, I can make parking is closed. I can do some announcement or I can display that. So how can I get that? Logic. So Siemens timer will be working like Siemens counter will be working like this only. What it is doing? At the first input itself, output is on, and moreover the accumulator is not stopped with 3. It is counting 4 and it is having a limit also. It is counting up to 999. Right? So what we can do for this? We'll do some logic for this. Okay. So let's see. So what is the purpose of reset? If I put the reset, accumulator value go back to 0. Let's see that. What is the reset input? I 0.2. I'm pressing that. See, accumulator value reached to 0. Because of that, your counter output is also off. So this is the purpose of reset. You can press the reset whenever you want. Suppose you want to reset the counter. Even the two cars entered already, but still you want to count from 0th car. What you will do? You can press the reset. Okay, so reset will make the accumulator value to 0. That is a function of reset. Now what I am going to do? Let's see the function of set. What is the role of set in a counter? Suppose, what is your preset value? 3. If I press the set input, that preset value 3 is moved to the accumulator. You want to see? See. Can you see here what happened? I have not pressed I 0.0. That means a car is not entered. There is no car. There is no detecting of car. So I 0.0 is not at all giving any signal. But if you want to make the accumulator value to the preset value, you can make use of the set option. See? Can you get the point? So that is the importance of set function in the counter. If you want to make use of it, you can. Else, No need. Got it? So I'm going to repeat. Whenever you are pressing I 0.0, it is started counting from 1, 2, 3. Correct? So how can I make use of the counter according to my requirement? What is my requirement? After counter reached 3, let me know. After that only I want the output. Okay, so that case you can make use of some logic so that your Q 0.0 will be turned on after the third count. What we can do? Preset value is 3. When the counter value reached 3, I want the signal to be turned on. What function we can use? We can make use of the comparators. Got it? What comparators will do? It will compare. It will compare the accumulator value to the preset value. Correct? So when the accumulator reached preset, it will give the signal. Got it? Let me do that. Yeah. See, you can make use of greater than you can use, or greater than or equal to I'll use. Fine. Both are same. You can use any comparators which will be checking whether it is reached or not, like that. Okay. So what I'll do? So it is comparing. So or we can take the greater than or equal to, which will be taking the 3 also. Okay. So what will happen? Even though it is crossed 3, my output need to be on. Like that. Fine. So I'll do. Here it should be 3. Correct. Because 3, what is 3? 3 is my preset value. But how can I take the accumulator value here? So this is the accumulator value. Here only I am getting the accumulator value. But how can I get this CV to be compared here? So for that, initially I need to store the CV in some registers. Correct? So I am using this register MW0, which is used to store the integer 16-bit. Correct? So I am going to use that here MW0. Got it? So I am going to use the comparators to make use of the counters as per my requirement. Got it? So that's what I am preferring, the comparator greater than or equal to. So let's go for the online. Let's check. So now see. Can you see? MW0 is 0. Why? Accumulator value is 0. Now see. I am going to, one car is entering. Okay. Can you check your output? It is not turned on as previously we have done. No. It's not happened like that. I have restricted this by putting a comparator. Got it? Okay. Second car is entering. See, this value is we are using here, right? So second car is also entered. When third car entered, it is giving the signal. See, third car already entered. So close the parking. You can make use of this anywhere. Got it? Right? So this is how you can make use of it. After that, how many cars will come? It will not. The closed is closed only. Got it? See? One more thing. You may ask me, see, how many times I am giving the signal? Now that time it will be counting. How can I stop the counter to stop counting? What we can do for that? Any idea? What we can use for? What we can put to stop the counter? What we can do? Think about it. We can do, or I want the counters to stop counting. So what I can do means I can restrict the path between the input and counter. Correct, na? I can do like that. Right? I can make use of the counter and input block. I can block the route. Correct. What I am telling means you can restrict, you can put some normally closed contact here which will be restricted by the counter, or function will be restricted by this input or anything. I'll just put one logic here. Let's check whether it is working. I'm just going to do one latching function. Nothing big I'm going to do. It's just latching function. I'm going to do latching here. We need to join. Let's see. No, it will not work. Here, I need to put a latching up to this. So that what will happen? Or you can use a second rung to do that. Correct? You can put a second rung to do that. What I can do, you know. Let's see here. Instead of I'm putting that in one memory. Okay. This is Q0.0. I'm saving that in one memory. Right? And that memory is latched here. This is one option only. Okay. So how to restrict the counter to count? Right? So I am putting it like this, and here I am putting M0.0. Let's check. Fine. Let's check whether the logic we have done is working or not. See, first car is entered. Just a minute. I'll keep the cursor here. Okay, first car is entered, second car is entered, third car is entered. Correct? Third car is entered. So, logic is on. Our output is announcing a parking is filled, like that. When the fourth car is tried to come, can you see? I have stopped my counter to counting. I have pressed the input for the fourth time, but this fellow is not counting. Why? Because means you have put a normally closed contact. Simple. Correct? Got it? So like this only we need to make use of the logic to restrict the counter from counting. If you want that also. If the counter is exceeding your limit but that's not your problem, means okay, no need of logic. But if you want to restrict the counter also, means you can make use of the normally closed contact put over here. So counter function is common, but according to the requirements you are in need, you can put the logic however you want. So I am putting one small logic by using a memories which will restrict the counter. Got it? Fine. So if you want to reset, if you press the reset, it will reset. Can you see? Fine. So next, again, if you want to run, you can make use of it. Click on the first rung to see the output. Yeah. 2, 3. Yes, it is started. Again, if you want to reset and start from the beginning. For example, if you press the reset first itself, see, accumulator value immediately reached 3 and all your output is on. After that, even though if you are putting input, it will not take because already accumulator value reached 3. Got it? So this is how you need to work with the up counter. Up counter will be start counting from 0, 1, 2, 3. It will start counting from down to up. Got it? So this is a up counter. When you want to make a count from the beginning, that is up counter. I can tell up counter is used in a car parking example. No, there you can put a up counter in the entry side. Okay. So if you want to count how many cars exiting in the exit side, you can put the counter over there. Up counter you can put. What they will do, it will count how many cars has exit. 1, 2, 3, 4, like that it will count. Okay, so if this is the working of counters. According to your requirement, you can make use of it. Fine. So in our next session, we'll see how to work with down counter. Got it? Until then, bye. Hello everyone. In today's session, we are going to see about down counters. Fine. So let's start. So in our previous session, we have seen the up counter, right? So what will be the down counter function? So it will be counting from up to down. Okay. So take the same car parking example. You are counting the number of cars which is coming inside. Okay, which is coming inside. I mean entry side, you are counting how many cars are inside. Okay, according to that you are putting parking is filled or parking is free, like that. Okay, so up when it reached 3, you are putting a parking is filled. Fine. So when you will be moved that parking is closed. Suppose instead of 3 cars were there inside, so that you have put the parking is closed. When 1 car is left or 1 car is leaving, there is a place for 1 car, no? So in that time parking is open, right? How can you get that 1 car is exited? So in that case, you can make use of the down counter in your exit place. Correct. First I will tell how to work with the down counter. After that, with that car example, we can see the up down counter. Fine. Because in that place, both the counters in the exit and entry place should have the same address. Okay. Let's see the working of down counter first. So I'm going to select the rung and I'm going to put the down counter. Same as up counter, it is having 4 inputs and 3 outputs. And here also it is asking the question mark. Correct. So I'm giving the counter address as C0. Right. I'm going to repeat the same thing whatever I have done for up counter. Okay. C#3. And reset value I'm putting like this. Fine. Can we check what will happen now? Yeah. So see, if I turn on the input, nothing is happening to the counter. See, it is not at all happening. Why? As I have already told, down counter will count up to down. Correct na? Down means what? Up may be some limit. Okay. Down means what? It is 0. Already my accumulator value is 0, no? From this down means there is no value for Siemens PLC. Siemens counter. That's what it is not responding to the input. See, I'm turning on. Nothing is happening to the counter. This is the reason. Down counter function is counting from up to down. Already 0 is the down. 0 is the last value, down value. Okay. Below this it cannot count. That's what it is not responding. Point number 1. Fine. So how to make this responding? I need to make the accumulator value to the limit. Correct na? So for that only we should use the set function. See, whenever I press the set, accumulator value reached to 3. Correct. Fine. So now what I need to do? If you count down now, it will start counting. See, 2. It is started counting down. See, when I press this for the 3rd time, output will also go to disable and accumulate. Because of that, accumulator value reached 0. Because of that only this fellow get off. Correct. So this is how we need to work with the down counter. So down counter will not respond automatically like this. Like up counter, it will not work. You need to press the set function first, because down counter should count from up to down. That's the main thing. See, now it will start counting. Correct na? That's the working of down counter. I'll do one thing. I'll explain up down counter in a same up and down counter in a different block. For example, see here. I'll just copy this. Copy and paste it here. Copy, paste. Okay, I'll delete the middle network. Now this is up, this is down counter. Okay, so what I'll do, I'll change this block to up counter. So since I'm going to use the same counter for the same function, I should put same address. Okay, so here I'm going to put some different set of function address. C#3 and reset should be same. Okay, or if you want to use different you can, but same if you prefer. Both will be turn off at the, both will get reset. Okay, so here I'm going to use that comparator function. Take the same that car example. Okay, car parking example. This is MW0. This is 3. Got it now, guys? So here I am putting some other output because output should not be in the multiple places, right? See? Fine. Now, what we can do? Let's go for online and check. So, this is the perfect example for the car parking. Okay? And one thing I have missed. What is that means? This is the entry side, no? I'll type here. This is the entry side. Okay, this is the exit side. So exit side also you should have some sensor to detect the car is exiting. So for that you should use a different input. It should not be the same I0.0. Okay, it should be the different input. I am just using one different input here. So this is the entry sensor. This is the exit sensor. Okay, this is the logic. So let's start the example from the beginning. Now your first car is entering and there is a parking slot and only 3 cars can park inside. Okay, got it? Now, one car is entering. One car is entering, that's what I pressed this. So when I pressed that, can you see this is also increasing, this is also increasing. Why down counter is responding to the I0.0? Because both the counters are sharing the same address. Why I have shared the same address? I will tell you why. Now one car is inside the parking slot. Correct na? Now, and that one car is leaving. While leaving means which sensor will detect? I0.4. So I am going to press I0.4. So when I press I0.4, that means 0 car is inside the parking slot. So accumulator value should go to 0. Let's check that. See, when I press the exit sensor, both are going to 0. Why? Because of that only. Both are responding to both sensors. Correct? Let's proceed with the example. One car is entering, second car is entering, third car is also entered. So parking is filled. Parking is closed. 3 cars are inside. There is no place to park the 4th car. Correct na? Now this is the parking is closed. This is parking is closed output. This may be a display or horn or something, whatever it is. Fine. Now let's see. One car is exiting. Correct. So now the parking is closed is automatically disabled. Now one car can enter. Correct na? See, accumulator value changed to 0. So one car can enter. That's the logic. When one car is entering, again it will go to parking is filled. So this is how you need to work with the up-down counters. If you are using up counter block separate, down counter block separate in your example means both should share the same address. If you are putting a different address, that will be a normal down counter function. If you want to interlink both counters function means you should use the same address. That is the point you need to note down here. Got it? Yeah. So now if I press the reset, what will happen? All will go to from the beginning. It will start from the beginning. Everything goes to 0. Got it? So this is how you need to work with the counters. What is pending? Up down counter. Let's work with up down counter. So now I am going to replace here with the up down counter. So what is here means both up and down counter function is present inside. Instead of using two different blocks, use the same block. That is what they are telling. Fine. This is going to perform the same thing whatever we have done just before. Fine. So I'll make the counter address. Yeah. So here see, it is having 5 inputs and 3 outputs. These 3 outputs are common that you can know, right? And see here, CU. This is for counter input, up input. This is the entry sensor. Count down. This is the exit sensor. I have put this one, right? I'll put the same address here. And for set, you will be using one address. And this is a preset value. Fine. And this is a reset. Got it? That's it. And here I should put MW0. So whatever we have done by using the two different blocks, the same thing is performed with the one block. Got it? So let's go for online and check. Yeah. Now car is entering. Fine. One car is leaving. Initially one car entered. No, after some time one car is leaving. What is counter down function? I 0.4. So see here. Yeah. So accumulated value goes to 0. That means 0 car is inside. 0 car is inside. Got it? This is the same thing whatever we have done before, right? By using two blocks, up and down counter separately with the same address. The same function is replaced by a single block. That's it. Now one car is entering. Second car is also entered. Third car is also entered. Second is entered. Now third one is entered. So parking is filled. Okay. Now one car is leaving. Parking is free. Again one car is entering. Parking is filled. One car is exiting. Second car is exiting. Third car is also exiting. Now parking is completely free. Right? Now I'll turn off this. See? You can do from this. Right? So this is how you need to work with the counters. Right? Now, suppose with this counter you want to work only with a down counter. So what you can do? You can make use of the set function. What the set function will do? See, if I turn on the set, accumulated value reached to 3. So now you can make use of the down counter entry. See, it is reducing. Got it? So if you want to perform only down counter with this block means you can use the set function. If you turn on a set, it will move the preset value to the accumulator value. Okay. After that you can use the down counter function separately. Got it? So this is how you need to work with the counters. Fine. Yeah. So that's it about the up down counters. Right. So we'll meet you all in the next session with these coil. How to work with these coil. Fine. So I hope you have understood the counter concept. So we have 3 counters. One is up counter, down counter and up down counter. We have 3 different blocks for all the 3 counters. So according to the requirement, you can find which counter you want to use. If you are using up down counter for the same function, you should use the same address. Fine. So we'll meet you all in the next session, guys. Until then, bye. Hello everyone. In today's session, we are going to see about the integer functions. So generally, what is the use of integer functions means we can make use of the integer parameters like addition, subtractions. We can use the integer parameter to do the functions like addition, subtraction, division, multiplication and mod function. Okay, so here you can get the instruction list. Can you see here we are having the integer function. In that subdivision we are having addition underscore I. What is that I means? It is an integer. Okay, so in Siemens, for double integer, for floating point number, for integer, we are having a different instruction block. Okay, for example, see here, this addition block is there and again another addition block is there. Fine. So this addition block is for integer and this addition block is for double integer. And we are also having another addition block which is specially for the real numbers, that is floating point number. We'll see that in the next session. Okay, floating point number, integer function will, floating point number, arithmetic function will see there. Okay, this is not common for all the PLC. In Allen Bradley, in some other PLC and all, there will be only one addition block. Fine. But here in Siemens, we are having a different block, different arithmetic block for different data types. Got it? So let's move on to the topic today. We'll do the integer functions for integer and double integer. Right. So what I'm going to do means first I'll take the addition block. I just connected one input and one output. In between I'm going to connect the addition block. So just look into it. What is the input to the addition block? There are two parameters. One is there are three inputs. Just a minute. I'll just remove this so that you get to know better. See here. When I took the block, it is having three inputs and two outputs. Fine. So the EN is the enable block, enable input. Fine. So for this we should give the bool data type. That may be any one of the digital parameter. I'm just connecting I0.0. Fine. So EN is the block enable input. That means it is like a rung condition. Fine. So another one, IN1. This is the input 1. And this is the input 2, integer. Right, IN1 is the integer 1 and IN2 is the integer 2. That means we are going to do the addition of these two parameters. Whatever you want to do the functions like arithmetic function, anything, you need to give to this IN1 and IN2. This IN1 and IN2 is common for all. Can you see here? If I take a subtraction block, here also IN1, IN2 is there. Because we need to do the subtraction between these two integers like that. Got it? So coming to the output side, it is having ENO, output enable. Fine. And one more output point is there. Here it will result the addition of two integers. Got it? Fine. So ENO is the block enable. Like for example, if this I0.0 is on, this the one which one you are going to connect here, that will also on. I'm just connecting one output here. Okay. So whenever I0.0 is on, Q0.0 will be in a on condition. Got it? So what I need to give here, I'm just giving 5 here. See, it is accepting. It is a constant number. No, it is accepting. And I'm just giving 4 here. I'll just go for online. It is asking one or more address are filled in or not filled in. What does that mean? Here it is a question mark. Here I need to give something. Since it is an input, I can fill with the constant number. But this one is the output. I should give some address or something. Right. So I'm just giving MW6. Any address you can give. I'm just giving MW6. Okay. Let's move on to the simulation part. Fine. So what will happen? This 5 and 4 will be added and stored in MW6. Got it? Now the addition block is not enabled. Why? Because the input condition is in a off condition. Correct? So let's turn on I0.0 first. Just a minute. It should be bit. Correct. So now I'm going to turn on I 0.0. See, when I give the input condition, the addition block get enabled and it's storing the value of 9 in MW6. Why it is 9? Because 5 plus 4 is 9. So if I disable, MW6 is retained with 9. Fine. Because once it is happened, right? The addition is once happened, so it is retaining it. See here, Q 0.0 is off because I 0.0 is in a off condition. Fine. So this is the constant, this 5 and 4 I have given before coming to the simulation. If you know the values are constant means you can go with this method. Or else, if the values are not constant, it will get vary. I want to give the number in runtime. That case, you can give the address. What address you need to give here? Since it is an integer block, you need to give the integer address. If you have any doubt in giving the address, just put a cursor near the question mark. It will give you what you want to give. What address you need to give. It is giving INT. I'll show you again. Can you see INT? INT. Correct. So that means I need to give both integer address here. So I'm giving MW0 and here I'm giving MW2. Why I have given MW2? Because MW0 will take MW1 also. One channel is having 8 bits, so integer will take 2 channels, 16 bit. Got it? So now we will go for the online. See, now MW0 and MW2 are 00. Correct na? Let's see. I'm turning on. Okay. In a previously somewhere we have used the MW0. Na? That time it was 100. We have not cleared that. That's what it is showing. 0 plus 100 is 100. Now I'm going to change the value of MW0. How to change the value? In a comparator we have seen, no, the same thing I'm going to do. Click on the small line, right click, modify. I'm going to give 89. So what is the answer now? 189. Got it? For example, if I turn off the input, now I am giving some random number. Now I am changing the value of MW. I am just giving 23. Okay. The addition was not happening. Why? Input condition is false. That's the reason. So if I enable the input condition, it will add both the values and will store that in MW6. Got it? Right? Okay, let me check whether the block need this is mandatory or not. What if I am not giving I 0.0? Let's check that. So it is not mandatory. So it is not mandatory in the terms like the addition block will work with the rung. The rung is connected with the rail, no? So it is taking that condition. Okay. So the problem with we are not putting the input condition. The problem with this type is the control is not in our hand. So addition will continuously do. For example, see, MW2 is the running number. It is coming from the field which is running, maybe. Okay. That time this one is continuously changing. Correct now? So if the control is in our hand, we can stop the performance of addition block. So that's what the important of input before the addition block. So see here, I have not given any input condition. So if the value is running, always it will do the addition. Suppose even though if the value is coming, I don't want to perform the addition means that time you can turn off your input condition. Here since I have not given any input, I need to do like this. So better always give a input so that a control should be in your hand. If you don't want to perform the addition function, you can turn off this. That's the important of input condition. Not only for addition block, generally I am telling for all the rungs you are writing, there should be some control in a programmer hand. Okay, fine. So this is how we need to work with the addition block. The same thing we are going to do with subtraction block. Let's do that. Here also we can give the constant numbers. Fine. So let's go for online. What it will do if I give, it will subtract 10 with 2. Okay, 2 from 10, in1 minus in2. Okay, that's what it is, 8. So let's check whether it is accepting negative number or not. Obviously it will accept. Okay, here I will give MW2 and output. Okay, fine, output let it be MW6. Now yeah, I'm turning on. So both the values are there, so it is subtracting. Now I'm going to change the value as 0. So what is the answer? Minus 23. Got it? Why it is minus 23? Because it is subtracting from the first number. Okay, so 0 minus 23. Same thing we have seen in a comparator also, right? First number only it will take for the first position. Okay, so 0 minus 23, like that only it will take. If I give this as 0, it will be 0. Got it? So this is how we need to work with the integer functions. I'll take multiplication. I'm going to give MW0, MW2, MW6. Let we perform another function also by putting another rung. Yeah, so instead of this I'm going to put division. Okay, so I'll give the same thing, MW0, MW2, and this is MW. This should be different. Output should be different, no? See, input you can give to both the blocks, that's fine. But here I have given MW6, so I should give a different address here. That's what I have given here. Same thing. This output is already used, so I need to give a different output here. Fine. Let's go for online. So 0, 0 multiplication 0, 0, 0 division is 0. Now I'll change 9. 9 into 0, 0. 9 by 0, 0. Now I'm going to change MW2 as 3. So there it will be 27. Here it will be 3. Okay. Got it? Yeah. So we'll go with double integer blocks. So what is the use of double integer blocks? So here you need to give, you can give the big numbers. Fine. So can you see, when I keep the cursor near the question mark, it is asking me d-int. That means you should give the double integer address. So I'll give MD0. Here it will be MD4. Why MD4? Because it will take 4 channels. This is MD8. Here I'll take subtraction double integer. I'm going to give the same number. Why I'm giving the same number means, instead of giving inputs differently, I'm going to give the inputs same. Got it? Let's run. Yeah. So already some values were there in MD0. So it is just doing the subtraction between them. Okay. Now here also obviously some values will be there. Same, you know, this one, this one. So it is doing the addition. It is doing the subtraction. I have not given this number, but previously when we were used this MD0, no, that time we have given this number. That's what it is taking. If you want to change this, you can. That's it. You can change like this. Okay. Yeah. So like that, you can perform the addition and subtractions. Okay. Yeah. If you want to see the output, click on the network one so that you can visit everything. You can see everything. Now, we'll do the division and multiplication. I'll put a division here. and I'll put a multiplication here. So same address I'm going to give. So here also MD0, MD4, here it should be MD12. Got it? So we'll perform. So as I have already told, we have a different blocks for the integer and double integer. So it will perform the multiplication function, it will perform the division function. Okay, I'll reduce this number size. I'll just give 2. See, it is multiplying and this is doing the division. Got it? So this output is enabled because en is on. So if I turn off that, the function performed, the answer was stored in the output side, no, MD8 and MD12, that retains same, but this block is disabled. So if you change now, nothing will happen. If you change now, it will not perform the function. Why? Because input condition is off. If you turn on the input condition, it will do the function. Got it? Yeah. So we have one more function which is pending, that is mod function. What is the use of mod function? Mod function will give the reminder value, right? So I'll give same we'll go for online. Okay, so for understanding, I'm just giving a small number. Okay, 100 I'll give, and here I'm going to give 3. So what is 100 by 3? What is the remainder we are having? 1, correct? Let's see. Can you see? Mod function will give the remainder value. Okay, so it is giving 1 as the answer here. So we'll change. We'll give 2. What is the remainder? 0. Correct. I'll give 5. I'll give 6 now. 4 is the remainder. Correct. 94 will be coming. 96 will be coming. So 4 is the remainder. Got it? So mod function we have in a double integer block. Okay. So this is how we need to work with the integer functions. So in the next session we will see how to do the arithmetic function for the floating point numbers and what are the remaining blocks we are having in a floating point instructions. Fine. So until then, bye. Hello everyone. In today's session we are going to see about the arithmetic function for the floating point numbers. Right. So as I have already told, we have a different block for doing the arithmetic functions for the floating point, and that instructions you can find in floating point here under this. Okay, floating point math. Okay, it's nothing but arithmetic blocks. Correct. So can you see here addition R, addition sub? What does this R mean? It is a real number. So that nothing but a floating point number. Correct. So in a previous session we have seen for integer and double integer. Here we are going to do the same thing, and that for real numbers. Okay. So let's see what is the difference. So here the similarities are it is also having a 3 inputs and 2 outputs. What is the address for the real block? We have seen in the comparators, right? It's same as double integer. Correct. MD. It's not a special address or not there. So it is MD only. So how I need to give the input, that is important over here. Can you see? I 0.0 is already in a on condition. I'm just turning off. Let it be on. So here let's change, modify. I'm just giving 8.9. I should give the floating point number, correct? So just see 8.9. Right? So this value is 0. I'm just changing again this to 8.9, right? So 1.1 I'll give. Can you see 8.9 is added with the 1.1 and it is showing the value of 10. Okay, I'll just give 1.2. or 1.5, something like that. Can you see? Now the value is 10.4. So here for the floating point numbers, you should give in point. Okay, so you should not miss the the decimal point we are putting, no, that floating point number, that is mandatory. Okay, so that's the difference between the double integer and this block. You should give the values like this, correct? So it will get added up with the 1.5 and it is showing the answer in MW8. Got it? Shall we do on for the subtraction block also? We'll do that. I'm going to copy this rung and paste it in. Yeah. We'll do division also. Okay. I'm going to change this with sub. Okay. This one I'll go for multiplication, subtraction, and this one gonna be the division. Okay. So for all I'm going to give the same number. Okay, fine. So here I'm going to give MD8, here MD12, here MD16. The address should be very particular because MD8 I am giving here means it will take 8, 9, 10, 11. 4 channels it will take. So for the next address I am using should be MD12. I should not use MD11 or MD10. That means both the outputs will get collapsed. Okay. So here also I have used 12 already. So 12, 13, 14, 15 is used by this address and 16 is the next available one. Got it? That's what I have given MD16 over there. Now I'll go for online. I'm turning on, right? So already we have given the value in the previous addition block, no? So let's see here. This is doing the multiplication of these two numbers and stored in MD8. This one is doing a subtraction. See, 876.89 minus 1.5. It is showing 875.39. Same thing it has done for division also. It is divided by 1.5 and the answer is 584.593. Got it? So wherever you want to feed the real number as an input and you may get a real number as an output. In that case, you should use the real blocks of Siemens. You may ask me, I cannot give the normal number here. You can give. See, I'm giving 90. I want to give 90. 90 is normally integer only, but since it is a floating point block, I can use like this, 90.0. Okay. So this is how you need to use the real blocks. Got it? So we have 5 more instructions are pending. That is absolute. What is the absolute? What is the absolute instruction? Will do any idea? So what is the definition they have given for this instruction? Absolute value of the floating point number. So what is the absolute means? It will remove the numbers which is after the decimal point. If you have given 91.09 means the absolute value of 91.09 is 91. What it is doing? It is removing the decimal part. Okay. So here also it is the input is asking in a real. Correct. So you should give the proper address. If you are not giving the proper address, it will raise the error. Yeah. So I'll just change this to 78.90. So the answer is, I'm extremely sorry. There is one small correction. Absolute value it's not the real, it's not, no, that is the truncate function. Okay, so I have done a mistake. So absolute value is removing the negative sign. If it is in a negative, if you are giving the negative input, it will give in the positive. Okay, so if you are giving the negative number, it will be changing that to positive. For example, see here, so the I have explained, you know, that negative integer part, it will, that is a truncate function, not an absolute function. I'm sorry, right? So what it will do, I'm just giving like this. Okay, so can you see, absolute value will be removing the negative sign from the input. Okay, so what if you are giving the positive, it will remains the same. See, it will remains the same, correct? So I confused with the truncate function. We are having trunk functions. I will explain you in our next upcoming sessions. Okay, so what is the truncate? So truncate means it will remove that decimal part. So absolute means whatever you are giving, it will consider the output as positive. Okay, so if you are giving a positive itself, it will take that, no issues. But if you are giving a negative number, it will take the, I'm just giving, it will take the positive. The negative signature, it will not bother. Fine, this is absolute. Absolute value of the floating point number is removing the negative sign from the, that means it is considering the negative number as positive number. That's it. Okay, yeah. The next one we are going to see is square root. Okay, so what is the purpose of square root? What it will do, square root of the particular number it will give, correct now? Let's go for online. These are all the math functions, right? So I'll give 100, 100.0. What is the square root of 100? It is 10, correct? So I'll just give one big number, 425.0. So it is 20.6155. It is absolute, the number. Even with the decimal point it is showing. It is the square root of 425. I'll go for 625. Okay, the values it is showing in the exponential. I'll give 1000. What will be the answer? Square root of 1000 is 31.6228. Correct? Yeah. So any other square root if you want to find, you can give. I'm just giving some random numbers only I'm giving. And if you want to get the perfect square, means you should give the perfect square here. The answer should be a perfect square, means you should give the correct number for this. Because since we are giving the random number, we are getting like this. Okay. I'm giving the random number. So it is giving the square root of the random number. Fine. So this is how you need to work with the square root block. Same thing, we are going to do the square. So let's do one thing. I'll take a square and I'll give this MD4 and we'll check whether we are getting the same thing whatever we are giving here. Okay, I'm storing that in different address. Fine. Here also I'm putting the input condition. Ready to run? Yeah. See, here I have done the square root. It is showing the answer and that the value I am giving here to square. So it is giving the whatever value we have given. I'll give 1000. So for 1000 what we got? Some 33 something, right? 31 something. Can you see here? And the same thing I'm giving here. It is showing here. Square root, square. Got it? So this is the use of square root and square functions. Next we are having is log and exponential. So here I am putting a log, natural log, okay, and here I am going to give the exponential value. Okay, let's go for run. Yeah, so here also see here we have already given MD0 as 1000. It is showing the logarithmic value of 1000, and I'm just giving the same thing as the exponential. It is giving the answer as 1000. I'll just give 10 log of 10 10.0. It is 2.3. correct. Fine. So I'll give log of 10. Log of 10 given now, log of 20 will give. So the answer should be 1.3. Oh, it is 2.9. Yeah. Fine. This is the natural logarithm. Okay. Natural log. So these are all the functions that, for example, in your requirement, you may need of such functions. You want to process some variables. You want to do some functions to you need to add some functions to the variables, means you can make use of these arithmetic blocks. Fine. So this is natural log and this is exponential function. Correct. So this is how you need to use the instructions in the Siemens. You should give the MD0 address. For example, if you are not giving a MD0 address, if instead of that you are just giving MW, so it will, there itself it will show the error. What error it is showing? Let's check that. I'm just giving here also. See, actual data type word does not fit the formal type real of the formal parameter. Correct. So MW means it may be an integer or word that is not fit for the real block. So you should not use like that, it is telling. Okay. So why these parameters, this log, exponential, square root all comes under the real block, means output will have a real numbers. Output will have the real point numbers. So floating point numbers. In that case, if you are using a integer block or double integer block, you will not get the perfect output. Okay. So what is the complete output you want, means what is the output even that is having a real numbers? I want to see the numbers which is after the decimal point. In that case, you should use the real instructions like floating point functions. Got it? So in our next session, we will see how to use the sine, cos, tan. Fine. So I hope you have understood the arithmetic blocks. So we'll see you all in our next session with sine, cos, tan. Got it? Yeah. Until then, bye. Hi everyone. In today's session, we are going to see about the remaining instructions in floating point functions. Correct? So what is the thing? Sine, cos, tan, same thing. A sine, A cos, A tan. Correct? So let's see about the sine first. So what we will be doing with the sine? It will be the trigonometry function. Correct? Fine. So let me give sine 30. Let's see what will be the answer. What should be our answer? Sine 30 is, what is the answer? 0.5. Correct? Let's check that. See, I am giving sine 30. 30.0 I am giving. Okay. So what is the answer it is giving? It is giving some random answer which is not right. Correct. So while using the trigonometry function in Siemens, the blocks we are having for trigonometry should accept only the radian value. Okay. So I cannot give the degree value straightly to the sine block. It will accept only radian value. Okay. So to find the radian value, I need to make use of the formulas. Got it? What is the formula to find the radian? Pi by 180 into degree. Radian is equal to pi by 180 into degree I will be using. So what I need to do? I need to use a pi by 180. First I need to do the division. Correct? Then pi by 180 into degree. That means that is a multiplication. Correct? Right? After that, the answer of pi by 180 into degree is the radian, and that is the one I need to give to the sign block. Can you understand what I am doing? Right? I cannot give the radian value directly to the sign instruction I am having here. So now I need to use the formula. What is the formula for radian? Pi by 180 into degree. Pi by 180, that is a division. Pi by 180. Pi is, what is the value of pi? 3.14. Correct now? I am giving 3.14 here. And what is 180? It's nothing but 180.0 I am giving. Okay. And I am storing pi by 180 in one address. Let it be MD0. I am storing here. And that MD0 is multiplied with your degree. Whatever degree you are giving, that is the one. So I am giving that in one address. Got it? And this multiplication value I am getting, no, that is the radian. Got it? And that radian, if I give to my sign block, see, I am giving the same address. I will be getting the answer. Let's check now what is sin 30. See, this is the one where I need to give the degree. Correct now? So I am giving 30.0. Can you see the output of sine MD12? What is sine 30? It is 0.5. Correct now? I'll give 90 here. What is sine 90? It is 1. Okay. So this is how you need to make use of the trigonometrical function in Siemens. In some other PLC, you may have a block for radian to degree, degree to radian. Like that you are having a block. But in Siemens, we are not having that. So you need to use the formula method. Correct. So for pi by 180, you can make use of the division block. And for multiplication, you can make use of the multiplication block. And that too from the floating point functions. Floating point arithmetic functions. At last, I am going to do the sine function here. Okay. This is common for all the three functions. Cos also same. Tan also same. Got it? So let's do this A sine. What we need to do for A sine? So if I give 0.5, it should give 30 degree as the output. Correct now? So here how can I make use of the formula? What will be the formula now? 180 by pi into radian value. Correct now? Correct. So what I need to give now? Here I am going to give the A sine block. Why I am giving A sine block here? 180 by pi into radian is your degree. How to get the radian value? You will be giving over here. Correct? Let's see that. This is 180. Correct? This is 180.0. And this is 3.14. Correct? And here you need to give the radian value. It will give the radian value. Here you need to give the 0.5. For example, if you want 90 as answer, you should give 1 here. Okay. So I am giving this MD12. Okay. This is where you are getting the answer. No. So I am giving MD12 here. And I am storing that in one different number. Let it be MD16. Okay. And now I am going to multiple this MD0 and here I have already used MD0. So I will do one thing. I will choose MD20. I am storing in MD20 and MD20 into MD16 I am going to do. Okay, I am going to see the answer in MD24. Okay. So just opposite I am doing. Sine block will give the degree value. By using A sine block, I can able to get the degree value. Okay. For that also we need to use the division and multiplication block. Got it? See here, this sin 90 is 1. Now for 1 I am giving, I should give the 90 as the degree. So whatever I have given here, see? Correct na? So I'll do one thing, I'll change this to 30 degree. 30. What is the answer? 0.5. If I give 0.5 here, both will get multiple and I get 30. Correct? So this is how you need to work with the trigonometry functions in Siemens. This is common for all the remaining cos and tan. What I need to do? Note down the address here, or I'll just copy the address and I will delete that. I'll give A cos here. Okay. For A cos it should be MD12. This is MD16. Okay. Now I'm going to delete this block. Same thing I need to copy here. What address I have used already? MD8 and MD12. Okay. MD8, MD12. Okay, I'm going to delete this. Let's run. Okay. Got it? So cos 30, you are getting value, and that is you are getting the 30. Fine. So let's see what is cos 0. I'm giving 0.0. It is 1. Correct na? Cos 0 is 1. Okay. Here you will be getting the 0. This is degree. This is your cos 30. Got it? So this is how you need to use the functions. Same thing I'm going to do for the tan. Here I'm going to give tan. What is this? MD8 and that is MD12. Correct now? I'll delete the block. I'll delete the block. Yeah, this block I'm going to delete. So here what I need to use? A tan. Okay. So here it will be MD12. This is MD16. Correct now? MD16. I'll delete the block. Okay, this is, I'm repeating, I just explained the only one thing and I'm repeating the same thing for all the blocks. Okay, here tan 0 is 0, 0 is 0. So I'll give tan 30. What is the answer? We are having 0.576. If you are giving the same thing here, it is giving the 30. Correct? So I'll go for tan 90. It is showing some random value. Okay. I'll give tan 45. It is 1. Correct na? Fine. Got it? So that's it. The sin cos tan you need to use with division and multiplication block in Siemens, since we are not having the conversions like radian to degree, degree to radian. If you are having that, there is no need of the formula usage. Okay. If you are not having the conversion block, you should use the formula type. And formula you can perform with your division and multiplication block. Okay. So this is how you need to work with the floating point instructions. We will meet you all in the next session with another interesting topic. Until then, bye. Hello everyone. In today's session, we are going to see about converters. So let's move on to the session. So converters are used to change the number from one form to another, right? So can you see here, we are having a different type of converters. Like it is starting with BCD to integer, then integer to BCD, then integer to double integer, BCD to double integer, and double integer to BCD. And we are also having double integer to the real number. Fine. So generally BCD to integer, right? So we are going to convert the binary values to the integer. So let's see one by one. I'm going to take first BCD to integer. So I'm taking this block. So if you want to See this block, just have a look. So it is having one inlet and one outlet. Totally two are there, correct? So in this inlet, we are going to give the BCD value. Fine. So in the outlet, we are going to get the integer value. So this is how it will convert from BCD to integer. So what address we need to give here? Since it is a 16-bit, correct? So see, whenever you are putting a cursor near the question mark, it is giving in colon word. That means we should give the proper address, right? So I'm going to give the 16-bit address MW0. And for out also it is 16-bit, correct? So integer. So I'm sure I'm going to give MW2. Fine. So what is this I0.0 is? It's an input condition. Fine. The control should be in the user hand. That's what I am using this. So this is not mandatory, but if you are using, the control should be in your hand. After you have pressed this I0.0, then only the conversion will be happening, right? And that EN, this is also one of the inlet, correct? So two inputs and two outputs for this block. So EN is nothing but a block input. So you need to connect this I0.0 to EN, and ENO is the output enable. So Q0.0. I'm just connecting with the output, right? So I'm going for the online. Now, for the previous, in the previous session, for the comparators and arithmetic function, we will be giving the values by changing here, correct na? So we will be giving the values by right clicking, modify, correct? So suppose if I want to give the variable, see, it will not accept the binary values here. Okay. So previously for the comparators and arithmetic function and all, we have given the values straightly in this option. But since it is a BCD, I cannot give in this place. So where I can give means there is one option to give the binary values, and that is called as variable table, right? So where is the variable table option is? Go to PLC. Under that, can you find monitor modify variables, right? So this is the option you need to pick. Just pick. Okay. So here the variable table window open, correct? So first, the first one, it is asking the address, symbol, display, and the next column is display format. Next column is status value, and the last one is modify value. So instead of giving the input and seeing the output here, we are going to use this variable table to see the input and output. Fine. Got it? So what I'm going to do, what is my input? That is my MW0. Correct? So symbol, it's not mandatory, no need to give, and display format. So what is the data type of MW0 now I'm going to give? It is a binary. So when you are right clicking, can you see? Just click on the box and click right click, right? So can you see various formats are there? Now I'm going to give the format in binary. MW0 I'm going to give in binary. So I'm choosing that binary. Got it? Right? Fine. So don't go with the status value and modify value now. Just move on to the second row. In the second row, what is my next input? What is the next thing I need to monitor? That is my output. Correct? What is my output address? MW2. And what is the display format you want? I'm going to convert binary value to the integer value. So I should choose decimal here, so that I can able to view the answer in integer. Correct? So like this, I need to write the input and output address and the format, in which format I want to see. Actually, why we are coming to the variable table? I couldn't able to see the input and output in the needed form. That's what I'm coming to the variable table. Correct? So I should choose the format according to my requirement. Fine. So now this place, modify value. So here, this is the place where you want to give the input. For example, I want to give input like this. For example, I want to convert a binary value of 1 and I want to see that in an integer. Right? So I'm just giving 0001. So it will be taking, MW0 is nothing but a 16-bit address. So it will be taking the input as a 16-bit. Can you see, I just given the 4-bit only. Just click, there is one option called monitor variable. When you click on monitor variable, automatically the value is taken here. Don't confuse about the status value, okay? Don't see the status value now. Just to see the monitor value. This is the input I have given. I have given 0001. So automatically it is taking the remaining values as 0. See, all the 16 bits are filled now. The last is the one I have given. The remaining is filled by system. And this one is monitor modify variable. This is modify variable. This is the option which will be updating whatever you are giving here. See, after I pressed this value is shifted to status value. Correct? So MW0 I have given. See, MW2, what should be the answer of MW2? That is 1. Correct now? So BCD value I have given in a binary form as 1. Output should be 1. But here it is showing something. Y means I have not turned on the input. I have given the input condition here, right? I 0.0. After this only the conversion will be happening. This is what I have told you. Control is in user hand. Okay, the conversion will not happen until user pressed. Okay, fine. So now what I am going to do? I am going to press this I 0.0. Right. So when I press that I 0.0, BCD to integer conversion is happened and it's updated the value of 1 here. Right. So let's do one thing. Again I'm going to change the modify value. So again I'm giving another 1 here. So answer should be 11. How to update the variable table? Just click on modify variable. See, after I clicked, it is updated to 11 now. Correct? So again I'm changing here. Let's make it as 2. So answer, what is the answer now? Let me update this. Yeah, what is the answer? 211. Fine. So in a BCD format, right, in Siemens PLC, so up to 999 it will be doing the conversion. What is the maximum value you can give in this modify value is 999. Okay, that means I'll show you here 1001, right? 1001. 1001. So this is 9, right? 999. So this is the maximum value it can convert. Got it? So what actually it means? It will be taking the first 12 bits for conversion. And the first 12 bits, right? That should be the maximum value of 9 each. So up to 999 only you can convert in the BCD to integer conversion. So what is this remaining 4 bits? It will not bother about the remaining 4 bits for the conversion, but it will bother about the 16th bit. If the 16th bit is 0, the value you have given is positive. Fine. If the 16th bit is 1, then the value is negative. Shall we update this? See, now I have updated, now I have given 16th bit as 1. Now update, can you see? It's minus 999. Correct? Why? Because for the 16th bit I have given 1. So let's change that. I'm changing the 16th bit to 0 again. Again see, since it is 0, it is taking that as positive value. Got it? So what I have done, I have taken the BCD to integer format. Fine, that is 16-bit. Integer means 16-bit, right? So I have given MW0 and MW2. I cannot able to see the output and input properly here. So I'm going for the option PLC monitor modify variable. Okay, so it will take us to the variable table. So here is the one I need to give the address of input and output and the format I want to see. See, can you see here? This is binary I have given so that I can see the values in binary. This is the decimal I have given, so I am seeing that in a decimal. Suppose, see here, if I change the value this to binary, it will be showing the answer in binary. Okay, so you should use the decimal to see the value in the proper format. Whatever after the conversion, how you want to see, that is listed here, right? So this is the one. And how about this bit? This is 16, 15, okay, totally 15 bit, 15, no, 0 to 15. So this is 15, 14, 13, 12. Okay, so the last 4 bits it will not bother, but the 15th bit it will be taking it as sign bit. For example, this bit is changing. In between this bit is changing means it will not at all bother. Okay, so these 3 bits are not at all bother, but the last bit is mentioned as a sign bit. Got it? Now again I want to show you one thing. Suppose if your value is exceeded 999. For example, see, I have given 999 here, no? So suppose I am changing the value more than 9. Okay, this is 10, right? A. Correct. So if I update, see, it is not updated anything, but your PLC is stopped. Your PLC is stopped. So this is what happens if you give more value. I mean, if it is beyond the limit, the PLC will stop. Okay, so the maximum value you can convert in BCD to integer is 999 only. Right? So this is how you need to use the BCD to integer format. Right? So in our next session, we will see the remaining converters. Fine. So until then, bye. Hello everyone. In today's session, we are going to see about the converters. So in the previous session also, we started with the converter introduction. So we have seen this BCD to integer converter, right? So today we will start with integer to BCD. So it is just opposite to the BCD to integer. So here input should be integer and the output will be coming in the BCD format. So let's check that. So the block looks exactly like BCD to integer, right? It is having 2 inputs and 2 outputs. The first input is EN, which is the input condition to the block. And ENO is the output, which is output to the Q0.0. It is like when the block is in on condition, this ENO will be on, right? So next, in and out. So in is the place where you need to give the input value. And out is the place where we will be getting the output, and we need to give the address. Since it is a 16-bit block, how to identify whether it is a 16-bit or 32-bit means here they have mentioned as integer. So integer to BCD means we need to convert 16-bit integer to the 16-bit binary value, right? So I'm going to give the integer address, which is nothing but MW0. You can give anything, but since I'm starting with the MW0 and MW2 like that. So the next address is MW2, right? So I'm going online. So in the previous session itself, I have introduced about the variable table to you, right? So variable table I'm taking. So what is the MW0 now? Now that is a decimal. That is an integer. So I'm changing the format, and the next one we are having here is the binary value, right? So now I'm going to give any integer. Let's take 211 or let's take 11, right? Same thing, modify variable. Now it is 11. I'm going to turn on my input condition. So when I turn on the input condition, can you see here 11 integer is converted to the binary value, right? So see here I have given the display format as decimal and binary, and status value is 11 because I have given the input as 11, right? And that value is converted into the BCD format, binary format, that is in a 16-bit. Correct? So now I am just changing the value to 111. I'll change 111. Right? Now I am going to update. So after I updated this, can you see here 1, 1, 1, that's what it is 111. Right. So as I have already told, last bit is the sign bit. Correct. So since I have given positive, I have not given anything, so it is taking this number as a positive number. So that's what the 16th bit is filled with 0. Suppose if I give minus 111, I'll give minus 111. Let's watch this 16th bit after I updated. Can you see now? All the last 4 bits are changed to 1. Okay. So this is how integer to BCD will be working. So when you are giving the minus sign, last 4 bit will be changed to 1. Fine. So if I'm removing that negative, let's see what is happening. So the number is changed to just 11, 11. 1, 1, 11 it is. Correct. So here also the maximum value is 999. Okay. The maximum value you can give here is 999. If you are giving more than that, it will be stopped. The PLC will get stop mode. The PLC will go to stop mode. Got it? So this is the way to use the BCD to integer and integer to BCD. Right? So let's move on to the next block, which is integer to double integer. So integer to double integer. So what I'm going to do, integer means what is the address we can give. So what it will do, it will be changing from 16 bit to 32 bit. Okay, so integer means it will be taking 16 bit. Double integer means it will be taking 32 bit. Okay, so I'll do, for the integer I'm going to give MW0. Right. So for the integer, we need to give the MW0 address. But the answer we are having here is in a double integer. Can you, if you put a cursor near the question mark, it is giving d-int. That means what? It is a double integer. So address I need to give here should be MD, starting with the MD. I am giving MD4. Right? So this is integer address and this is double integer address. Let's go for online. So let's go for online. So I'm going to use the same variable table to watch the output. So first I have given MW0. The next one is MD0. Right? So here what I'm going to do, I'm going to see both the address in the binary form. Okay? I'm going to see both the addresses in a binary form. So let's watch here. I'm going to give just one here. Okay. One mistake I have given. What is that? See, I have given again MD0. So the address is MD4, right? So I should give the proper address to see the exact output, right? Yes. So I have turned on, the input is already turned on. Now see, I have given the 16-bit data, but that is shifted to the double integers. Okay, that is shifted to 32-bit. Can you see here? I have given just a 16-bit, but the output is in 32-bit form because I have given MD4. Right, and I have used the block integer to double integer. Right, so this is how you need to use the integer to double integer block, and we are having BCD to double integer block. Okay, let's see that BCD to double integer. So what it will be doing? We will be giving the binary values in 32-bit. That values are converted into double integer format. Right. So BCD in 32-bit. So here in question mark it is giving D word. That means I should use MD address. Correct. And obviously for the double integer we will be using the double integer address. Right. So I am giving MD4. Let's go for online. See, I am repeating the same steps with a different block, right? So, yeah. So, let's see this. I'm going to give MD0 and that is MD4. Fine. First, I'll give just 0 here. Yeah. So, I have given just 0 and here also it is 0. Okay. Now, already it is in on condition. I'm going a variable table. Now, I'm going to give BCD value in 32-bit. Fine. So, let's give some random values. I'm giving 1, 1, 1. Go for modify variable which is updating. Okay. Okay. So, here what I need to do? I need to change the format to decimal. Correct now? Because I'm going to see from BCD to double integer. Correct. So, here I need to change that to decimal. Yes. So, once I have changed to decimal, can you see 111? 111 is the answer. Correct. That's what I'm seeing here. Right. So, as we have seen in 16-bit, the maximum value was 999. Correct. So, here also the maximum value is 999. It will be 999, 999. So, as usual, the last bit is the sign bit. I am giving the last bit as 1. So, the value is shifted to minus 111. Right. So, the maximum value I can give here is 9. For each and every 4 bit, the maximum value you can give here is 9. Right. So, if you are giving more than that, the PLC will move on to the stop mode. That we need to understand. There is some limit for the BCD for blocks, and that is 999 for the integer, and for double integer means for 32-bit means it will be 999. Got it? So fine. This is how we need to use the BCD to double integer, and we are having one more block which is double integer to BCD, which is just opposite to whatever we have done now. Correct? So I'll take this block, double integer to BCD. So here as usual same address, MD4. I'm going online. Right. So let's go for the variable table. Now this is moving to decimal and this is moving to binary. Correct? Right. So whatever value we have given, yes. So it is coming in this format. Let's see. I'll just give minus 11111. Yeah. Yeah. Can you see here minus 11111? Since I have given the minus, the last 4 bits are changed to 111. As we have we have seen in the 16-bit, same thing is happening. So 111111. So here also the maximum value you can give here is 999. Last 4 bit is considered for the sign. Fine. So that's it about the double integer to BCD format. So converters are common in all the PLC. You can find the converters in all the PLC softwares. Okay, but the instruction usage will get differ here and there. But the concept is same. Right. So we have one more block for this session, and that block is double integer to floating point number. Okay. So let's see what it is doing. So for double integer and floating point, the addressing format is same, right? Because both are 16-bit numbers. 32-bit numbers. Correct. So I'll go for online. Right. So let's see here. This should be decimal and this should be floating point. Here see, we have floating point option also to see the display format. Right. So what it will do, whatever value you have give, it will add the 0.0. Okay. So if you are giving 10, it will make 10.0. If you are giving 100, 100.0. If you are giving 208, it will be taking 208.0. Like that it will be updating. For example, see here I am giving 208. Okay, 208 I am giving. Okay. So if you are updating, can you see here? It is taking at 208.0. Right? Okay. So why we are having such conversion means some blocks will accept only floating point number. Okay. So in that case, you are having a double integer value. But how to give that double integer value to the floating point block? You can use such conversion to do the conversion function. After that, you can give this to the floating point block. Got it? So yes, so we have seen today integer to BCD, integer to double integer, BCD to double integer to BCD, and double integer to the floating point number. Right? So in our next session, we will see about the ones complement and twos complement session. Right? So until then, bye. Hello everyone. In today's session, we are going to see about the converters part 3. Right? So in the previous session, we have seen all these converters, and today we are going to start with this one. What is that? INV_I. That is nothing but ones complement. Right? So ones complement for the integer. Can you see the name here? Ones complement integer. Right? So what it will be doing? So if you are giving the binary value as 0, 0, 0, 0, it will convert that to 1. If you are giving 1, it will take that to 0. Like that, it will complement the input and put the value in the output. Right? So since it is an integer block, I am going to use the address called MW0 and here MW2. Fine. So let's go for online. I am going online. Right? So already my input is in on condition. I'm just turning off for the time being. Now to see the output properly in the binary format, I'm going to use the variable table. And how to open the variable table and all we have already discussed. So this is my variable table. Here I'm going to give MW0. Right? And another value MW2. Now I want to see both the input and output in binary form. So I'm taking this as binary. Right? So if you want, you just expand and see the display format, full name of that. Right? So right. So here I'm going to give the value. Let's give 0, 0, 0. Like I have already told, right? Fine. So it is taking completely 0. When you go for online monitor update, so it is converted. So I'm just giving the input condition also. Right? So the value was already inside. That's what the output came immediately, even though if I have not pressed this. Okay. Now let's see. I'm just going to change. Now I'll just turn off this. Now I'm going to change. It will not update. I'm making the last 4 digits as 111. So it's not updating. See here, it's not updated. But your question is updated. I mean, your input is updated, but output is not updated because your input condition is not turned on. If you turned on, it will be updated. See, I have given all the remaining bits are 0 and the first 4 bit as 1. So the first 4 bit are changed to 0 and the remaining bits are changed to 1. Got it? So this is ones complement for the integer. Correct? So same way we are having for double integer also. Let's see that. I'm going to turn off the input condition. So double integer block is nothing but the next one. This one. INV_DI. Ones complement double integer. Let's take this block. So nothing difference. It will be showing the answer in 32-bit. That's it. Let's go for online. Yes. So I need to change here, right? MD0, MD4. Remaining and all is same. Correct. So now let's do one thing. Let it be the same value. Okay. Let it be the same value. I'm going to turn on my input condition. Yes. So can you see here? Everything is changed. Right? So the last bit is the sign bit. Correct. I have given 0 here. So it is changed to 1. Fine now. Suppose if you want to see the value in the decimal, can you see the negative sign here? Correct. Because here I have given negative. I mean it is a positive number. But when it is doing the ones complement, the number is changed to the negative number. Why? Because the 16th bit is, I mean the 31st bit. I mean if you are calculating from 0 to 31st, the last bit is 1. 1 means that is a negative, sign of negative. Correct. So that's the thing. That's what the last number is. 1 means if you see the same number in the decimal format, it will be giving the negative value. Correct. So this is how ones complement will be working. Right. So we have one more format over here, that is one more instructions we are having, that is negative neg underscore 1. This is nothing but 2's complement. Right. Let's see that. 2's complement means what? 1's complement plus 1. Correct. And this is for the integer. So I am using this address MW0, MW2. Right. So let's do one thing. In the same network, or no need of another separate network, I'll delete this. I'm going to connect one branch and I'm going to take the 2's complement block also. So for the 2's complement block, I'll use this address MD4, MD8. Different address I'm using. Right. I'm going for online. Right. So in the variable table, I need to add, this is MW0, MW2, MD4, MD8. Correct now? So here MW0 and MW4 are your input. Fine. So I'm changing everything to binary format. So it is not that you need to use the variable table for only one block. Whatever address you want to mention in the variable table, you can. Right. So this is one's complement I have given. Let's see. I'm going to give the same thing over here. Right. That is in a 32-bit format. So I'm updating. Let's turn on my input condition. So yes. So this is the ones complement of this number. This is the answer of one's complement, 2's complement of the number. One's complement means it will just complement one time. 2's complement means one's complement plus 1. It will be adding 1 to the one's complement answer. Correct. So this is for integer and this is for double integer 2's complement. So one's complement instruction will be starting with INV. 2's complement is NEG. Okay, don't confuse with this is a negate function, not like that. They have given the name for the 2's complement as NEG. Got it? Shall we move on to the next one? Yes. So then what is this? Negate real number. What it will be doing? Let's see that. So we are going to perform the negate real number block. So everything looks same, right? NEG I is for 2's complement, this is for integer, 2's complement for double integer, and this is different, negate real number. So let's see that. Can you see the input format we need to give is the real. So I'm giving MD0 and here MD4. I'm going online. Right. Yes. So I'm going here. I think here we can give the answer. I mean input here itself. I'm giving 8.9. What is the answer? It is minus 8.9. So if you are giving the positive number, it is changing that to the negative number. Let's see what it will do if I give the negative number. Minus 8.9 I will give. It is changing that to positive. Correct. So if you want to change the sign of the real number, positive number to the negative number means you can use the block. Same, negative number to positive number means you can use the same block. So plus means positive, negative it will give the answer. Negative means positive. In the positive manner it will give the answer. Right? So that's what negate. Plus means negative, negative means plus. Positive. So this is the negate real number, and obviously you need to give the real number here. I mean floating point number here. You should give the floating point number. Fine. So yes, this is negate real number, and we have 4 more instruction which is very important. Right? So round. Right? So what is the round function means? Round, and all the 4 blocks are working with floating point numbers. Right? So for round, input is floating point, output is d-int. Okay? So round off means what? It will be eliminating the floating point number. Correct? Na? So output should not be the real value again. It should be the double integer. So I am giving MD0. Here MD4 I am giving. Okay? MD4. So let's see what is the working of this. Yeah. So minus 8.9 I have given. So if you want to see proper output, go to variable table and check over here. Let's delete everything. This is MD0 and this is MD4. Correct now? So the first one is the floating point number and the second one is the decimal. Correct? So right. So here I will give minus. No need of minus. If you want you can give, but still I am not giving minus. I will give 100.6. Okay. What is the output here? What is the output here? 100.6 means it is taking 100.101. Okay. So if I give 100.4, what it is taking? 100. Okay. So below 5 means it is taking the lower integer. Okay. If after 5, above 5 means it is taking the higher integer. So let's see what will happen if I give the exact 5. It will take the lower value. Okay. So let's check with 100.59. It is taking higher value because it is almost nearer to 100.6, right? So it is taking the higher value. So round off means once it will take to the below integer or above integer, depends upon the value after the decimal. Okay. So I'll give 100.49. It will be taking 100 because it is almost nearer to 100.5. Okay. So this is how round instruction will be working. If it is above 5, it will go to the higher integer. It is below 5, it is go to the nearest to lower integer. Right? So this is round instruction. Fine. Let's see what is the function of next instruction, which is called as trunc. Trunc double integer part. So here also the input is real, output is d-int. I'm going to give the same address. So let's see what it is doing. What is the difference between this trunc and round? Let's see that. I think in one of the previous session I have explained about the trunc to you when I was explaining the absolute block. I remember that. So let's see here. 100.49 I have given, but answer is 100. Okay. Suppose if I change 100.99 I'll give, which is almost nearer to 101. Correct. Now see, still the answer is 100. Okay. So what it is doing means it is abruptly cutting the floating point number. I mean the number which is after the decimal point is abruptly cut. Okay, that is trunc. It will take only that double integer value or integer value. Right? How maybe it is very nearer to 101, but it is not taking 101. It is taking 100. Okay, it will truncate the double integer part. That's what the trunc function will be doing. I will see with one more example. 89.90 I have given, but the answer is 89. Right? So trunc is truncating the double integer part. Fine. So this is the working of trunc function. So let's see the next one. Sealing. So here also my contact is, input is MD0, here MD4. So let's see what is sealing. I am giving 89.9. It is taking 90. Okay. It is taking 90. What if I give 89.4 or 89.3, which is nearer to 89, right? Yes. Still it is taking 90. Okay. If I give 89.01, let's see what it is doing. Which is very nearer to 89, correct? But still it is taking the 90. So sealing means always it will take the number towards infinity. I mean, it will take the higher value. Like sealing means higher, right? Sealing, how we are, is a normal general word, right? In dictionary. Sealing means like higher. So always it will take the nearest highest integer. Which is the nearest higher integer, 89 or 90? 90, right? If it is 89.01, what is the nearest highest integer? Means that is 90. Comparing to 89 or 90, 90 is the highest. So it is taking 90 instead of 89. Right? That is what sealing is. Fine? So this is not a round function, not truncate function. This is a sealing function which is taking the highest integer. Right? So I'll go with one more example here. 2.01. What it is taking? 3. Got it? So yes. So let's see about floor. So here also MD0, MD4. So sealing and floor are just opposite to each other. Sealing will take the highest, right? Floor will take the lowest. Okay. Let's see that. Okay, fine. So I have given 2.01 already. What it is taking now? 2. I have given 2.01. What is the nearest to lowest integer here? 2 or 3? 2. Correct. So that's what it is taking 2. I'll go with 8.99. It is taking 8. Correct. Floor. So you may ask me, then what is the difference between trunk and floor? Because both are same, no? Whatever value you are giving here, trunk will also do the same thing. Then what is the difference between trunk and this one? Floor. You should know. So floor means it will floor towards the negative infinity. Okay. So trunk means whatever you are giving, it will be cut down the decimal part. It will take only the double integer part or integer part. Okay, that is trunk. But floor will, the answer looks same for the positive number. For example, see, I am going to give the negative number. Let's see, I am giving minus 9.8. Okay, so what do you think? What will be the answer? It is minus 9. Let's see. What is the answer? Minus 10. Why? Because it is flowing towards the negative infinity. If the same value I have given to trunk, it will be giving the minus 9 answer. Let's see that. Let's do that also. Okay. So I'll do one thing. I'm going to take trunk function here. This is what the difference you should know. It may look same, but both the functions are not same. So I'm giving the same input, but I'm saving the answer in MD8. Right? Let's go for online. If you are giving the positive value to both the instruction, it looks same. But to see the difference, you should understand the concept. Yeah. See here, can you see the difference? I am giving minus 9.8 as a input. Floor is taking minus 10, but trunk is giving minus 9. So as usual, no, trunk will cut down the decimal part and it will take only the integer or double integer part. So it is taking minus 9. But floor will take the value towards the negative infinity. Negative infinity towards means nearest is minus 10. That's what it is taking. Suppose if I have given plus 9.8. 9.8. Okay, I'll give both, anything. So what is the answer? 9. It is also 9. Correct, na? So for positive number, you cannot find the difference. For the negative number only, you can find the difference. So yes, so we have covered all the converter instructions. Right? So let's move on to the next interesting instructions in the next session. So until then, bye. Hello everyone. In today's session, we are going to see about shift and rotate instructions. Okay, so let's move on to the session. So you can find the instructions from this place. There is a title called shift and rotate. So in that we are having shift right. If you click on that, you can get the name here. Shift right integer. Then shift right double integer. Then shift left word. Shift right word. Shift left double word. Shift right double word. Got it? So here we are not having shift left integer. So here there is no instruction like shift left integer, because if we are doing the shifting towards the left side, then it will change the sign of the value. Maybe it may change the negative value to the plus and plus value to the negative. Right? So that's why there is no instruction like shift left integer. Right? So what the shifting will be doing? So if we are doing the shifting, right? So for example, you are having a 16-bit binary value and we are going to do the shifting. You should tell how many places you want to shift. For example, you may tell 1 place, 2 place, 3, 4, like that. You can give the number, right? So after that, when the input condition becomes true, it will be shifting the values towards the right. Okay, so let's see the instruction in detail. So when I'm taking the instruction, it is having 3 inputs and 2 outputs. So what are the 3 inputs we are having? One is enable and one output ENO. This is common for all the blocks in Siemens, right? This is a run condition. Whenever the run condition goes true, this Q0.0 will be in a on condition. Fine? That is okay. Next, IN. There is one input called IN. So here is the one we need to give the input data. So which data you want to shift? That one you need to give. So I am giving one address for this since it is an integer. Since it is an integer block, I am giving MW0. Okay. And how about this N? What is this N? N is the place where you need to give how many bits you want to shift. Okay. So here also what I am going to do, I am going to give one address. Because in runtime I want to change that value, means I can make use of it. Fine. So in the next, I'm going to pick MW4. Right. So I'm going for online. Fine. So now all the values are 0. Fine. So same, to see the output, we need to go to the variable table. So I have already created the variable table for this MW0, MW2 and MW4. Right? So first MW0 should be a binary. MW2 is a decimal, because how many places you want to shift, that you will be giving in the decimal point. Okay? And the answer should be in a binary. So I'll give one random value here. So I'm giving 1010. Okay, so watch out now. I have given 0 0 1 0 and here everything is 0. Just I'll make 1 0 1 0 0 and 0 1 0 1 1 0 1 0. Now how many places I want to shift? I just want to give 4. I'll just give 4. So 4 places it will shift. 4 places towards right, since it is a shift right instruction, no? So 4 places towards right means this 0 will go, this 1 will go, this 0 will go, and this 1 will go. Okay, so the 0th bit is occupied with this 1. First bit is occupied with 0. Second bit is occupied with 1. Like that, these remaining bits are occupied with first 12 places. The remaining 4 places are filled with 0 because we are having 0 at the front, right? 16th bit is 0, so it is a positive value only, so the answer should be filled with 0. So let's go for yes. So can you see here? Can you see? These 4 bits are gone. Why these 4 bits particularly? Because I have chosen 4. So since it is a shift right, it will be shifting this side. So this 4 bits will go, and the 0th bit is occupied with 1 0 1 1 like that. Correct. So the remaining this side, the last 4 bits will be empty, and that bits are filled with 0 if your 16th bit is 0. If your input data's 16th bit is 0 means it will filled with 0. Okay, so let's do one thing. Now I'm going to give the same input, but I'm giving 2 places I want to shift. Let's go for monitor. So what happened? So I have just shifted 2. So only first 2 bits will go. So the 0th bit is filled with 0, first bit is filled with 1, second bit is filled with 1, fourth bit is filled with 0. Can you see here? Whatever I have told is listed here. And the same thing is repeated. Now the last 2 bits are 0. Correct? The last 2 bits will be empty and that bits are filled with 0 now. Got it? So this is how we need to do the shifting. Right? So now I'll go back to 4 and I'm running now. Okay? This is the first one we have done. Now what will happen if the 16th bit is 1? Let's see that. So 16th bit is 1 means what? My value is the negative value. My input data is the negative value. Correct? So let's see what will happen to the answer's last 4 bits. Can you see what happened? So the last 4 bits are shifted to 1 1 1 1. I mean it is replaced with 1 1 1 1. Because in shifting it will bother about the sign of the input. So as we all know, 0 means positive number, plus means negative number. Correct? So if your input is having 16th bit as 0, no issues. After shifting, it will be filled with 0 0. But if your 16th bit is 1, then your answers, in your output, that many places are empty, no? That is filled with 1 1 1 1. Okay? That is what shifting is. So this is shift right integer. Got it? So like that, we are having shift right double integer. So what it will do? It is nothing but a 16-bit value. That's it. So this is 16-bit instruction. I'm going to give MD8, MD12. Oh, okay. So here one thing you need to I want to clarify. This is double integer. This is also double integer, but the n we are giving, no, that is a integer. So I should give, that's what when I was typing MD, it was not accepting the address. So we should give the proper address. Got it? So what I can give, I'll just give one random address MW20 and here I'm giving MD12. MD12, right? Shall we go for online? Yeah. Fine. So for this I want to give in a variable table. What I need to give? MD8 Fine. So MW20. What is the last one? MD12. Right. So this is binary. And the n value, no, that will be decimal. And this should be again binary. So let's give some random value over here. Yeah. See, I have given some random values here and I'm going to give 2 shifting towards right. So see here, this 0, 1 will be gone. The 0, 1 will be gone. So last bit or the first 0th bit is filled with a 0. First bit is also filled with a 0. This 1, 1 is shifted here. Can you see here? Right? Since the last bit is 0, it is remains 0. So suppose if the last bit is 1, can you see? It is filled with 1. Right? Here we have shifted only 2 places. That's what the last 2 places are filled with 1, 1. This 0, 1, 0 is shifted here. Don't confuse. This 1, 1, 0 is shifted here. Got it? Fine. Any doubts? Okay. If you are any doubts, please let us know. We will be here to clarify all your doubts. Correct? So fine. So what is the next one we are having here is shift left word. So shift left. What is the purpose of shift left? What it will be doing? It will be doing towards the left side. Right? Yes. So let me share the screen again. What it will be doing? It will be doing the shift towards the left side. Correct? Yeah. So let me share. Let me give the address. So this is the word, no? So it is also our normal 16-bit. So shift left. Let's do that. Yeah. So in a variable table, if you see, I'll just give 2. So shift left means this side. This side it will move. It will shift. So this 1, 0 will gone. 1, 0 is filled here. 0, 1 is the here like that. So the last 0th bit and first bit will be empty. That is filled with, can you see? That place is filled with 0, 0. Okay. This is shift left word. So I have given 2 places to shift. Right? So it is shifting towards the left side. Got it? So I have given the input value here and I have given the 2 places we want to shift towards the left. So this is your output. So by using variable table, you can see the output very clearly. Right? So this is shift left word. And the same thing we are having shift right word. Okay. So in the shift right word, let's see what it will be doing. Shift right word. So I'm going to give the same address because it is a 16-bit. So let's go for online. Since the variable table is open, this will automatically ask us to, this will overwrite like that. It will ask you, just give with OK. Right. Shift right word. So let's do this. I'll change. Now let's give 3. Yeah. Now the output is updated. So 3 places it will go. Right. So 3 places it will move towards the right. So first 0th bit is filled with 1. First bit is filled with 1. Second bit is filled with 0, 1. So 1, 0, 1, 1. Can you see here? 1, 0, 1, 1. Now let's check. The 16th bit is what? 16th bit is 1. But see here, after shifting, 3 places are empty. No, that places are filled with a 0, 0, 0 here. So in our previous instruction, like shift right integer or double integer, if the 16th bit is 1 in the input state, so in output also the 16th bit will be 1 1 1 like that. How many places were empty, that many 1 will be there. But see here, I have done the same shift right only, but output is filled with 0 0 0. Why? Means this is a word instruction. So word will not store the sign value. Okay, it will not bother about the sign. Whether it is 0, it will be 0. If it is 1, that time also it will be 1. It will be 0 only. Right? So word bit will not store the sign. That is the logic. This is a difference between this shift right integer and shift right word. You should understand that. Right? So that's it. And we are having 2 more instruction in shift right double word, shift right again, shift left double word. So what it will be doing? MD, okay, I have given already MD address, right? I'll go with that. MW20 and this is MW12, I think. Yes. This is MD12. Yes, I have done that. Right. Let we go for the next instruction also so that we can see the output there. So let's see, I'm going to give the same address here, but we'll change that output address. I'll give MD16 to see the shift right double word. Okay. I'll go for online. Yes. So in a variable table, I'll give MD12 to see the output of So this is my left double integer. This is my right double integer. Here I should give 16, not 12. Okay. So see, this is my input. This is 2 I have given. So I have updated it. So what is MD12? MD12 is shift left. So 2 things shifted towards left. Can you see here 1 0 is shifted. So last 4 bits are built with 0 0 0 0. See here. So the last 2 bit will be empty. That is filled with 0 0. Right. Now the next one is the answer for the shift right double word. Correct. Double word. Shift right double word. So here these 2 bits will go and the first 4 bits are 1 0 0 1 1. Can you see here 0 0 1 1, right? And the last bits are filled with 0 0 since it is a word block. Since it is a word block, the last bits are filled with 0 0. Can you see here? Here it is 1 only, but still the last 31st bit is 0 0 only, right? So this is the shift logic in PLC. So this is common for all, but the instruction usage will get different softwares, different between the softwares. Okay. So right. So now we are going to do the rotation. So in shifting, whatever bits I am shifting, no, that will be going somewhere. We cannot able to see. Correct. The last 2 bit I am shifting means that 2 bits will go. It will vanish. Right? We cannot able to see those bits in the instruction. Right? But rotation is the one, how many bits we are removing, no, that will be coming and joining towards the other end. That is what the rotation is. Okay? Let's see that in instruction. I'm going to give the same address so that we can see the output in variable table. Okay, so I'll go for online. Right. So here I'll delete the first 3 so that it will not confuse you. Yes. Now this is shift left. This is shift left answer. This is shift right answer. I think yes. Yeah. The first one is shift right. This is shift left. Shall we see with the right? Okay. So now see, this is my input data, right? So now I'm going to rotate. It's not going to shift, it is rotate. So two things will go. This 0, 1 will go and join in the other end, means it will join here. Okay, it is actually shifting only, but after it got shifted, that 0, 1, 0, 1, the last 2 bit will not vanish. The first 2 bit, 0th and first bit will not vanish, but it will come and join over in the other end. Can you see here that 0, 1 is here? This 1, 0 is shifted this place. That 0, 1 we have rotate, no, that is rotated and come and join towards the other end. Got it? So the same thing, whatever happened here means, here this 1, 0, this side, it will be shifting towards left to right, and this 1, 0 will come and join in this place, this side. This is the corner, no? This is the other end. For this is the other end. For this one, this is the other end. Right? So this is what rotate instruction. Rotate means it will do the shifting and the bit we have shifted will not vanish, but it will come and join in the next corner. That is the difference, nothing else. Got it? So this is how we need to work with the shift and rotate instructions. It's very easy, but once we need to know how it is shifting, after shifting what will happen, that one we need to understand the concept. Apart from that, this is the very easiest one, right? So yeah, fine. So let meet you all in the next session. Until then, bye. Hello everyone. In today's session, we are going to see about the status bits. So let's start. So you can find the status bits over here. So we are having so many status bits. Can you find here? So the first one we are having here is exception bit overflow. The next one is exception bit overflow stored. Up next is exception bit unordered. And then it is exception bit BR memory. Okay. And the following 4 are normally closed contact of the above 4. Right? So this is a normally open contact of exception bit overflow, and this one is a normally closed contact of exception bit overflow. So now we are going to see these 4 instructions. Fine. So let's see how to use this. Now this is exception bit overflow. Fine. So if we are using an integer block, there is some limit for the integer block. Okay, up to some value only you can give. And what is that value means? It is minus 32767 plus 32767. Right? So I'll show one document so that you can understand that better. Yeah. So can you see the screen over here? So for the integer, we are having minus 32768 plus 32767. So suppose if you are using an integer block, take an addition block. If your answer is above this value, then that overflow bit will be turned on. Right? The same thing is for double integer. This is the maximum limit for double integer. So it is plus. This is minus 2147483648 plus positive value. Got it? And the same thing, this is for real value, floating point number. So this is the maximum limit we can use it for the integer block, double integer block and floating point block. Got it? So now let we see this, let we take the example for the integer block. Got it? So let's move on to our software. Yeah. So now what I'm going to do means I'm going to use one integer block. I'm going to take the addition block. Got it? So in the addition block, as usual, I'm going to give my address. Right. So suppose if this MW4 value is beyond 32768, what will happen? How come we get to know that the block is beyond the limit? right? So in such cases, we can make use of the status bit to show some indication, right? So what I'm going to do means I'm going to add one more rung and I'm going to add the status bit overflow, right? So bit overflow. So if this is like an input contact, right? So I'm going to connect one output here. Now let's see the working of this bit, right? See, now I have given already some values are stored in MW0 and MW2. So the value is in MW0 is 16256. So answer is also 16256. This is within the limit, correct? So this is the limit below 32767. Fine. That's what the overflow bit is off. Got it? Suppose if I change the value of this, yeah. So now see, if both the values are added, what will be the value? This is beyond our limit, correct? Can you see MW0 is showing some wrong value? Fine, it cannot able to add because this is beyond the limit of our addition block. So in that time, your overflow bit will be turned on. This is what we need to understand, right? So the same thing, for example, if I am changing the limit, I'll change this to 78. Can you see this is below the limit 32645. This is below our limit, so your overflow bit is in an off condition. Got it? So I'll do one more block I'll take here, that is normally closed contact of this overflow. So I'm going to connect one more output here. Okay, fine. So better I'll take that in a next rung. Overflow bit normally closed contact with one output, and that output I'm naming it as Q0.2. Got it? I'm going for online. So yes. So if you see the third rung, it is on. Why? Because this is a normally closed contact of OV. This is below the limit. So automatically this fellow will be in a off condition. So normally closed contact of OV is an on condition. That's what Q0.2 is in a on condition. Got it? If it is beyond the limit, let's see what will happen. It is also below the limit. I'll add 5 more or 10 more. Yes, now see. Now this is above the limit. So OV is on. Normally closed contact of OV is in off condition. Got it? So this is similar for double integer block also. I'll take the double integer block. MD0, MD4, MD8. Got it? So I'm going online. Yes. So this is beyond the limit. Okay. When you are adding both the values, that will be the beyond the limit. So, yeah. So now this is below the limit. It's not beyond the limit. That's what your normally closed contact is on. Can you see the answer? 2133074055. So this is below the limit. What is the maximum limit of DI? 2147483647. So this is below the limit. That's what this is off. This is on. Now I'll do one thing. I'll give some bigger value. Still it is below the limit. Better we'll use the variable table here. So we'll go to variable table and I'm going to change this as decimal. Yeah, decimal. So there is one negative value over here. That's what it is considered that as negative and putting it is doing the negative. So now see, let's change the value here to 1 4. I'll just give the maximum value here 3647. Yes. Yeah. So now what I have done, I have given the maximum limit in one place and some other random value in the next place. So this is showing some wrong answer. But how come we get to know this is a wrong answer? So by using the status bit, can you see the status bit is on? Because even the output is also not turned on. Can you see here Q 0.0 is also not turned on because this is beyond the limit. Your DI block maximum limit is 2147483647, but the answer we got is beyond the limit. That's what this has turned on. Got it? Suppose if I change the value here, I'll just add 0. Yeah. So now what happened? This is below the limit. This is exactly the limit whatever we have seen. 2 power 31 minus 1. So now see, this is below the limit. Got it? So this is how overflow bit will be working. Got it? So let's see what is overflow stored. Fine. So now what I'm going to do, I'm going to copy. Okay, I'll have clarification for this now. So now only one rung is overflow. So you are capturing that in next rung and you are putting the status. Q0.1 is the status if the bit is overflowed. Got it? Suppose if multiple rungs are overflow, how to get that status bit? It is mandatory to put the value, to put the rung. After every rung, we need to put OV. It will take some more rungs, right? It will occupy some space. So for all the 4 rungs, you need to add corresponding OV. Okay? So instead of that, we are having one option, that is exception bit overflow stored. So let's see what is the working of this. I'm just going to copy the same network and I'm putting here. So I'll change the address here. And here also I'll change the address. Better I'll give 12 here and 16 here. And this is also I'm going to change. Fine. Right. Now, instead of OV, I'm going to use overflow stored. Got it? Right. And I'm going to delete the 5th rung. This 4th rung I'm going to delete. I'm not going to use that. So I'm deleting. So let's go for online. Yes. Now, let's go to variable table. So again I need to add MD12, answer MD16, right? So this is gonna be the decimal and this is also gonna be the decimal. Got it? So yes. So now I need to give the new value here. Let I give some value. Got it? Oh, this is beyond the limit. Okay. Yeah. So now I have put some value and MD16 is the answer for that. Right? Now see. Yeah. So the rung 1 already we have seen, no? That is overflow. This is under only. This is below the limit only. This value is below the limit only. But previous rung of network 2, network 1 is having overflow. Right? So if you are using OS, overflow stored, that will be taking care of all the previous rung. In any one rung overflow is happening, it will be showing the status. Got it? It is overflow is only for the previous rung. Overflow stored is for all the rungs you have used before the OS. Got it? So for example, now I will change the value here. I'll change that to 0 So now that will be below the limit. Got it? Now see, overflow stored is not turned on. So status is also off. Got it? So if the same thing, if I have used the normally closed contact of OS, let's see what will happen. Instead of this, I am going to use overflow stored, normally closed contact, and one different output I am going to use. I'll use 3, and here I have used the multiple outputs, so I'm going to change that. Got it? So I'll go online. Now which one will be turned on? Can you guess? Yes, it will be network 4. Why? Because everything is within the limit. There is no overflow happening. So that time your normally closed contact of OS will be turned on. Can you get the point? Yes. So like this only we need to use the overflow stored. Got it? Yeah. Yes. So here I want to show you one thing. Imagine I'm going to use a overflow bit here. I just want to differentiate the overflow and overflow stored. I'll give one random address. Yes. Now see. Yeah. Now I have used both overflow and overflow stored. Got it? Suppose this block is going beyond the limit. Yeah. So this block is going beyond the limit. That is not captured by overflow. Got it? But can you see overflow stored is turned on? This is the difference between overflow and overflow stored. Okay. So why overflow is not turned on? Because its previous rung, network 2, is under the limit only. Got it? That's what this is not turned on. Overflow stored is on. Suppose if I go beyond the limit of this, that time your overflow will be turned on. Let's see that. Yeah. Can you see? Now overflow is on. That is the difference between overflow and overflow stored. I hope you have understood this. Now let's move on to unordered bit. There is one instruction. This is unordered bit. So what is the use of this? For that I am going to take a division block. Okay. So if any value which is unordered, in that case it will be turned on. Now see, I'm going to use the division block. Yeah. So if the MW4 is unordered, it cannot be expressible. In that case, your unordered bit will be turned on. Okay. Suppose if I change the value of this, your unordered bit will be off. Right. So this is the working of unordered bit. Then what will be the normally closed contact? It is just opposite to normally open contact. Right. So I'll use one output here. Actually, there is no need to use the output every time. You can see the rung condition itself. Let's see that. Yeah. It will ask for output for some cases because this is the input contact. No. Suppose if you have connected any counter or timer, that time output coil is not necessary. Since input contact is empty, we should connect one output contact. If it is a timer or counter, it will not ask for output. Even though if you are not connecting output, it will accept. Right? So what is the now unordered bit? Closed contact will be turned on, right? Yes. Can you see? Normally open contact is off. This is on. Okay. So now I'm going to change this to 0. See? It is on. It is off. Got it? So this is unordered bit. Okay? Yeah. So we have one more is pending, that is BR memory. What is that? BR memory. Let's see that. BR yeah. Yes. So since the time is running out, we will see the BR in the next session along with your result equal bit 0, result bit equal 0 and remaining 4 bits are there like this. And the normally closed contact of all the bits are there. So let me see these status bits along with the BR in the next session. Fine? Yeah. So until then, bye. Hello everyone. So in the last session we have seen about the status bits, and the fourth one we have seen was BR. So I'm going to start this session with this BR. So what is this BR? Exception bit BR memory. Okay. So if you click on that, it will come as a contact. Fine. It will come as a contact. So how to use this contact means, if you want to use a BR contact, before that you should use one more instruction, that is in a bit logic, which is none other than the save block. Okay, so we need to use the save instruction first. After that only we can make use of BR. BR and save is like a pair. Without save you cannot use the BR. Fine? Yeah. So I'm going to give a save. Save will be looking like a coil. Okay. So what it will do means, it will replace the memories. Okay. For example, if you want to turn on Q0.0 using I0.0 but not directly through one memory. So what you will be doing? You will be connecting one memory coil here. Correct? M0.0, and that memory you will be connecting here, and this will be your output. Right? So if you go online using that memory, this will be on. If you want to turn off, you can turn off. Right? So Q0.0 is on, and if you turn on using this memory, this will be on. I'll open the bit. Yeah. Can you see this is on? M0.0 is on. So using this we can turn on. But without using memory, how to turn on? Let's see that. So this was from our previous session, everything is in on condition. Now I have turned off everything. Now without using memory, I can make use of the save block. Okay, save, and here I should use the BR block. Can you see? Right? So let's go online. Yeah. So if I turn on I0.0, automatically Q0.0 will be on. So the save I have used is taking as a reference from the BR. From BR we are making Q0.0 to turn on. That's what the logic is. Okay. So how many BRs you want to use, you can make use of that. I'll just copy and paste. And again I'm pasting. So 3 BR I'm using with the different outputs. Let's see that. So here one output, and here also some other output. Right? So yes, I'm going online. Let's see that. So I'm going to turn on I0.0 only. Oh, so it is already in on condition. See, if I turn on, everything is on. Q0.0 is on, Q0.1 is on, Q0.2 is also on. Okay, so this is the use of save and BR. Right? For example, if I use one more save block, what will happen? Let's see that. This is, I'm going to use I0.1 with one save. I'll delete this first. Okay, fine. Now, in the next instruction, I'm going to use one more BR. BR with one different output. Let it be Q0.2. Okay. Now, we go for online. Yes. So, if you turn on the first save, only two outputs are on. So, previously three outputs were on, right? So, now, can you see here? I'll put it in a front. Yeah. Can you see here? Only Q0.0 and Q0.1 is on. See, Q0.2 is not on. Because if you are using save, the upcoming BR are corresponding to that save. If you are using the second save, the below BR are corresponding to the second save. Okay. So, this BR will not respond to the first used save. Okay. This BR. The BR we have used here is responding to this save. See, this save is not on. That's what this BR is also not on. I'm going to turn on that. Yes. So, now Q0.2 is on. Can you get the point? So, this is save and BR instruction. Fine. So, we are having normally closed contact of BR. This one. Okay. I'll replace this one with normally closed contact. Let's see what will happen. What will happen? Initial itself, I'll go for online. Yeah. Let's see that. So if I turn on I0.1, this BR is not turned on. So if I off, that time also it is not turned on. Okay. So what does that mean? Means BR will not work as normally closed contact of this one. BR should need condition along with this if it is a normally closed contact. Okay. So BR needs some condition to put over here so that Q0.0 will be in a on condition. So you cannot use the normally closed. See what will happen actually. See, this BR should make Q0.2 to turn on, correct? But this is not turned on because it needs some condition to happen. We cannot use normally closed contact of BR only in the run. You should use with one more condition. Got it? So this is save and BR memory. So let me move on to the next instruction, which is equal 0. Result bit equal 0. Fine. So before moving on to this, I'll take one integer block. I'll take subtraction block. I'll put one input and this is MW0, MW2. Yeah. So in the next run, what I'm going to use means I'm going to use this equal 0 block. So one more output here. Okay. So I'm going online. Yeah. See, this is not at all turned on. So imagine this is taking that MW4 as 0. So that's what this bit is on. Now I'm going to turn on this. Now see, the resultant is 16,000. So the result bit, the previous rung is not having an answer as 0. It's equal 0, but the previous rung is not equal to 0. So this is off. Suppose if I have changed this to 0, subtraction answer is 0. So this is turned on. Okay. So same thing, we are having a normally closed contact of that. Right. So I'll use that also. I'll use normally closed contact of this. And one more output here. I think this is not used. I'll use this. I'll go online. Yeah. Yeah. So this is on. Suppose if I change this, yeah. So this bit will be on. Got it? So if it is equal to 0, this will on. It is a normally closed contact, means it will be on. If it is not equal to 0. This is equal block. Similarly, we are having so many blocks, right? Greater than or equal to, less than or equal to, greater than equal to, less than equal to, not equal to. Fine. So let's see this. Greater than equal to I'll take. And this I'll take. Go online. Yeah. Now see, the answer is 45. Okay. So MW4 is greater than or equal to 0. This is the block, right? This is the one I have used. Right. Yeah. See, greater than or equal to 0. So MW0 greater than or equal to 0. That's what Q0.0 is in a on condition. I'll make this as some minus value, minus 9. Can you see this? This is turned off, this is on, because minus 9 less than or equal to 0. Correct? Suppose if I put this as 0, if I make this as 0, let's see what will happen. Both will be on, because both are equal 0. Because this is greater than or equal to, this is less than or equal to. Got it? So yes, so this is greater than or less than. Similarly, we are having normal greater than is there and this is less than is there. I'll do this. Yeah. So my answer is 0. 0 is equal to 0, but both the blocks are not satisfying the condition, so it is 0. Now I'll make one thing as 80. So 80 greater than 0. So this block is on. Correct? Yeah. So you should consider this answer. MW4 you should consider. So this block will be considered with this answer. So 80 greater than 0. That's what this is on. Suppose if I change the value to something. See, now it is again 2 is greater than 0. So I'll make minus 90. So answer will be 170. Okay, this is 80 minus of minus 9. Correct? So what I should do, I should increase the value here. Minus 200. Yeah. Plus 90 I'll give. Yeah. So if I give, the answer is minus 290. Correct? So answer is minus 290 means it is less than 0. That's what this is turned on. Fine. So the answer should be minus means this will be on. The answer is positive means this will be on. So this is less than or greater than 0. And the next one we are having is not equal to. If the answer is not equal to 0, this will be on. See, minus 290 is not equal to 0, so it is on. So let's do one thing. I'll make this as 90. So answer is 0. Correct? So that this will not be on. Right? This is equal to 0, right? So that's what this is turned off. So see, we are having all the whatever we have seen, same thing is listed here as normally closed contact. Right? So we'll do only 2 blocks now. So I'll take normally closed contact of this and I'll go online. Now it will be on because this is a normally closed contact. Even though the answer is 0, this will be taking normally closed contact. Correct? Yeah. So that's what. Now if I change the value, let's see what will happen. Answer is 10, which is not equal to 0, but this is normally closed contact. So it will be off. Fine. Yes, so this is how we need to work with the status bits. Fine. So we have seen all the status bits. So it will be giving some indication if according to the instruction. If it is overflow means that will be turned on. If it is stored, it will be turned on. Unordered bit BR. So everything comes under the status bits. So in next session we are going to see about the word logic. Fine. So we'll meet you all in the next session. Until then, bye. Hello everyone. So in today's session we are going to see about the word logic. Okay. So what is word logic? So if you expand this, you are having a 6 block, right? So this is AND for word, OR, XR, and next one is AND double word for OR and double word for XR, right? So this is first 3 is for the 16 bits and the next 3 is for the 32 bits. So now how to use the instruction, let's see that. Now I'm going to select the rung and I'm going to put this word AND, right? So since it is a word block, I need to give the word address, nothing but the integer address, right? So I'm giving MW2 and here also I'm giving MW4. So what it will do, what AND operation will do? So it will do the AND operation of MW0 and MW2 and store the answer in MW4. Got it? So let's go online. Yeah. To see the output, we need to go for the PLC and modify and monitor and modify variables that I have already opened here, and I have given MW0, MW2, MW6. Everything is in a binary I have given. Correct? Right? So I'll change the value over here. Yeah. So same for MW2 also I'm changing some values. Yeah. So I'm going online. So first, yeah. So the simulation part, this is also in on condition, correct? So let's check the variable table. What I have given the AND operation, right? So what it is doing? Okay. The one thing I mistakenly given MW6 here, but in answer I have given MW4. See, MW4 I have given. So I'll take a MW4 here and I'll update that. Yes. So can you see here 0 1 under means it will be 0. 1 1 1 0 0 0 0 0 0. Same thing. If you check here, everything is there. Right? See 0 0 0 1 0 0 1 0 0 1 0 0. So it is doing bit by bit AND operation. Okay. So this is your first input. This is your second input. It is doing the bit by bit AND operation and doing the result in MW4. Got it? Fine? Yes. So similarly, we can do for OR also by taking OR block. Let me do this. This is OR, right? Fine. I'm going to give the same input. Instead of giving different input, I'm going to give the same input but storing the answer in different address. Fine. Let's go online. Yes. Yeah. So now in variable table I need to update MW6. That's it. And that too in binary I want to view. Yes. Yeah. Can you see this is the OR operation output? 0 1 1. 1 1 is also 1. 0 0 0 0 0 0. 1 0 0. 1 0 1 0 0 0 1 1 0 1 1 1 1 1. So it is also doing bit by bit OR operation. Okay. So this is AND operation output. This is OR operation output. So what is the next one? We are having XR. I'm taking the block, giving the same input. I'll give 8. Fine, I'm going online. Yes. So here I'm updating MW8. And this is also in binary. Can you see the output? 0 1 1 1 1 0. So it is doing bit by bit XOR operation. So this is for the 16-bit operation. If you want to do it for the 32-bit, you need to connect a double word block. Okay. So here I'll give MD12, MD16, and this one is MD20. Got it? I'm going online. Yes. So I need to update the variable table with MG12, MD16 and MG20. Got it? So all three are again binary. Yeah. So this is doing the AND operation. So this is 0 completely. So this is also 0. Now I will update only this. Yeah. So now I'll update this also. So it is taking 32-bit, it is taking. So if you update this, can you see here only in 2 places output is on, because both are same in that place only. Okay. So similarly for OR operation you can give, and XOR operation also you can give. I'll replace this one with XOR, right? I'm giving the same address, MD12, MD16, and this is MD20. And here I'm going to give one more instruction, and that is XOR. Okay, for that also I'm giving same input, MD12, right? MD16, fine. And output I'm going to give as MD24. So that will be doing the XOR operation. So now what I need to do, I need to go for the simulation and I need to update the variable table, right? So I'll update the variable table with only MD24, and that is also a binary value. So can you see now it is doing the XOR operation. Both are 0 means it will be giving 1. Both are different means it is giving 0. So the first 3 instructions are for the 16-bit and the last 3 instructions are for the double word. 32-bit. Fine. It doesn't bother about the signature. It doesn't bother about the last bit. Okay. So that's what it is come under the data type as word. It is not an integer data type. So it is a word data type. It will be taking only the positive side. It will not store the sign. Okay. So this is the block completely for the word. Since word and integer are sharing the same address, we are using MW0, MW2. And for double word, double integer are sharing the same address, we have used the MD4, MD address we have used. Got it? So this is how you need to do the word logic in Siemens. So we have seen 3 logic gates over here. Fine. So this output I have told, I think in the previous session I have told. If it is an instruction, there is no need to connect the output. Okay. If you want to make the output like indicating that the operation has done, you can use the output like I have used this Q0.2. Fine. So yes, that's it about the word logic. So yeah, we'll meet you all in the next session. Until then, thank you. Hello everyone. So in today's session, we are going to do some exercise problem based on the concepts we have seen and the logic we have seen so far. Fine. So let's move on to the first exercise problem. Yeah. So when I0 is pressed, after 5 seconds Q0 is on. After 5 seconds Q1 is on. After 5 seconds Q2 is on. After 5 seconds Q3 is on. So they have given 1 input and 4 outputs. So when you press the input, after the 5 seconds of your I0 pressed, Q0 should on. After Q0 turned on after 5 seconds, it is like 1 by 1 in the interval of 5 seconds. Right? So let's see this in the software. Fine. They have 1 input and 4 outputs. Each output need to turn on with a 5 seconds interval. Fine. So since you are having like this, how many timers you supposed to use? You're supposed to use 4 timers, right? Because 4 outputs are there and 4 intervals are there. I have told you 4 timers not because of 4 outputs. It's because of 4 different time intervals. Fine. So let me see that in a software. So I'm going to take 1 input, right? 1 input and I'm going to name it as I0.0. Let it be, this is our main input. Fine. I'll make I0.0 is IO. In a question we have given they have given IO, no? That is the one. So when I0 is pressed, after 5 seconds, I want first output need to on. Okay. So what I'm going to do, I'm going to put one on delay timer over here, which is giving 5 seconds delay. Correct? Is 5T#5S. Hope you have remembered this. This is a format to give our preset value, right? So after 5 seconds, I want the first output need to on. So I'm naming this as Q0.0 as the first output. Fine. So what will happen when I0.0 is pressed? First output will be turned on after 5 seconds. Correct? Next. What next? The second output need to on after the 5 seconds of Q0.0. So what I need to do? You can take a reference from here or you can take reference from down. So what I'm going to do means, after Q0.0 turn on, I need to turn on a timer. So whether you can take this as a response, Q0.0 here or this T0, right? So I'm going to take T0. Fine. So after T0 turns on, I'm going to turn on one more timer and I'm going to name it as T1. I'm going to give the same preset value. Okay. And after this, I want the second output need to on. Got it? So how I'm taking the reference? First output turn on. After that, I need to start the second timer. So you can take 2 reference. One from this T0 or you can put this Q0.0 also. No issues. Okay. What I'm doing, instead of using output as a contact, I'm using the timer output as a input contact to the second timer. Fine. Then the next 2 steps are I'm going to repeat. What I'm going to repeat? Here I'm going to take a reference from this timer. At the end of the second timer, I need to trigger the third timer here. Right? And after that, I'm going to connect the third output. Fine. So here I'm going to give the same preset value with a different timer name, and this one is my third output. Got it? So I have repeated the same step, nothing new. Fine. And what is the last step? I need to turn on the fourth output after the third output and after 5 seconds. Correct? Yes. So all the outputs are turning on with consecutive 5 seconds interval. Right? So I'm going to take the reference from the previous timer. Going to give the name and same 5 seconds delay, and this is the fourth output. Got it? Fine. So First, what I have done, when I0 is pressed, why I have connected all the rungs after I0? Because this is the input condition. No timer should start before pressing of this. All timers should under the control of I0.0. That's what I have connected I0.0 as the root. Okay. Shall we go for online and check? Yeah. I'm going to turn on the I0.0. Okay. First output is not on. After 5 seconds it is going to on. Second output is going to turn on after the 5 seconds of Q0.0. Third output is also going to turn on after the 5 seconds of Q0.1, and it is repeating. Got it? Fine. It's done. So this is a sequence in ladder logic, one by one. See, I am taking reference for the second output from first rung end. Correct? Same thing here. I am taking the reference. Fine. Got it? So this is how you need to do the first exercise, and we have a subdivision of the first exercise. Let's see what is that. Yes, so this one we have done. Yeah, can you see here? For the above question, all output should turn off in reverse manner with 5 seconds duration of each output. So for the same question, they are asking us to turn off Q3 first, after 5 seconds Q2, after 5 seconds Q1, after 5 seconds Q0. First we have turned on one by one. Now we need to turn off one by one from last, reverse. Got it? Shall we see how to do that? Yes. So this is the half solution we have done. So what I need to do here? Q3 is on. Fine. After 5 seconds, this Q3 should go off. Correct? I'm right or wrong? Correct, no? Q3.0 should turn off after the 5 seconds of its turning on. Correct? So what I need to do? I'm going to take the reference from T3. And I'm going to turn on one more timer which will be giving the 5 seconds delay to turn off this. Got it? So what I'm going to do, I'm going to take the reference and I'm going to give the new timer name and same 5 seconds delay. This timer I'm going to give here to turn off the Q3. Okay, why I have given the normally closed contact? We know, right? To break the contact, to break the circuit, we need to use the normally closed contact. Got it? That's what I'm using this. And I'm going to repeat the same steps for the remaining outputs also. See, I'm going to do the same thing. Here also, I'm going to implement same. One more is pending for the first output. So see here, for this I'm taking reference from this. This is T5. This is same preset. Fine. This is again, this is T5. This is T6. T5. T6. And this one is taking reference from the previous. That's what it is. T6. This is T7. And this is the preset value. Fine. So by using T4, I'm turning off the last output. Correct. So by using T5, I'm turning off this. T5. And by using T6, I'm turning off the second one. And by using the last timer, I'm turning off this. T7. Shall we check that? I have used totally 8 timers here. I'll go online. I'll go for monitor. Yeah, check out here. So these are all the first 4 outputs now. See, after 5 seconds Q0.0 is on. After 5 seconds Q0.1 will be on. After 5 seconds Q0.2 will be on. And fourth output will be on. Okay. So after 5 seconds, what will happen? Fourth output will go off. See, it is already off. See, it is off. Next to this one. Next to this one. Next to this one. Fine. Yeah, that's it. And complete cycle is done. See. This timer, no, the last timer is used to turn off the first output. That's it. Simple. Fine. So this is how we need to do the first exercise. Got it? Sequence is very important. If you have missed the sequence, then your output will not be in the order. In which way you want the output need to turn on? In which way you want to turn the output to be turned off? For example, instead of the reverse manner, if they have told Q0.2 need to turn off first, means what you will do? You will be putting T4 here, T5 here, T6 here, T7 here. It is just the opposite of this. Got it? Fine. So let's do the next exercise. So let's see what is the next exercise. Exercise problem 2. Build a ladder logic for blinking of the light. 5 seconds on, 5 seconds off. Right. So it is like we have seen in the serial lights and all, no, blinking of that LED. We are going to do the same thing. How to do this blinking? So it is like automatic, right? Once you press the input, automatically the light need to on off like that. Some reset is happening in between. That's what the timer is again and again turning on, giving the 5 seconds, again turning off, giving the 5 seconds. Correct? So let's see how to do this in a software. So here you are having only one input because you need to give the input. Once you press the input, the output will be on for 5 seconds, after off for 5 seconds, again on for 5 seconds. So until I press the input condition to go false, it will be happening in a cyclic manner. Correct? Shall we do that? Yeah. So let's see how to do this. Yeah, I'm sharing the software. Hold on. Yes. So let's see how to do this. So now we are going to do the blinking. Correct? So you are having one input and one output. Correct? So this is the output you need to turn on and turn off with 5 seconds delay. This is I 0.0. This is Q 0.0. Let it be like this. Fine. Now this should be turned off after 5 seconds. Correct? So what I need to do, I need to take one normally on delay timer. And I'm going to give the name as T0 and this one as S5T hash 5 seconds. For example, if you want to see the immediate blinking, you just reduce the number of seconds. I'm going to give 3 seconds. So after 3 seconds, this fellow should go off. I'm right? This should go off like this. Fine. Now, what I'm going to do, I'm going to take one more branch. Why? Because it will turn off after the 3 seconds. But after 3 seconds, again it need to turn on, no? Correct? So how to do that? For that, I'm in need of one more timer. Fine? So see, I'm going to take one more timer. So when this timer need to start? When T0 ends. Yes. So I'm taking T0 as a reference here and T1 and same this one. Okay. So what I'm going to do? I'm going to, when this on, this should off. I'm resetting. So what will happen? If I reset this, this will go again to normally closed condition. This will be on for 3 seconds. Correct? Fine. Any doubts in this? Shall we check whether it is working or not? Shall we check? Yeah. So now what I'm going to do? I'm going to turn on. Yes, on for 3 seconds. Off for 3 seconds. Oh, I have given the 5 seconds over there. So it will be off for 5 seconds. Can I change that? Yeah, I'll change. Let's do one thing. Let's give for 2 seconds so that we can see the blinking nicely. Okay. Yeah. See? Off 2 seconds, on 2 seconds, again off 2 seconds, on 2 seconds. Correct? Fine. So until I turn off this will be happening. Okay. If I again turn on, it will again start from on, off like that. Got it? So this is how we need to do the blinking of light. Fine. So how many seconds you want, according to that you can give the timer. Fine. So I'm here using the on delay timer. Fine. So yes. So we have seen the 2 exercises today in this session. So we have 2 more exercise. Fine. So we'll see that in the next session. Fine. So until then, bye. Hello everyone. So in this session we are going to continue with the previous session exercise problem, and today we are going to see another 2 exercise. Fine. So let's move on to the problem number 3. Build the ladder logic for two-way traffic control system. So in the introduction classes I have told about the in traffic surveillance, like video surveillance and all, they are using PLCs. In foreign countries and all, people are using PLC for the traffic control. Fine. So let's do the simple logic for two-way traffic, and I'm going to give the four-way traffic control for your homework exercise. Fine. So let's see the logic. So since it is a two-way, you can take any 2 direction. Fine. So you can take north, west, south, north, like that. So for this exercise problem, I'm taking north and south. Okay. Since you are the programmer and according to the requirement, you can build the logic. Fine. So this is my logic. What does the logic means? When I press the start button or when I press the input condition to the traffic light system, immediately north green should turn on. Okay. And that time south should have red color. Okay. Because only one side should have a green color, right? Fine. So south people are having red color. Fine. So after 5 seconds, north is going to yellow and south is also going to yellow, because north is going to change to red color and south is going to change to green color. Okay. So whenever you are shifting from green to red or red to green, there should be a yellow. It's the program or logic in my program. Like that you can create any logic. You can create logic only when red to green change is happening. No, that time only you want yellow, means you can. That is also fine. Okay, the logic can be anything. According to the requirement, we will be building the logic. Okay, so for this question, what I have given is, if one side is green, another side should be red. After some time, the green is going to change to red and the red is going to change green. So in between, I want yellow. Okay, the same thing. When red is going to green and green is going to red, I want yellow to be happening. Okay, so why this problem is ended with only 4 cases? Why means, after this yellow, what will happen? North green, south red. That is what the first case is, right? Okay, so only 4 cases are the case. After that, it's going to be the cyclic action. Again, it will go to first and it will run. After the 4 cases, again it will go to the first. Like that, it is a cyclic action. Fine. Shall we see how to do this? So totally how many outputs we are having? We are having 6 outputs, correct? Because one side 3 colors, another side 3 colors. I mean LED or light. One side 3 lamp, another side 3 lamp. Red, green, yellow, red, green, yellow. Fine. So totally we are having 6 outputs. And we are going to use one start and stop push button also in this program. That's optional, but I'm going to use in this problem. Fine. Shall we see how to do that? Yes. We'll go for the software. Sorry. We'll go for the software. Yes, here is our software. So this is the previous problem we have done. So I'm going to take a new network. One is start push button, another one is stop push button. I'm going to save that in a memory. Since it is the push button, I'm going to latch it. This one we have already discussed. Okay. So what is this? I0.0 is a start push button. Okay. What is this? I0.1 stop push button. This is your memory coil. And this is memory you are latching. Fine. Got it? This is the initial one. So if you press and leave, it will be in a on condition only. So I'm going to use M0.0 in all the rungs hereafter. So when M0.0 is pressed, what is the first output we want to turn on? We need to turn on two outputs. What are the outputs? One is north green, correct? So I'll give one new address, Q0.0. This is Q0.1. So I'm going to write it in a comment section. Q0.0 is NG, north green. Okay. Q0.1 is south red. Fine. Got it? So I'm going to give the reference in the comment box for you. Fine. Now, when this fellow need to go off? After 5 seconds. Correct. So after 5 seconds means I need to give one timer, right? Obviously. So here I am taking one branch to give the timer, right? So T0, I'm going to give a 5 seconds delay. So after this 5 seconds delay, I want both the outputs need to go off. So I'm connecting before the output. I'm going to give T0, T0. You may ask me, since it is common, why can't I put a T0 here? Okay, so if you put a T0 here, it will make the timer to go off. Then how come I can turn off this? Can you get the point? So I want the output need to turn off, not the timer need to reset. Okay, that's what I have connected this T0, T0 separately. Fine. You should not put over here in this place. You should not put like this. It is wrong. If you put like this, this will be wrong. Okay, this should not happen. Fine. Right. So at the end of first timer, what should happen next? Okay. What is the first cycle? North green, south red. What is the next? North yellow, south yellow. Fine. So I'm going to connect two more outputs here. Okay. So Q0.2 and this is Q0.3. So here I am giving Q0.2 as north yellow, Q0.3 as south yellow. Fine. So this is gonna turn off. At the same time, this could gonna turn on. So I'm connecting like this. I'm giving reference from the previous round. At the end of T0, these two are going off. These two are going on. Simple. Okay. So at the same time, we need to turn on one more timer also because after 5 seconds, this should go off. Correct? I'm going to introduce one timer here. T1. Same 5 seconds I'm giving. So since it is a yellow, let's give it as 3 seconds. Okay. After 3 seconds, these two should go off. Correct? Yes. I'm connecting a normally closed contact, but because this will break the path T1. So this is gonna break. Fine. So what will happen? When this gonna break, what should happen next? Yes. What is that? North red and south green. So I'm connecting that output also here. I'll write here Q0.4 is what? North red. Q0.5 is south green. Correct now? Yeah. So what is the reference here? This is our normal M0.0 and this one is the previous timer. Correct? Fine. At the same time, I need to turn on one more timer. Why? Because this timer will turn off these two and turn on the yellow. Correct? That's what I am going to introduce this. Fine? And at the end of this one, T2 will make north red and south green to go off. What should turn on? Yellow. Do you need to connect the yellow coils again? No, right? Because yellow coils are already we have introduced. Fine. So you need to connect a parallel path here to turn on yellow again. Like this. Like this. Got it? Which timer it is? T2. T2. So Q3, Q0.2 and Q0.3 will be turning on. That is yellow for 5 seconds, right? After 5 seconds, what should happen? That should go off, correct? So I need to connect one more rung here to turn on the fourth timer. So this is as usual M0.0 and this is the previously used timer to turn on one more timer here. This timer is T3 and I'm going to give 3 seconds. So after the end of this timer, what should turn on? Turn off yellow, correct? Yellow should turn off. So I'm turning off both the yellow here. T3, T3, T3. This is also T3. What should turn on again? How about the question we have given? So we have done up to this. Up to this we have done. Now after that what should turn on? Again your green and red. So the output was already given, no? The output was already given. Where is the output? In the first rung we are having, no? This is our, no, not this one. This one. North green and south red. So this should turn on again. So how to make the cycle to happen again? Any idea? Because it was already done, right? So how to make that happen again? So for that we need to make use of the last timer to reset the first timer like this. That's it. So once you have reset, this timer will reset, no? That will make the output to turn on again. And the cycle will start from the beginning. Shall we see that? I'll go online. Let's check. So here, first two, this is north green, south red. Then both are yellow. This is north red, south green. Okay, I'm going to turn on. Since it's a push button, I'm turning off. See, for first 5 seconds, these two are on. Next 3 seconds, these two are on. Next 5 seconds, these two are on. Next 3 seconds, again yellow. Okay? Yes. So after 5 seconds, this cycle is again started. Can you see the cycle is again started? That's it. So whenever you want to restart the cycle from the beginning, you need to use the last used timer to reset the first one. Or you can use the reset coil or something to reset the timer. Fine? Which timer? First timer. Because if you reset, because you may ask me like, we have used 4 timers, but why we are resetting only one timer? Because all the timers are connected in a sequence with the first timer. So if you are resetting the first one, it will automatically reset all. Okay? That is the logic you need to understand here. So if you are very clear with the two-way traffic, no, then 4-way will be very, very easy. So in 4-way we will have how many outputs? Each directions are having 3 lamps. So we are having 4 directions. So 4 into 3, 12. Start and stop push button are 2 inputs and 4, 3, totally 12 outputs. Fine. So there also you can create your own logic. Here I have given yellow for all. You can skip that yellow for one thing. For like when you are shifting from green to red, there is no need of yellow. Like that also you can design the logic. It's a programmer thing. Okay. According to the customer requirement, you can give the logic. Same the preset value also. Preset value also you can change according to the customer requirement. Fine. Okay, fine. So shall we move on to the next exercise? Yes. So let's see what is our next exercise. I delete all the rungs first. We'll start from the beginning. Yeah. So the next exercise is also very interesting one. Yeah. Exercise problem 4. Automatic door opening system. Okay. So it is automatic door opening system. Any guess what it will be? In shopping complex or in mall and all we will be going, right? Whenever we enter near to the door, automatically the door will open. Correct? The door will be completely open till open limit switch. These two, okay, I'll discuss first what are the inputs here. So let me have start and stop push button as usual for all the problem. Okay, so those two are the inputs, and also open limit switch is one input, close limit switch is another input, object detective sensor is the input. Correct? So we are having totally 5 inputs. Fine. One is start and stop, open limit switch, close limit switch, and object detective sensor. We have 2 outputs here. One is open door motor, another one is closed door motor. Okay, so we are having 2 outputs here. One is open door motor, another one is closed door motor. I'll tell the logic. What it will do means, whenever a person is come nearer to it, automatically it will get open because object detective sensor will sense. Correct na? So when the sensor is giving the signal, the door should open. So open motor should turn on up to open limit switch. Fine. When the open limit switches happen, in that time also people are coming. So it will be waiting for them to go. So once the people are not coming, once the object detective sensor goes off, it waits for 10 seconds. Okay. Because in that 10 seconds some people may come, no? So after the 10 seconds, if people are not there, it will start closing up to close limit switch. Up to close limit switch. So while closing, if anyone comes, automatically it will open. Correct? Now that is the logic, right? If it is closing, if some people is coming, again it started closing means it is not a good programming. Correct? If someone is entering while closing, it should open again. That's the logic. Shall we see how to do this? Yes. So I think I should now delete the first rung. Okay, I'm going to delete the remaining rungs because first rung is same, no? For all. So let's see. This is my rung. This is my condition. I need to use all in all the rungs. Fine. So this is the one I'm going to use. So first, what I'm going to do means object detective sensor. Fine. So I'm going to put one object detective sensor here, which is detecting the people are coming. Correct? So that time what I need to turn on? Open motor. Correct? So this is my first output, open motor. Okay? I0.2 is object detecting sensor. Okay? I'm putting this D sensor. And Q0.0 is nothing but opening motor. Fine? Got it? Okay. Now opening motor is happening. Up to what? Up to open limit switch. So I'm going to put one normally closed contact here and I'm introducing that as open limit switch. I0.3 as open limit SWITCH switch. Fine? Got it? So yes. So this is happening. Fine? So in the next run, what I'm going to do, when this open limit switch comes, wait for 10 seconds. Correct na? That is what our logic is, right? When the opening is completely done, it will wait for 10 seconds. So for that 10 seconds, I'm going to use one timer here. Just for time being, we'll give for 5 seconds. Okay. So it will wait for 5 seconds. So in this 5 seconds, okay, so in this 5 seconds, if anyone is coming means it will be opening only. Okay, suppose after the 10 seconds, if no one is coming, what I should do? The motor should start closing. Correct? The motor should start closing. Fine. So what I am going to do, when M0.0 I am connecting here. Okay, fine. And here I am going to take a reference like this done bit of T0. I am going to use T0 here, right? Or you can put normally closed contact of object detecting sensor. What is our object detecting sensor? Because no people are coming, correct? That time I want closing should happen. So you to take the reference from this place. After that, you need to connect your closing motor. Let it be this is Q0.1 closing motor. Fine. Okay. Closing motor up to which one? We are having one more input here, right? What is that? Close limit switch. Correct? So I am going to introduce one more input here, and that is close limit switch. So up to that it should be closing. Fine. Right. For example, I need to connect if closing is happening. Okay. This is happening. At that time, if someone is coming means what should happen? This will get open. Correct. This will get off because object detecting sensor, this one will get open. No? So this will be off and again this fellow will go on. Correct. So what I am going to do, I am going to connect okay, let it be. I'll just run this. This is the logic. Let's see one by one. I'll turn off all because some memories are already in on condition. M0.0 is already in on condition. That's what in a question it is on. It's loading. Yes, so I'm going to turn off this. So let's start. Fine. So whenever you are starting, what is happening? Okay. Now the motor is closing. Fine. Because object detecting sensor is not on. No. So whenever you are turning on your object detecting sensor, opening is happening. Fine. See, opening is happening. Up to what? Up to your open limit switch. So when open limit switch is happen, your opening will be stopped because that limit switch is happened. After that it will wait for 10 seconds. Okay. That time your object detecting sensor is not there. Closing will be happening. See here. Closing is happening. Suppose in that time your object detecting sensor is coming. So that time what should happen? Again your motor should turn on. See, since it is a simulation, you need to turn off your open limit switch immediately. Turn off. Why? Because once it is started closing. See, I'll start from the beginning. I'm starting. Now object detecting sensor is coming. So opening is happening. Correct. Up to what? Limit switch. Correct. When the limit switch is there, a timer will be happening. Correct. So in that time, your person are not coming. That time means I need to turn off this. Closing is happening. When closing is happening, I should turn off this also. Because closing is happening. No. So when the close limit switches comes, automatically this will go off. Okay, see, when you are implementing this in a application, automatically sensor will give the signal. Since it is a simulation, to see the proper output, you need to turn on and turn off the input accordingly. Else, you will get confusion easily. Correct? So, you need to do the thing properly. For example, say I am starting. Object detecting sensor is there. Opening is happening. Open limit switch is there. So, it will wait for 10 minutes. So, after that, your object detecting sensor is giving 0. No persons are coming, means it will start closing. That time your open limit switch will go off. After some time, close limit switch will come. That's it. Can you get the point? So like this, you need to toggle the things properly. Fine. So that's it. You can stop. Fine. So yes, so this is automatic door opening and closing as a simple logic I have taught you. This is a simple logic. Fine. So like that you can expand the logic as per your requirement. Okay. So you can also put this one like interlocking you can do. What is interlocking means? When Q0.1 is on, this should not on like this. This is Q0.1. This is interlocking like safety purpose. If one is on, another one should not happen. Like that, you can interlock like this. Okay. This is optional only. You can interlock. Like both motors should turn on simultaneously for that. Okay. So this is the option. Apart from that, we have used various interlocking, right? After this only this should happen. When closing is happening, object detecting should not give input. Like that, this is also one kind of interlocking. See, I have used a normally closed contact. Fine. So yes, so this is how you need to use the logics according to your application and requirement. Fine. So we have seen 4 exercise in the practice sessions. So I'm going to give few more exercise for your homework. So I'm going to give the solution for that also. Please go through that and practice that. So we'll meet you all in the next training module. Fine? Yes. So until then, thank you. See you. Take care.